Hello, welcome to our module 2, and our goal here is to learn some basic commands that we have available in the Linux operating system, as well as some concepts that are required in order to work on this environment. So first of all, before we actually start discussing some commands, we have to briefly understand how the operating system works. Now, it is important to state and to realize that the focus of the CompTIA Linux Plus course or exam is not focused on understanding the how the operating system works. So this exam actually understands that you understand how this operating system works. So they assume that you have the understanding that is required, conceptually speaking, in order to work in this environment, because this is an exam that is focused on people, professionals that are already working in industry, doing jobs that are or tasks that are Linux based. So once again, the focus here is not to go through the history of Linux. It's not to understand how this operating system evolved. Our focus here is to understand how the operating system works in regards to the technicalities, in regards to how to treat the commands, how to interact with the end user or the admin. So let's just recap. And again, I'm assuming that you have some knowledge in regards to how the operating system works. But just to recap, this is an illustration of how the Linux operating system works when it comes to interfacing the hardware and the end user. So basically, the hardware is controlled and accessed by the operating system itself, which is the kernel. So the kernel is the operating system. It does not include softwares or applications that we use. Now, we cannot directly interact with the kernel. Well, actually we could, but it's way too complex. And the idea is to have the operating system being managed by a user or admin, but facilitating the tasks that are required by that user. So in order to allow the end user or the admin to interact with the hardware, we have the kernel in between. However, the kernel is not easily managed or accessed. Therefore, in order to facilitate the user's tasks, we have the software. So we have these 4 layers here. The user is interacting with the software. The software is responsible for translating what the user wants to do and sending that request to the kernel. The kernel will analyze whether those requests or functions are permitted, whether they are valid or not, whether they are permitted or not, and if they are, then the hardware instructions will be sent to the hardware, meaning that let's say that the user is trying to access the internet. So it will require, well, actually many devices will be requested. But let's say, for example, the network interface. So the kernel will send instructions to the interface, will receive data from that network interface. So in a very generic way, in a very rough way, this is how we as users or admins interact with our hardware when you're using the Linux operating system. Now, as I mentioned, the Linux operating system, as any other system, is basically composed by a main software called kernel. However, that is not the only software that we use. We need the softwares. It is important to understand that because this combination of kernel plus a set of softwares is what delivers us the concept of a Linux distribution. So Linux distributions are nothing more than a combination of a kernel, which most of the times is common to a major of the Linux distributions that we have available. It doesn't mean that different distributions are using the same version, but they are using the same kernel platform, the same basis. The difference between the distributions is basically it is the softwares, the set of softwares that will be embedded to that kernel. So the combination of kernel plus software delivers to us the Linux distributions. Regarding the Linux distributions, we have a variety of Linux distributions. We're just going to briefly discuss the main ones. So let's start off with the Debian distribution. So this distribution is actually base for many other distributions. For example, this distribution that we're running, that we installed in our first class, in our first module, which is the Ubuntu distribution. So Ubuntu is based on the Debian Linux system, and many other distributions such as Mint, Gentoo. There is a bunch of others. Now, why is it important to understand that you have this distribution available? The Debian distribution is well known for its package manager. A package manager is a software that will facilitate the way that you can manage applications, manage softwares. Let's say that you want to install a software, or you need to update or remove a software. Back in the day when we didn't have package managers, basically you'd have to get a hold of the source package, which would require you to configure, compile, and then install the softwares, the files. Now, with a package manager, it is a lot easier. Basically, especially the modern package managers, that they only require you to have internet access. Basically, obviously, it may involve some level of configuration, especially when it's the first time that you're using your system or you just installed it. But once your package manager is configured, basically all that you need is internet access. If you do have it, you just have to say, okay, package manager, I want to install this software. It is going to do everything for you and just tell you, okay, it's done. Okay. So the Debian distribution is well known for its package manager, which is called DPKG, or the internet-based package manager APT. We're going to have a class to discuss package managers, but it is important to know that because the exam, the CompTIA Linux Plus exam, demands from you to understand how the two main package managers work. One is the Debian package manager, so DPKG and APT, and the other one is the CentOS package manager, which is yum plus RPM. Again, we're going to have a class, we're going to have a module just to discuss that. So, as I mentioned, from Debian, we have many other distributions. One of those is Ubuntu. We also have Red Hat. Red Hat, back in the day, it was a free distribution, free as in charge and as in giving you access to the source code, which is, it is still a distribution that will give you access to the source code. The package managers, the repositories, and the support are not free of charge anymore. So Red Hat basically became a enterprise company. So based on that enterprise distribution, the same idea that we have the Debian distribution with other distributions coming from it, the same thing happened to Red Hat. Many other distributions came from the Red Hat distribution. One of those is CentOS. So CentOS is basically a free of charge distribution based on the Red Hat distro. We also have some other distributions such as SUSE or SUSE. It depends on the language that you're using. It is a German distribution. also based on the YUM and the RPM package managers. And another family of Linux distributions is Slackware. So Slackware is a Linux distribution that is based, it's based on the concept of Unix systems. So the idea of Slackware is deliver to the admin an environment that is so simple, and simple being not easy to use, but in the number of tools or resources that you have available. So the idea is not to embed too many softwares, too many resources to the admin, to the user, in order to make this distribution performable. So the idea is to have a very lightweight distribution which would deliver a better performance. And that concept comes from the Unix environment. So it is the distribution that has more similarities when compared to the Unix environment. And obviously some other distributions came from the Slackware distro as well. And many other distributions are also available. For example, Kali Linux and Scientific Linux. These distributions are specific distributions or subject-specific distributions. These are distributions that you can do anything that you could do in, let's say, Debian, Ubuntu, Slackware, Red Hat, CentOS. You can do the same things, but these distributions, they have a focus. The idea of using these Linux-specific distros is you're going to use it to perform specific tasks. So, for example, the Kali Linux is a security distribution. More specifically, it is a distribution for white hatters or pen testers or ethical hackers. So the idea of this distribution is to give you many resources that will facilitate your task if your role is to perform pen testing, test security. If you work in a scientific environment, doing research, doing science, you have one distribution called Scientific Linux that will come with many, for example, mathematical modeling tools, chemistry tools, publication tools. So you have these specific distributions. So these are some concepts that are required for us in order to understand and work with a Linux distribution. As you already know, the Linux distribution that we're going to use is Ubuntu. That's the one that we installed in our first module. I am going to go here to my Ubuntu. So once you initiate, you power on your system, this is the screen that you're going to see, right? You're going to have your user and you're going to need your password. So you log in and you're going to face this environment right here. Let me just close this message. And you're going to have this environment right here. Now, again, it all depends on the distribution that you're using. If you're using a Ubuntu distribution, by default, you're going to face the graphical environment. The graphical environment is very similar to use a system such as Mac OS X or Windows. So basically everything that you need to do or you want to do, you're going to use your cursor. Okay, so you have some shortcuts here and you have your menu right here. So you can see show applications, you click there and there you go. You have your utilities, your softwares or shortcuts to your softwares. Now, since our focus is not going to be on using the graphical environment, we have to understand the command line environment, the command line interface. The Linux operating system, as I previously mentioned, is basically the kernel. Now, in order to interface with the kernel, we have many available tools, many available resources. One of those is the graphical interface. However, system admins or network admins that are working with the Linux environment are supposed to understand and be able to work in the command line interface. The reason is the graphical interface is not only one software, but a set of softwares. And since the focus of a Linux admin is to manage servers, specifically secure servers, you should avoid installing, running additional softwares. So the idea is to run softwares that you actually need. Therefore, if you have a Linux server, you should avoid using this type of interface right here. You should use the command line interface. You can even have this graphical environment installed, but you should not run it. You should not have it running. Therefore, once again, we have to get used to the command line interface. For teaching purposes, what we're going to use is the terminal. So I'm going to click here, and it's going to open this command line interface, which I'm going to change the way it looks. But whatever I do here now is using the graphical, the command line interface. The proper environment, the proper graphics that you should see is not this one. I will, during our classes, during these videos, I am going to use this window right here, this tool called Terminal, but just to make it look better for you. Now, when you are actually using a Linux server, you are not going to have this graphical environment. You're going to have the actual command line interface. To go to the command line interface, you're going to press Function Command F3 if you're using if your Linux system is being virtualized in a Mac OS X environment, or Control Alt F3 if you're using a Windows system. Obviously, depending on the virtualization tool that you're using, this can differ, but basically that is the shortcuts that you're going to use. And this is the environment that you're going to face. So this is the actual command line interface. And when you see the command line interface, you're going to first see here a description of your system. So it is a Ubuntu version 18.0.3. It's a LTS version. And then your virtual machine name, which in my case is Linux-VirtualBox, and TTY3. That is because you actually have different terminals that you can use. So if I press here, again, I'm using a Mac OS X virtualizing this Linux environment. If I press Function Command F4, then I transition to TTY4. If I press Function Command F3, I'm transitioning back to TTY3. So you can transition between these different terminals, which shows you that it is actually a multi-user and multitask environment. I could, for example, log in here in my TTY3 as a user and in my TTY4 with a different user, or even the same user, and they're working at the same time. Now, so I am going to log in here with my Linux user, and there it is. You may see, and this may vary according to the distribution that you're using, but what is mostly important here is what we can see right here. So at the very bottom, we see the last line, Linux at Linux-VirtualBox, column, tilde, $. This is what is called the prompt, the command line prompt. This is the interface that will be displayed to you in order to interact with you. So this is actually the environment that you're going to use in order to type commands and do whatever you want to do. So basically, when you're managing a Linux system, this is the interface that you're going to see. This is where you're going to type commands that you need in order to perform tasks. And this is what we're going to use during our course. We're going to see so many different tools, so many different commands that we can use to perform whatever needs to be performed according to the focus of the CompTIA Linux Plus exam. Now, I'm going to go back to the graphical environment. There it is. And again, just for display purposes, I will use this environment from now on. So this class here was focused on understanding in a rough way how the Linux operating system works, understanding and knowing some of the main Linux distributions, and having a first contact with our environment, both graphical and command line interface. In our next class, in our next video, we're going to see how commands work, how to build commands, and get more familiar with this interface. I hope you enjoyed this class. Thank you. Hi, welcome to this class, and here we're going to see how to use the command line interface along with a few commands and the syntaxes, or how you can, we're going to discuss how you can build statements or build commands. And there is a very simplistic, basic structure that you can use to use commands. You're just gonna need the tool or the command that you want to use, and that is the hardest part. Understanding which command you have to use in order to achieve a certain goal or solve a specific problem. And then you're gonna have the options, the command's options, followed by the parameters. There is the very basic syntax. So a command would be like the command, options, where options can be either preceded by a dash or two dashes. Usually you have both options. So most commands you can use. So let's say that you want to see a version, for example, the version of that tool. A few commands or many commands, they have the -v option or -- version. So generally speaking, the options are going to be preceded by one dash if you're using just one single character to express, or two maybe, to express the option that you want to use, or two dashes followed by a entire word or description. But once again, that is just a generic rule. It doesn't apply to all commands. You actually have to check the main page or the help for that specific command. But in general, this is what you have: command space, let's make it brief like this, any options that you have available. Then if you want to, or if you have to, you have the parameters. And there are commands that they don't require any parameter. There are others that they do require one parameter, others that require two parameters or more. So once again, you have to check the syntax of the specific tool that you're going to use. So, for example, let's take a look at the ls command, which is short for list. So the list command, the ls command, is going to list the content of, well, if I don't specify any parameters, it is going to list the content or the files that are stored in my current directory. So first of all, let's take a look at the pwd command. It shows you where you are. So what is your current directory? What is the directory that you're working in? So right now I am in my home directory. Each regular user, well, that includes the administrator user as well, but each regular user has its own home directory, which is stored in the /home directory. So for example, here, if I use the command who am I, which does not require any parameters. So as you can see here, these commands, they do not require parameters. Actually, the ls command allows you to use parameters, but you're not required to. So as you can see, I'm only using the tools, no options, no parameters. So the who am I command is going to show which user I am using. So I'm using the Linux user. In the home directory, there's going to be a subdirectory for each regular user that exists in my system. So it's not the case, but let's say that I have the Linux 2 user. I would have Linux, because that's the home directory for my Linux user, and I would also have the Linux 2 directory that would be my Linux 2's my Linux 2 users directory. So the pwd command shows where I currently am. I am in my home directory, and I am going to use the ls command. Now, as we saw here, if I don't specify any parameters or options, it is going to list in this way, the content of my current directory. Let's say that I want to list, and you don't have to worry about this right now, but there is another directory which would be similar to the C drive in a Windows environment. So if I do ls space / I would list the content of that specific directory, not my current directory. Now, ls is a command that also allows you to inform more than one parameter. So what I did here was ls space /. That means I want to list the content of this directory. The / here is a parameter. The ls takes directories or files as parameters. Those are the files or directories that you want to list. Observe that I mentioned in the plural form. That is because you can use ls to list not only one directory or file, but I could do, for example, this. Now, let's see the result. I did ls space / space downloads. I'm saying that I want to list the content of this directory here and also this directory here. I'm passing two parameters, not only one. As we can see, that's the result right there. So this is the content of the / directory, and this is the content of the downloads directory. As we can see, the downloads directory is empty. Now, when I use space to inform something, such as here, and I don't precede that information, that data, with a dash or two dashes, I'm saying that's a parameter. If I want to use options, I have to use the dash or dash dash. Now, I am going to clear the screen here. In order to clear a screen, you can either hit Ctrl D, letter D, or you can type clear. They both do the same thing. Okay, so how do I see the parameters and I'm sorry, not the parameters, but the options that a command has, and also the overall syntax of a command? Generally speaking, you can use the -- help options. There are some commands that they have the -age option, just one dash with the age character. So there you go. I am going to scroll back up. So ls -- help And this is the overall syntax. You can do ls, the options, and the files, where the files are the parameters. And you can see here that it only says file, it does not say directory. That is because actually we're going to have a class to discuss that. We're going to have a video about that. But keep in mind, in Linux, anything is a file. A directory, a file is a file. A directory is a file. A device is a file. So let's say your monitor, it's a file. Your RAM memory is a file. Network connections, that's a file. So anything in a Linux environment is a file. That's why you see the file keyword here. Okay, so there you go. Now the options are, as previously mentioned, down here, where the letter that represents what you want to do is preceded by a dash, or if you want to use the keyword, not just a character, you're going to use dash dash. So, and here you have an explanation of what that option or those options do. As we can see here, the ls command has several different options. I am going to clear the screen again. One important detail here that we have to observe and we have to understand is what is called the command prompt. This is the prompt. The prompt is the interface that is waiting for you to interact, to enter whatever you want to do. Now, the command prompt is defined by the user at the machine name. And then you have a representation or the directory itself where you are working at the moment, and then a symbol that identifies whether it is a regular user or a admin user. So here I am logged in with the Linux user. I am using the machine Linux VirtualBox. This symbol, the tilt, tells me that I am in the home directory, my home directory. Let's say I go to the / directory. Okay, there you go. And this is the command that you can use to change directories. cd, change directory. So you say cd space the directory that you want to go to. Okay, so cd space /. Okay, now I am in the / directory. And then I have a symbol that tells me whether I am a regular user or the admin user. The $sign tells me I'm using a regular user. If I was logged in as a admin user, the root user, that's the admin user in a Linux environment, root. So if I was logged in with the root user, this symbol here would be a pound. It wouldn't be a $sign. Another way of analyzing the options of a command or even the syntax is using the man pages. So as we saw, I could do ls or any command. So let's say cp, that is a command to copy a file from one location to another location. Make a copy of a file, not move, but just a copy. Okay, but I don't know how to use cp. What are my options? What are the parameters that I have to use? Right, we know by now that we can use the -- help option. Okay, so there you go. If I scroll up, oh, there are many options here. However, for some reason, it depends on the command. Once again, it depends on the tool that you're using. But for some reason, I can't find what I want or what I need in here. Well, obviously, there are two options. One, there is no option to do what I want to do. Or two, there is an option. The help page is not just telling me. If you want to take a better look, a better understanding of a tool, you have to use the man pages, the manual pages. So I can do man space cp. And there you have it. Sometimes the man page is the same as the help pages. Other times it's much more complete. There is much more information in there. And to scroll up and down, you use the arrows, your keyboard arrows. There you go. If I'm done, I don't have anything else to analyze, I can simply use the Q character to quit. There, I just went back to the terminal. Now, we discussed that we have many tools, many commands to do stuff in a Linux environment. But only using these tools, these commands, sometimes is not enough. Because you have temporary information that should be used or that is there in the system. And you have to know how to deal with these temporary RAM information or data. That is why we have, and it's similar to any operating system, we have the environment variables. Those are just some variables or just a memory allocation, a position, a space in the RAM that will be created to store temporary information. Those are the environment variables. The system has some environment variables, but you can also create other ones, or you can change the ones that already exist. How do we work with environment variables? So if I simply type the env command, I'm going to see all the variables that currently exist in my system. Better yet, the environment variables that currently exist in the system and in my session. Because there are environment variables that they're associated with your session or with your environment. That's why they're called environment variables. Meaning that I can have a user here. I am using my Linux user. Well, so there is the environment variable called logname. If I log in with, let's say, the Linux 2 user, then the logname variable will have a different content, different data. That's because they are attached to the environment. Each user has its own environment. I can also have variables that exist for a specific user, but they don't exist to other users because I am allowed to create my own variables. And obviously, most of the times I don't want those variables to be accessed by other users. Okay, so here we can see some variables, and I can use the scroll to scroll up and take a look at those variables. Scroll down. But there is another option. So I'm going to clear the screen here. Control L to clear the screen. Or once again, clear. I am going to use env once again. However, now I'm going to use this symbol right here, a pipe. It's a vertical bar, a pipe. The idea of a pipe is allow you to connect one command to another command. The output of a command is going to be the input for another command. Because basically, that's how we interact with the system. That is actually how the system interacts with not only the user, but also with softwares. So ideally, the way that the kernel works is it will receive information, it will receive requests, it will receive data, treat that, and perform something. The tools are just the same, the softwares are just the same, as well the commands that we have available. They need some type of input, telling them what to do or where to apply what they can apply. Based on that input, they will generate an output. So, if I simply do env, I am giving an input, which is nothing. When I have a command that does not require any input, it will, well, that's a command that accepts no parameters. But what is the input? I'm telling the command that I want to simply invoke it. It knows that what I want to see is the environment variables that I have. The ls command can also, as previously mentioned, receive no parameters, but it can also receive one or more parameters. Those parameters are the input. Now, the output by default is going to be my display, my monitor. That's where the result goes to. But that is because the Linux system is based on default or standard input and default or standard output. The standard input, that's the keyboard. The standard output, that's the monitor, that's the display. I can change that. We can actually change that. So when I do this, what I'm saying is I want to run the env command, and the input is nothing. I could use commands that would receive parameters as input. But now when I use the pipe, I'm telling the env command, the result is not going to be sent to the screen. The result is going to be sent to another command. The output of the env command is going to be the input to another command. And here I am going to use the more command. What does the more command do? So more, let's say, more VM Linux. It's a file that I have here. It's a regular file. Okay, so it's going to show the content of that file. That's all it does. However, if I'm using a file that is longer than one page, it will display the first page. Okay, so this file here, /etc/services, this is a very long file. I want to see the content of that file. But since it's too long, as soon as it fulfills the first page, it will stop. If I want to go to the next page, I have to press the space bar. I'm going to press the space bar here. There, I can see the next page. So as I press the space bar, I'm going to go to the next page. If I'm done, I can simply hit the Q character and there. Just left the content. It's not displaying the content of the file anymore. So it opens a file with read permissions. It's not editing the file. It's just showing the content of that file. Okay, so I'm going to press Ctrl L once again to clear the screen. Now I'm going to do env pipe more. Observe that I am not passing a file as input to the more command here. And this is all I'm going to do. Why? Because the output of env is the input of more. There. Now the result of the env command will be presented, and as soon as the first page, my screen is full, it will stop. I have to press the space bar to go to the next page, and the space bar to go to the next one until the output is completely done. And that is what the more command does. Okay, so these are my environment variables. Now, how can I change the content of an environment variable, or how can I create one of those? First of all, let's take a look at a very important and very known environment variable, which is the path environment variable. There's the content. You can observe here that this variable actually has not just one content, not just a specific data, but a set of data. That's the first one. Then I have the column before I go to the second one, then another one, then another one, then another one, then another one. Now, this structure here is specific for the path variable. That's how it's been defined. Now, what does this variable do? I have to understand that before I actually change it or redefine it. A path variable defines the directories where the system is going to try to find the file that executes what you want to execute when you're typing a command. Okay, let's take an example here. I used, for example, several times the ls command. Well, the ls command is not a built-in function, is not a built-in tool, which means that it's not embedded in the kernel. It's an external tool, meaning there is a file called ls that actually executes what it has to execute, list the directory. But where is that file stored? You can use the which command space, the command name, and it's gonna tell you where it is. It's in the /bin/ls directory. When I type not /bin/ls, I don't want to use the entire path. I just want to use the command name. How does the system know what file it's supposed to run? How does it know that there is a ls tool in the bin directory? That's where the path variable comes in. So each of these paths here are listing possibilities of directories that may host, store tools or commands. When I type ls, it's very quick, but what the system is doing is it is going to the /usr/local/sbin directory, checking, is there a ls tool in there? No, there isn't. Then it goes to the second option. No. It goes to the third option. No. Then it continues until it reaches this directory here, /bin, and it sees, oh, there is a ls tool there. So that's what this user wants to run. And then it runs that specific command. So that is how the path variable is used, and the which command actually uses that variable to find where that specific command is located at. But now, how can I edit? How can I change the content of a variable? I have to, well, the basic way is doing, for example, let's say that I have another directory. So let's see the content of this variable again. To see the content of a variable, I can use the echo command. Basically, the echo command will send the result, you will send whatever you want it to show in the standard output, which is the monitor. If I simply say, for example, echo hi, it's going to simply return hi. Dispatch that to the default display. If I want to see the content of a variable, the variable name is path. But if I want to access the content of a variable, I have to use the $. The $sign before a variable name says I want to access the content of a variable. I don't want to add a content to the variable. I want to access the content. So echo $path. There it is. Now, let's say that I have another command that is stored in the /opt directory. It's not the case, but let's just assume that there is a tool, a command file in this directory, and I want to add it to my path variable. Simply put, this is what I need to do. There you go. What am I doing here? Okay, I'm defining a variable called path. Observe that I don't have the $sign here. And this variable path, which already exists, is now receiving a new value, which is the former content, plus this new content. There's the result. If we compare this with this, we can see that now I have the column /opt directory in there. However, there is a problem when I define a variable just by doing that. The variable name, the equal sign, and the content. This content is attached, it's linked to my current session, which means that if I open another session, so let's say if I do bash, what I'm doing here is open a new environment. So if I open a new environment, a new command line interface, a new command line environment, the content of the path variable will be lost. If I want to preserve that content, no matter which environment I'm going to, I have to export the content of that variable or export the variable. So this would be the correct way of defining a content. Okay, now I exported that content. If I open a new environment here, I will preserve that content. I'm going to clear the screen here. I can do the same thing to create a variable. So let's say that there is a variable, I want to create a new one, not manage or alter an existing variable. I just want to create a new one. What am I going to do? Same thing, but it's a variable that does not exist. So I can do export the hello variable, which will have hello world. There it is. Once again, when I want to put the value in, I don't use the $sign, I just use the $sign when I want to access the content of that variable. There it is. Now, we saw that we can actually use the pipe command to connect one command to another one. The output of a command is going to be the input of another tool. What if I don't want to connect two different tools? I just want to redirect the output or the input of a specific tool. So we also discussed that, let's say if I do ls, it is going to send the output of that tool to the standard output, which is my monitor. What if I don't want to see it in the display? I want to save the content, the result, in a file. Because when I send, which is the default operation, when I send it to the display, it's lost. If I clear my screen, as I'm going to do right now, there, it's lost. The content has been lost. What if I want to preserve it? I want to save it. You have to redirect that output. By default, the default output is the monitor. I have a couple of, well, actually I have a few symbols that we can use in order to redirect the output and some other symbols to redirect the input or to change the input. Mostly, you're going to work with output redirection, but you have to be aware that there is input redirections. Regarding the output redirections, first thing that we have to keep in mind, we have two different types of outputs. One is the standard output. That is, when you run a tool, when you use a tool, a command, and it works successfully, the output is going to be sent to one file. By default, that file refers to the monitor. Another redirection, another output is the error or the erroneous output. Let's say that you run a command, but it's wrong. The command does not exist, or you're passing a parameter that is not right, or you're trying to do something that is not possible. For example, you don't have permission to do such. Let's say that I try to list the content of the /root directory. The /root directory belongs to the admin user. Obviously, for safety reasons, a regular user as my Linux user, that's a regular user, should not be allowed to list the content of the /root directory. So the result is permission denied. This is a erroneous output. by default, the erroneous result is also sent to the monitor. But we can redirect those two outputs and we can redirect them to two different locations. So for example, I'm going to clear the screen here and I'm going to do a successful, run a successful command, simply ls. If I want to send this output to a file, I can simply do ls in the greater sign and the file, list success.txt. Oh, I can't be here, so let me go back to my home directory. Okay, so that's what I want to save in the list success.txt. Now observe that the output is not here, it's not listed. That's because it's now in the list underscore success.txt file. And I can use many tools, many commands to see the content of a file, such as the more command that we discussed. But another one is cat. It will simply just show the entire content. It's not going to stop every page. There it is. So the same result here. Now it's not in the display, it's in that file right there. If I do, let's say, list my downloads directory and redirect it to the list underscore success.txt, okay, it worked. But let's take a look at the content of that file. It's empty. It's empty. The reason is the downloads directory is empty. And I'm using just one greater sign here. The one greater sign, what it does is it erases the former content and replaces by the new content, which is nothing. If I want to append the content, so let me do this one again. There's the content of my current directory. If I want to append the content of the downloads directory, I use two greater signs. Well, nothing has been appended here, but that's because the downloads directory is empty, but the former content has been preserved. It's still there. If I want to redirect the erroneous output, such as this one, if I do this and observe here that if I start to type a command or a file name and I press the tab key, it will complete the command for me. Okay, so I'm trying to list the content of this /root directory and save that in that file. Well, let's take a look at the file content. It remains the same, and that error message that I wanted to save in the file is still in my display. It hasn't been redirected to the file. Why? That's because if I want to redirect erroneous messages, I have to use the number 2 before the greater sign or the two greater signs. Okay, now the erroneous result is not shown in my display. And let's take a look at that file. There it is. It's been appended to my file. If I want to redirect the input of a command, not the output, but the input, I can simply use the less sign. So, for example, let's say that I want to remove the list success file. Oh, so let me create it again. Not -f-i. Okay, so what am I doing here? The rm command stands for remove. That's the command that you want to use in case you want to remove a directory or a file. And I am using the -i option. That's an option that will actually ask me, are you sure that you want to do that? And then I have to answer yes. What if I don't want to answer that? Let's say that I have a file that has the answer that I need. I could redirect. So let me create it again. I could redirect that. Well, the file does not exist, but that's what you could do. So you can redirect the content of a file to this command. That would be the input. The answer to my command would be the input. So these are mostly the important concepts and resources that you have to be aware when using a Linux environment. Some additional resources that you have is using the history. If you simply enter the history command, it's going to display the last 500 commands that you used so far. Obviously, if you haven't used so many commands, it's going to show less. So history, there it is. So I have here the previous 29 commands that I used. Now, if I want to find a specific command that I used, you can hit the Control plus R, and you start typing that command. So I want to go back to a command where I, let's say, see the content of the path variable. You don't have to remember the beginning of the command. It can be any part, any string that you used. So let's say path. Oh, there you go. So it's showing me that I used this command, echo $path. But that's not the one. I can continue to hit Control R. It's going to go to the other ones. Okay, that's done. Those are all the commands that I used with the path string. If I am pretty sure that I want to run again a command, and I know which command I'm talking about, and I want to run again that command exactly the same way that I executed it. So in the command line interface, you can use the up and down arrow to go back to the commands that you used. So I'm gonna go up, and okay, so the last time that I used the ls command was this one, ls/root, redirecting the erroneous content to that file. This is the command that I want to run again. You can use !ls there. So the exclamation point plus just the beginning of a command, it will run the exact same command that you ran for the last time, beginning with that string. So here in this class, we saw how to create commands, how to check how a command syntax works, how to find help in order to build a command. We learned about options, parameters. We learned about environment variables, redirection, and piping, where redirection is redirecting the output of a command to a file, and pipe is redirecting the output of a tool to another command. So these are some very important concepts and resources that we have available and that you must know when you're working in a Linux environment. And obviously, these are requirements when taking the CompTIA Linux Plus exam. I hope you enjoyed this class. Thank you very much. Hello, welcome to this class, and today our module is going to be focused on user and group management. So in order to work in a Linux environment, you have to first of all understand how users are differentiated and defined, as well as groups. So first of all, we have to understand how the Linux operating system treats users. So there are three basic different types of users. We have the regular users, which are the users that we actually use in the system. We have the administrator users or admin users, which are users that have full power in the machine, which means that those users can perform administrative tasks. For example, they can change the network configuration, they can install and remove software, they can even change other users' configuration. And we have the system users. The system users are users that are not supposed to be used by an end user. It is possible to. So it is possible for an admin or a regular user use a system account. However, that's not the purpose and should be avoided. Now, how does the system differentiate these users? The first thing that we have to look at is the /etc/passwd file. So let's take a look at this file. I'm gonna more this file right here. Let me clear and okay, so that's the file. /etc/passwd. There we go. Now, observe here, as mentioned before, the admin user in a Linux environment by default is called root. However, the system itself does not know the root user. What the Linux kernel knows is user IDs. Each user has its own identification number. The admin user has identification number 0. That means that this user right here is the admin. That is why we use the root user as the admin user. We could perfectly change this name here. There would be no problem. So the way that this user database file works is you have rows, you have lines, and you have columns. Each user is stored in one line, and the columns are used to identify some information or define information about that specific user. So for example, here I have my root user. The second column identifies the password. It's been a while that the password has been moved, actually more than 20 years, that the password has been moved to another file, /etc/shadow, which we're going to talk about today. So, but before it was stored in this file here. When they decided to move this the password to this other file, they decided to keep this column identifying with the letter X, which means that it's just informing that the password, which is not the actual password, it's the hashed password, is stored in the /etc/shadow file. Then in the third column, we have the user ID. This number must be unique. Each user must have a different UID. This is the GID or group identification, group ID. This identifies the main group that the user belongs to. It doesn't mean that the user only belongs to one group. It means that this is the main group. So a user can be part of many different groups, but that user must have one main group. This number here identifies that group ID. Then we have just a description of that user. It can be any text, it can be empty. It's a description. Then in this column, we have the user's home directory. So the home directory for user root is /root. And then we have the program that should be executed every time that user logs in. Well, as we can see, if we compare the root user, the admin user, with, for example, these users down here, which are system users. These system users here, once they log in, they're supposed to run the command, the tool, /usr/sbin/no login. This is a tool that will actually force the user to log out. So whenever we try to log in with the system user, we won't be able to. Now again, it is possible to change that, but by default, that's what happens. The system users are going to start with ID ranging from 1, and it may vary according to the system, but modern Linux systems go up to 999. So from 1 to 999 are system users. And then starting in 1000, we have the regular users. So this is the user that I created during our installation. That's the Linux user. The password is stored in shadow. This user's UID is 1000. Its main group is also grouped with group ID 1000. It's just a comment about that user right here. This user's home directory is /home/Linux. The regular users have their home directory stored in this /home directory. And when I log in, I'm going to execute, the system is going to execute the /bin/bash, which is the command shell. I will have access to my command line interface. So that's how the Linux system differentiate users. Now, I'm going to clear the screen here. We also have to be able to create users and change configuration about those users, as well as remove users. Now, depending on the system that you're using, you can get access to the shell, to the command line interface, directly using the root user. That is not true in the Ubuntu system. So in a Ubuntu system, the root user cannot be used to log in. However, I can use my regular user, and that is the user that I created during the installation. I can use that user, in this case my Linux user, as a admin user. But whenever I need to run a command that is a admin command, I have to precede that command with the sudo command. So actually I have to put two commands together, sudo and then the administrative tool that I want to use. Now, how can I create a new user? So if I am a regular user, I can do sudo and then the user that I want to create. So let's say that I want to, the command followed by the user that I want to create. Let's say that I want to create a new user called new user. I'm going to do sudo user add new user. It's going to ask me to define a password for that user. But first, I have to actually inform that my current user is a admin user because I'm running the sudo command. Just to make sure that I am the regular user with permissions to run administrative commands, I have to inform my user's password. It's not the admin user's password. It's not the root's password. It's my own user. So my regular user's password, my Linux user's password is Linux. I type that in. Okay, it's created the new user. How do I know? How can I be sure that the new user has been created? Okay, I can go back to the /etc/passwd file. If we go to the last line, I can see there, new user, its ID is 1001, its main group is 1001 as well, its home directory is /home/new user, and whenever that user logs in, it's going to run the /bin/sh, which is the born shell, not the born again shell. There is a difference between the shell or the born shell and the born again shell. Why did this user was created with the born shell as a default shell and not the born again shell? That is because I created that user using the the user add command and not the add user command. Let me see new user, or let me just list the content of the /home directory. Another problem of creating a user with the user add command is that the home directory is not going to be created by default. As you already know, when we create a user, we're supposed to have a home directory for that user in the /home directory. Well, I don't have the new user directory inside the /home directory. Once again, that's because I created that user using the user add command. Let me create a user using the add user command, new user 2. Now, you can see here that now I have to inform a bunch of other information. I have to, it's going to ask me a password for that user. I'm going to say new user 2, just as the user login name. I have to type it again, new user 2. It's going to ask some other information, full name, new user, room number, work phone. So you can define all those information. If you don't want to, you don't have to. And it's going to confirm, is the information correct? If it is, I can just hit enter. If it isn't, I hit N and then enter. Yes, it is. Now, all this information that I've been asked for, full name, room number, work phone, home phone, and other. If we go to the /etc/passwd file, there, I can see that all the information that I respond to the add user command is going to be placed here as information about that user, which is a comment about the user, which is optional. Now observe here that the shell, the default shell now is bash. It's not sh. Also, if we take a look at the /home directory, and I'm going to clear this screen here, the new user directory is there. It exists. Another difference is that when we create a user with the user add command, it's not going to ask a password for that user, which means that I would have to, so after I create a user using the user add command, not the add user, after I do that, I have to define a password for that user using the passwd command. New user, that's the password. Okay. Otherwise, that user wouldn't have a password, which means that I wouldn't be able to log in with that user. When we use the add user command, that's not necessary because it asks for that password during the user creation task. Now, after we create a user, we can also change user's information. For that, I can use the user mod command. And there is a bunch of options. Basically, I have all those information that we have in the /etc/passwd file, such as the user ID, obviously, username, user ID, main group, comment, whether I want to create a home directory for that user, and if I do, what is that home directory, and also the tool or the command that should be executed once that user logs in. So, user mod, let's take a look at that. Let me do a pipe more here because I wanted to stop once the screen is fulfilled. So, user mod, then we have the options and the login name. -C if I want to define a comment or change the comment. -D, new home directory for the user account in case I want to define the user home directory or change it. Now, it is important to realize if I have a user that already exists and I'm using user mod to change its user's home directory, I also have to make sure that I use the -M option. Because if I just change the user's home directory with the -D option, I am saying, okay, this user now will have this other directory, but the files that are stored in the previous home directory are not being moved to that new directory. So make sure that if that's the case, you always use the -m option as well. Now, we can see some other options here that are not related to those data about users that we just saw. There are some different ones here, such as expire date, inactive, password, unlock, and some others. So there are some additional information about users. First of all, we've seen that we can use the passwd command to change or define a user's password. However, I can also use this tool here, this command, to lock, -L, to lock a user's password, or unlock it after I lock it. But I can also use user mod to do that. So if we go here, we can see that, and where is the option? We can see that we can unlock and we can lock, which is different when using user mod, because if I use passwd, so passwd-l, let's say new user, or to unlock -u, but you can see that I'm using lowercase l, lowercase u. If I use user mod, I have to use uppercase letters for these options specifically. But they do exactly the same thing. Some other information about users that we have is regarding their password. Now, we saw that in the /etc/passwd file, we have some data about users, but the data about passwords is not stored in that file. That's because it is in the shadow file. And if I try to simply look at the content of the /etc/shadow file, I won't be able to. The reason is I have a regular user right here. Well, obviously, if I want to analyze a file that stores users' passwords or hashed passwords and information about passwords, I have to be a admin user, which means that I have to use the sudo command. Once again, it's default in a Ubuntu system. There are other distributions that will allow you to log in with the root user. You wouldn't have to use the sudo command. Okay, now, what do we have in this file? Similarly to this /etc/passwd file, I have one user per line. If we observe a few users here, for example, the root user, we can see that there is an exclamation mark over there. It means that that user is locked. I cannot log in with that user. It's different from a system user where they are not locked, they just don't have a password. I could define that password. So, well, I could unlock the root user if I want to log in with that user, and I could define a password for system users in case I want to log in with a system user. Now, if we scroll down and observe the regular users, the second column, and the column delimiter here is the column symbol. In the second column, I have all this information here, all this information here, and all this information here. And what is this? This is the hashed password. So the password is not stored in clear text, but it's not ciphered as well. It's not being encrypted. It's a hash. And there is a big difference between a hash and a ciphered text. A hashed text is a one-way scrambling, which means that if I am in possess of this information here, I cannot go back to the original information, which is different from a ciphertext. If I have the key, I can get the ciphertext. If I have the key, I can go back to the original information. So how does the system work? Well, actually, this information here, right here, is called salt. When we define a password for user, the system is going to randomly generate a salt. With that salt in hand, I use a specific hashing algorithm over a clear text information, then that hash text is going to be generated. But this hash text here is only going to be generated if I use the same clear text with the same salt. So what does the system do when we try to log in? So let's say that I'm trying to log in. I will have to inform my user, for example, Linux, and the password. I type Linux. What is the system going to do? It's going to go here to this file. It's going to capture, it's going to look for that user. Okay, so the user is trying to log in with the Linux account. What is the salt for the Linux account? That's the salt. So the system is going to use this specific salt on top of the password that the user just informed. Now, since it's the same, if it's the same password that's been informed by the user with this salt, then the resulting hash is going to be this one. The system is going to compare the resulting hash with this hash here. If it matches, then that means that the user informed the proper password. If the system didn't have access to this salt, it would randomly generate another salt, which means that the hash here would not match. So that's how it all works. We also have some other information here. And what is this information? This is information about the user's password. Let's take a look at the shadow man page. A shadow or a password has all these options here. So what we see in that file is, first of all, it says encrypted password, which is not actually encrypted, it's hashed. Then we have the date of last password change. It's an epoch, which means that it's a number of days after January 1st of 1970. So the number that is stored there is actually the number of days after this date here. We also have the minimum password age. It means for how long in days does a user have to keep the same password once he changes his or her password. We also have the maximum password age. We have the password warning period. So before the password actually expires, how many days before that the user will start receiving warnings? Your password is about to expire. Change your password. And password inactivity period, that is the number of days after a password has expired that the password should still be accepted. So let's say that 7 days before, that's the default, 7 days before the user password expires, the user will start to receive some warnings. Your password is about to expire. Then 6 days, the user will receive that warning again. After that password expires, then we have a number of days that will define how many more days the user will have to change his password. It's a grace period before his account or her account is actually locked. And this is the account expiration date. So these are this information right here. So the number of days after January 1st of 1970 that the password has been changed or defined, the minimum number of days before changing the password, the maximum number of days, how many days before the password expires, in which the user will start receiving warnings. Then we have the maximum number of days after the password expires, that the user will have a grace period. That's the grace period right there. and this is the expiration date. So we can see that none of my users have a expiration date defined. Now, it would be way too complex to edit this file to change this information. So we need a tool, a command that would allow us to actually define that. And yes, we do have that tool. So we can use the changeAge tool to redefine all that. So if we take a look at the changeAge or changeAge tool, there it is. We have all these options here to define, to change those password data. Now, regarding users, we also have the userdel command. Now, observe here that if I try to remove a user, let's say the new user 2. So the user has been deleted. If I try to identify new user 2, no such user. And observe here that I'm using the ID command. The ID command is the command that can be used to gather some information about a user. First of all, if that user exists, and then some other information such as what's the group ID, which group or groups the user belongs to. So let's say ID new user, there it is. Now, let's take a look at the /home directory. I removed the new user, but I did not remove its home directory. That is because I removed that user using the userdel command, but I did not use the -r option. If I want to remove the user's home directory, I have to use the -r option. Obviously, it's not going to work here because this user does not exist anymore, which means that I have to manually go there and remove that directory in case I don't need that user's files either. So another command that we have to know is the rm command. In order to remove a file, I could simply do sudo rm and then the file name, but that's not the case. I don't want to simply remove a regular file. I want to remove a directory, which means that I have to use the -r option. And then I can remove that user's directory. There it is. Now, understanding user IDs and group IDs is very important. For example, one very interesting tool that we have available is the find command. And find allows us to search for files in our storage device, in our file system. Basically, the syntax is find the location from where the command will perform the search. It's a recursive command, which means that whatever the directory that I inform here is, it will also try to find that file that I'm looking for in the subdirectories. So if I do find space /, it's going to search for a file, the file or files that I'm looking for in my entire file system, because the / directory is similar to the C drive in a Windows system. And then I have options. For example, I could use here user 1000. Just to make this search quicker, I'm going to perform this search starting on my current directory. There it is. So all these files here, they belong, all these files, they belong to user 1000. And which user is the user 1000? It's my Linux user. So in my current directory, /home/Linux, I have a bunch of files that belong to user 1000, which is my Linux user. Well, obviously, it's my home directory. But what is important here is you can search for files defining a user. I want to look for files, search for files that belong to this user here, and you can use the user ID. Now, we also have commands to deal with groups. First of all, similar to the /etc/passwd file, we have the /etc/group file. Oh, too quick. I'm sorry. Let's go back there. /etc/group file. But it's a much more simplistic file. We have the group name. Groups can also have password. Similarly to the /etc/passwd file, the group password is not stored in this file. It's stored in the /etc/gshadow file. That's the shadow file for groups. We have the group ID, and then we have a list of users that belong to that group. As we can see here, my Linux user belongs to the SamboShare group as well. Now, we can see that we have a group here called Linux, which has group ID 1000. However, my Linux user is not listed here as belonging to the Linux group, and it's not required to. When I define that my user, in this case, my Linux user, and it's defined in the /etc/passwd file, that its main group is the Linux group because it's the group with ID 1000. So, okay, let's take a look at my user here. So, my user, Linux, which has UID 1000, has 1000 as its group ID, main group ID as well. I'm saying that my user's main group is the Linux group. And the Linux group has group ID 1000. Now, since my Linux group, my Linux user has the Linux group as its main group, I won't have that user listed here. So we only list users that do not have that group as its main group. For example, I want my Linux user to belong to the SamboShare, but the SamboShare group is not my Linux user's main group. Then I have to add the user to that group. We can create groups using the group ID, group add command. For example, new group. And then we have the group mod command, which allows us to add users to that group, or we can also use the user mod command to say, I want to add this user. For example, I want to add my new user to the, new group, new user. Now, observe here that if I use user mod with the -g option, lowercase g, to add my new user to that group, then the user's main group becomes that group that I defined with the lowercase g option. Well, let's say that I want my new user to remain in the new user group as its main group there. But I also want to add this user to that other group, but it should be a secondary group. So I can use the -G option. And there it is. If we observe here and compare with this, new users is still using new users as its main group, but it now belongs to the new group as well. It's part of the new group as well. And we also have the gpasswd command, which similarly to the passwd command will allow us to define, the passwd command allows us to define password for users, and we have the chage command, chage command, or change age command to define some information about a password. We have the gpasswd command to define passwords and some data about group passwords, but it's specifically for groups. I can also use the gpasswd command to add users to a group, delete users from a group. Okay, so we've seen these commands to manage users and manage groups, but we also have to understand what happens when a user logs in. Let's take a look at my regular user's home directory. And we have, along with the ls option, we have the -a option. It's used to display all files, not only files like this, visible files, but it will also display hidden files. In a Linux environment, file names that begin with dot are going to be hidden. So as you can see here, there is no files being listed that begins with the dot. If I want to see hidden files, I have to use the -a option. Now, first of all, where do these files come from? Because as you may remember, the only task that we performed so far was to install the Linux system. We installed the Linux system, created this default user, this regular user here that I called Linux, and all these files were created there. First of all, we saw that when a user is created using, for example, the add user command, its home directory is going to be created, automatically created in this /home directory. However, there are many files that are going to be created here, except for, so let me remove, this file is not created by default, and this file is not created by default. So when we create a user there, all these files here are being automatically defined. Why is that happening? There is a directory in the /etc/scale directory. That's the directory, /etc/scale, that defines files that should be copied to the user's home directory when that user is created. Now, you can see here a bunch of other directories that were created in my home directory, but it's not there in the scale directory. That is because when you log in with a user in the graphical environment, those directories are created. So it has nothing to do with the scale directory. This is a characteristic that is inherent to the graphical environment. If I don't log in the graphical environment, there is still a bunch of files that will be created in the user's home directory. These files are defined here in the scale directory. So that's the purpose of this directory. If there is a file that you want to make sure that a user will have access to whenever a new user is created, you have to place a file in this directory. So let's briefly make a test here. I am going to create a file with the content hello world in the /etc/scale directory. I'm going to call it intro.txt. Oh, so let me move to that directory. Let me edit a file here. I am going to use vim. And we will, in our next module, we will go through the command line text editor. It's not important for now. Okay, so I created in this / directory, I created this file called intro.txt. Now I am going to add a new user, 3. The password, if you want to inform that, okay. ID new user 3. The user has been created. Let's check if that user has its home directory. Yes, there it is. And let me list the content of this new user's home directory. Oh, if I actually list, let me clear the screen here. If I list using the -A option, we can see that all the files that exist in the /etc/scale directory were copied to this directory, the user's home directory as well. Now, observe here that we also have, by default, we also have these other files here, .bash logout, .bash rc, and .profile. These are command line environment files. They define some environment configuration. For example, how your command line interface will look like. As you can see here, whenever, first of all, my my command line environment is being colored. When I run, let's say, ls, directories are identified in blue. Some other types of files will be listed according, they will have a color according to their file type. All this configuration has been defined in one of these files. The same thing goes for environment variables. So if I have these environment variables here that I can access, I can see using the env command. If I have these variables here, that is because either these environment variables were defined in this /etc/profile file. So that's one file. Or in the bash.bashrc file. These two files, /etc/profile and /etc/bash.bashrc file, they are stored in the /etc directory, which means that the configuration, or for example, the environment variables that are defined in here will be applied to all users, admin or regular users. But if I want to define, for example, environment variables to a specific user, then I have the files, specific files for that specific user, which is stored in its own home directory. What I mean is, if we go to my home directory, I'm the Linux user and I have these files here. If I edit my .bashrc file and I add a new environment variable there, so let me edit this file here. We can see that we have some environment variables being defined here. For example, hist size, hist file size, and I have some other stuff here. Basically, you can just enter any command, any Linux command in here, and what's going to happen is when this user, this specific user logs in, all these commands that are stored, defined here, will be executed. And that is specific to my user because it's the file that is stored in my home directory. If I edit this /home/linux/passwd, new user3.bashrc file. So if I edit the home new user3.bashrc file, if I edit this file, whatever I put in there, it will only be applied to the new user3. And it will be executed every time that this user logs in. So we saw here that a bunch of stuff have to happen when we log in with a user. We saw how to create a user, how to change users' configuration, how to define users' groups, how to create groups. We also saw the difference between types of users, system user, admin user, and regular user. We saw what happens when a user logs in. So we discussed how to define new commands, environment variables according to a specific user. We saw how to define files that are supposed to be created in a new user's home directory. In general, we saw all the tools that we have available, or at least the most important tools that we have available when managing user accounts and group accounts. I hope you enjoyed this class, and now you have to work on your lab exercises. Thank you very much. Hello, welcome to our Module 4, and here we're going to study how to define permissions and how to work with permissions. And this is one type of security, file system security, that we can implement while working in a Linux environment. So first of all, we have to remember the difference between the super user and the regular user and system users. In a Linux environment, you can define permissions to some specific users. But the difference is you're not going to define different permissions to different users. You're going to define different permissions to different entities or different types of users. So let's take a look. Let me run ls with the -l option here, and then we can go from there. Let me create an empty file here using the touch command that we've seen before. So the touch command will create an empty file. So let me create a file here. Touch file.txt. Now, let me do ls with the -l option. We can see here that a file has what is called a inode structure associated with it, or simply an inode. Every file has an inode. The inode is a structure that will store information about a file. Now, what are those information that we can see in a inode structure? Here we have all the information that we have there. The first bit, moving from the left to the right, the first bit, which here is represented by the letter D, defines the file type. We will have another class where we're going to learn the different types of files. But for now, we just need to understand these two file types. D, which stands for directory, and that's why we see here desktop in blue. That's how the graphical environment will identify directories. So this is a directory. This is also a directory. We can see the letter D there, letter D, letter D. Well, actually, we only have directories except for this file here, file.txt. Now, what is the file type? There's just a dash. That dash defines that this is a regular file, what we usually name file. Once again, we have to keep in mind that in every Linux environment, anything is a file. It doesn't matter whether it's a network connection, it's a pipe, which is a channel establishing a communication between two tools, not using the network, whether it's a device such as a mouse, as your monitor, a network interface, it doesn't matter. Anything in a Linux environment is a file. So this first bit here identifies the file type. Okay, so we have directory, and we can see another file type here, which is a regular file. Then we have these 9 bits right here. And these are the permission bits. I am going to move forward, and then I'll go back to the permission bits. Then we have a number of direct links associated with that file. This is also a file type, which is called link. So we're not going to get attached to it right now. We're going to have a class for that. Then we have the owner of that file. In this case, the owner of all these files here, or directories, is the Linux user. Then we have the group that owns that file, or the owner group. The owner group is also Linux. And this is a default. By default, whenever you create a file, that file will belong to the user that created that file, and the group owner will be the primary group of that user that created that file. So here, if I'm using the Linux user and the primary group of the Linux user is also the group Linux, therefore Linux is going to be the user, the owner, and the group called Linux is going to be the group owner. Then we have the file size, which is here represented in bytes, and we can change that, but that's the default. Then we have the last time this file has been changed, modified. And finally, we have the file name. So this is what we have in a inode structure. Now, regarding permissions, the bits that are important to us are these ones, except for the number 2 here in the middle, because that's the number of direct links, which is not important. But the other bits there, or the other information, is what matters to us at this moment. Okay, now, why does the file type matters to us? Well, specifically when it's a directory and a regular file, it does matter, because the permissions, which are read, write, and execution, they can perform differently according to the file type. So if it's a regular file, these permissions can mean something. If it is a directory, they can represent a different thing. Not completely different, but there may be a few differences, which we're going to talk about. Okay, now, I have the file type, I have the owner and the group owner. And I also have the permissions. These permissions here are divided in 3 different blocks or 3 different entities. We can observe that we have 9 bits, 3 plus 3 plus 3. The first 3 bits corresponds to the owner. The second block of bits correspond to the group. And the third block of bits correspond to others. So we do have 3 entities. We have the owner, we have the group, and we have others. If a user is not the owner, if a user does not belong to the group, and therefore it belongs to others, it fits as others. So here we can see RWX for the owner. That means that the owner can do anything on this directory. Can read, can write or change, and can execute. The group or the users that belong to that group can read and can execute, but they cannot write. And others as well, they can read and execute. They cannot write. Observe here that when we create a file, a regular file, it's a bit different. When we create a directory, the directory will have, by default, it will have these permissions: read, write, and execute for the owner, read and execute for the group, and read and execute for others. When you create a regular file, we'll have read and write, no execution for the owner, read only for the group, and read only for others. That actually shows us one difference when it comes between a directory and a file when it comes regarding these permissions. So to understand that, we have to understand what these permissions do when we're talking about a file and when we're talking about a directory. First of all, let's observe the file. A regular file, it's easier to understand. In a regular file, when I have a read permission, that means that I can read that file. I can open it, or I can capture the the content of it. I can display the content. If I have W permission, if I have write permission, that means that I can modify that file. I can change the content. Now, pay attention. It does not mean that I can see the content, which may be a little bit confusing, but yes, that's how it is. Let's say that I did not have read permission, only write permission. That would mean that I could change the content of that file, but I would not be able to read the content. So in this case, I would need read and write. And execution, permission to execute that file. Differently from a Windows system, a executable file is a file that has the execute permission. And you can see here that directories have the execute permission, the X permission, whereas the regular file doesn't. Why does that matter? Because in a directory, in order to access that directory, in order to open that directory, I have to have permission of execution. I have to have the X permission. Sometimes it may look like, oh, but you should need read permission in order to open a directory. Well, but not really. The read permission in a directory will allow me to see the content, meaning I can list that directory. It doesn't mean that I can go in there. Let's say that I create a directory here, test dir. Let's take a look at the permissions that I have there. Oops. Okay, there it is. Read, write, execute. Read, execute. Read, execute. Now, let me remove, and I'm going forward and showing you the command that you can use in order to define permissions. Let me go forward and remove the permission of execution to the test dir directory. Okay, let's double check. Oh, nice. It is a directory, but there is no permission to execute, which means that I cannot open. Okay, but let me clear the screen here. Let's see the content of that directory. Nice, I can see the content. I can list it. Can I enter that directory? No, I can't. So as you can see here, since I don't have the permission of execution, I cannot enter the directory. If I place that permission back again, there it is. I'm there. Now, another very important detail when it comes to permissions in directories is that it is actually the permission that you set in a directory that will define whether a user can remove files from that directory or not. Or if a user can create a file in that directory, which is pretty obvious regarding the creation of files. Well, you need the permission to write in a directory in order to create files in that directory. Okay, nice. But people usually make some confusion here when it comes to removing a file. So I have this directory here. I forgot the -L option. So here I'm listing with the -L option to show the inode structure, the inode information. Since I am going to specify a directory, I have to use the D option, the D switch, to tell the system that I am not trying to list the content of that directory. I want to see the inode structure of that directory itself. Okay, so now let's create a file in this directory. It's an empty directory, and I am going to create a regular file here, test.txt. Well, if I list the files and their permissions with the -L option along with the ls command, I can see that, oh, okay, so the owner has write permission, which makes me think that is why I will be able to remove that file. Okay, so let me try to remove that file. Yes, I can. And I may think, I can remove it because I had write permission over that file. Well, if that was true, let me create that file back again. There it is. Now, let me remove the write permission that I have in the test directory. The permission that I have in the file, over the file, is just the same. I still have write permission. However, I do not have write permission in the directory anymore. Let me try to remove that file once again. Nope, can't do it. And the reason is actually pretty simple. We simply have to remember the concept of a directory. A directory is nothing more than a list. That is the actual concept, definition of a directory. It's a list. In this case, when it comes to file system, a directory is a list of files. It addresses files. It organizes files. Since it's a list of files, I have to have permission over a directory in order to remove that file from that list. So there you go. Now, how do we set permissions? Let's now do a thorough understanding, go through a thorough understanding of the chmod command. The chmod command, which stands for change mode, you can define the permissions that the file is going to have or that the entities will have over that file. So let's take a look at these permissions once again. And I mentioned that these are bits. They are bits where the bit on the right is, so it's a bit, so base 2 powered by, that's the first position, the first bit powered by 0. This is 2 powered by 1. This is 2 powered by 2. Which means that the value here in decimals, 2 powered by 0 corresponds to 1. 2 powered by 2 powered by 1 corresponds to 2. And 2 powered by 2 is 4. Those are the decimal values that we can assign to those specific permissions. Meaning, if I want to define read permission, I use number 4. If I want to define write permission, I use number 2. If I want to define permission of execution, I use 1. So these are the values that we can use in what is called the octal permission definition. But how do we build this? Considering that we have 3 entities, we have the owner, the group, and the others. You have to sum up, add up the permissions that you want to assign to each entity and use that number, that decimal number, for each of the entities that you have. Meaning, let's say that I want to give read, write, and execution to the owner. So that's going to be 4 plus 2 plus 1, that's 7. To the group, I want read and execution, no write, so that's 4 plus 1, that's 5. And I don't want others to be able to do anything, so that's 0. There it is. Okay, it worked. And we can actually see here that it's now represented in green. That is because I am giving permission of execution to that file. I just made this file a executable file. And that's what it is. A file to become executable just needs the permission of execution. It is another story whether it is going to execute something, it is going to perform something. That's another story. But that's what a executable file is in a Linux environment. And you can combine these values according to the permissions that you want. Now, the problem of using this is that I have to know all the permissions that I want to define. And what I mean by that is, in this case, I knew that I wanted to give read, write, and execution to the owner, read and execution to the group, and nothing to the others. But what if it doesn't matter the permissions, the overall permission? I just want to add something else or remove a permission. For example, if I didn't know or I don't care about the permissions that the owner have, whether the owner has read and write or just write, what I do know is that when I saw that this is green and this is a executable file, I don't want it to be. I just want to remove the permission of execution. So I use the textual permission setting. So how do I do it? I define the entity, in this case, user. For the user, I want to remove, so a minus sign, execution. And there it is. But wait, the group still has execution. Well, what I could do is this. You use the letters where U stands for user, G stands for group, and O stands for others. And then you use the sign, which can be equal, minus, or plus. If you want to define specifically those permissions, you use equal. If you want to remove, minus. If you want to add the permission, plus. You also have the possibility of using entity A, which stands for all. So A or UGO is the same. Now, we saw how to work on these bits here. What about the owner and group? What if I want to change those? Then you're not going to use the chmod command. You're going to use the chown, which stands for change owner or change ownership. Simply, you're going to use chown, the owner, dot or column. It's up to you, it doesn't matter. I'd rather use dot, and the group and the file name, like that. So let's say that I want to change this file ownership here. However, since I'm a regular user, I won't be able to say, okay, this file that belongs to me is not going to belong to myself anymore. I want to give it to someone else. For security reasons, that is not allowed. You're not allowed to do that. Only the admin user can do that. Well, the reason is pretty obvious. I could create for example, a Trojan horse, a rootkit, a virus, whatever that is, a malicious software, and I could change the ownership. I could say, okay, this file here now belongs to, for example, belongs to the root user, which could cause a mess in my system. So you have to be the root user, the admin user. Depending on the system, you're going to use sudo along with the chown command, or you can do su and become the root user, and then you start using the chown command. Okay, I want to say now that this file is going to belong to the new user, and to new group. I need my user password. There it is. Let's take a look at there. So changed. Owner, new user. Group, new group. There is just one problem. Test.dir directory belongs to my user, and the test file that is in the test.dir directory belongs to other user in other group. Let's say that I want to redefine the ownership of this directory, but I want that ownership to be applied to the files that reside within that directory. So I want to say that new user 3 and root, the root group, are going to be the owner of all that. Okay, let's take a look at it. Oh, so I changed the ownership of the test directory, test.dir directory. But what about the content? Nope, it didn't. Therefore, I have a switch here, which is the dash capital R, that will do the work. There. It's changed now. The dash R option performs this, and it's also available for the chmod command. The difference is for chown, it's a capital dash R. chmod, it's a lowercase r. Now, what it does is it will perform the ownership or permissions setup not only to the directory, but all the files that reside in that directory. If there are subdirectories, we have to remember that directories are files. So the same thing will be applied to those subdirectories and the files that reside within those subdirectories. It's recursive. Right? Okay, good. Now, let me clear the screen here. We do have some other different types of permission setup. Let's take a look at the /bin/ping file. So we can see here that, first of all, the appearance of that file, the file appearance, it's in red or a red background and a red highlight with letters, characters in white. What is doing that? Okay, so I have execution, I have read, I have execution, I have read, I have... Oh, wait, what's that? That's S. It stands for switch. It's this switch, in this case, switch user ID. It changes the ID, the identification of the owner of that file. Observe that this file here belongs to the root user. I am a regular user, in this case, the Linux user. A regular user does not have permission to run a ping command, because a ping command will open a socket. Regular users cannot open a socket. This file must be executed by someone else that actually has that permission. In this case, it's the root user. So when I set the switch user ID bit to that file, I'm saying that whomever is invoking this file, it will actually be executed when the kernel receives that request. It will be executed by the root user, not by, in this case, my Linux user. Proof of that is let me remove the SUID permission. There, removed it. Let me try to ping it now. Ping.google.com. Operation not permitted. Ping socket. I'm trying to open a socket. I can't. Okay, let me bring that permission back on. And I'm going to, there you go. The ping command is running. So that is the reason why you'd use or you have the SUID. Similarly, we also have the SGID, which is the switch group ID. Now, the reason why you'd use the switch group ID is a little bit different. Let's see when that happens. Observe here that the testdir directory belongs to new user 3, that's the user, and root as the group. I'm going to create a file in the testdir called sgid.txt. Oh, I can create it because I don't have permission. Yeah, so let me change the owner. chown Linux testdir. Oh, and I need write permission, okay. There. So we have this new file here. Observe that the testdir directory belongs to, oh, I changed the ownership. So let me clear the screen here and list it again. So the testdir directory, it belongs to my user, Linux, but the group is root. When I created the sgid.txt file in there, well, the owner is Linux as well, but the group owner is Linux. There are situations where I want that to happen. The group that owns a directory is one, but I want to have files within that directory where the owner is the user that creates the file and the owner group is the primary group of that user. There are situations though, and it is the most common situation. There are situations though where I want the group that owns the files that are created within a directory to belong to the group that owns the directory. One situation, let's say that you have a development environment where your IT staff, your programmers, your coders, they're sharing a folder. They have a folder, they have a directory where they're supposed to save the projects and the project files in that folder. Imagine if all files that are created within that directory will belong to the user that created it and the group that owns, or the groups that own those files will be the user's primary group. You're going to have a file created by, let's say, dev1, where the group that owns that file is going to be dev1 as well. You're going to have another file created by user dev5, where the group that owns that file will be dev5 as well. So you're going to have different files belonging to different users and different groups, which is going to make it so much more complicated because it's supposed to be a shared folder. In this case, let's say that I want to create a group. Let's say dev. So I am going to create my dev group here. I am going to say that dev owns this directory. That's how you redefine ownership of a file, but using only one entity. Instead of defining the owner and group, I just define if I want to change the owner, I just do the owner account like that. If I want to change the group, I use dot and the group like that. Okay, so testdir belongs to Linux and group dev. If I want to force all files to belong also to the dev group, I have to add to the group the switch ID permission. There it is. Now, I am going to create another file there called dev.txt. There it is. The owner group is dev. It's not my primary group, which is Linux. So that is why you'd use the SGID switch. And another special permission that we have is the sticky bit. And actually, it already exists in the system, and we can use it as an example. If we list the permissions of the /tmp directory, we can see that permission right there. The sticky bit is right here. First of all, what is the /tmp directory? It's a directory that exists in the system to host or store temporary files. Files that are stored in the /tmp directory, they will either reside there for a defined period of time, or they will be removed whenever you reboot the system, whichever happens first. Now, observe that all users, all entities, owner, group, and others have the same permission, which is do anything. So all these entities can create files, remove files, execute files that are stored in that directory. But when you have a directory that is so open, such as this one, there is a problem. If any user can do anything in that directory, that means including deleting files. That means that user A can remove a file that belongs to user B, which should not occur, should not exist. It's okay. Users can do whatever they want. They can create as many files, they can change files, but they're not supposed to be allowed to remove other users' files. That's why we have the sticky bit, to prohibit users from deleting files that don't belong to them. So I am going to create in the /tmp directory a file called my user, linux.txt. There it is. I'm going to log in with the new user 5, I guess. I think it's password, or maybe not. New linux 3, password. Who am I? New user 3. If I go as new user 3 to the /tmp directory, there it is. I myself now as new user 3 can also create files here, new user3.txt. So here are those files. But can I remove the linux.txt file? I can't. Now observe, I am new user 3. And you may think, oh, you can't remove that file because on the linux.txt file, you fit in these permissions here, you don't have write permission. That's not true. That's not the reason. We have to remember that what allows or prohibits someone of removing a file that resides in a directory is the permission, the write permission on the directory. The sticky bit is there in order to avoid, because since this directory allows any user to do anything, that means that a user can remove other users' file, but the sticky bit won't allow it. That's why I wasn't able to do it here. Proof of that is I am going to remove the sticky bit permission from the slash. Oh, so let me go back to the Linux user. There. Now, let me log in as the new user 3 again. There. I was able to remove that file. What's changed? This changed. There is no sticky bit here anymore. So that is why it's important to know these special bits. Specifically, SUID, SGID sticky bit. Obviously, we saw some other commands that are very useful and important because you need those commands to change ownership and permissions. The chmod and chown commands. Those are the resources, those are the tools that you need in order to work with ownership and permissions. Now, it is the time that you're supposed to know how to work with a text editor software. You will find in our folder, you will have access to a cheat sheet for the VI editor, text editor. There are so many other text editors, such as Emacs, Pico, Nano, so many others, MCEdit, but VI is the editor that will be available wherever. It doesn't matter which distribution you're using. It doesn't matter how old it is, how recent it is. It will have the VI text editor. So we don't have to go through VI, but you do have to learn how to use it. Therefore, you're going to have access to that cheat sheet. I hope you enjoyed this class. Thank you very much. Hello, welcome to Module 5. And in this module, we're going to discuss storage and partitioning, specifically talking about the Linux environment system. So the first thing that we have to keep in mind when we talk about partitioning and the storage is that you have several different types of storage devices. We have the most traditional one, the one that always come to our minds when we think about storage, which is the hard drive, but we have so many other different types of devices. So we have flash drives, we have floppy disks, although they're not common anymore. They haven't been around for a while. People haven't used that for a while, but still it is possible to use it, and it is a storage device. We have nowadays what is very common, storage in the cloud. We even have shared folders in the network, which is seen by the Linux system as a storage device. So a storage device is simply a location where you can store files, which means that let's say that you have a Dropbox profile, you have your Dropbox space. You're going to store files in that Dropbox folder or profile. It will be seen by the Linux system as a storage device. It makes no difference, the system makes no difference between the traditional storage device such as a hard drive and other types of storage locations. As long as you can store files in that location, it is seen by the Linux operating system as a storage device. Now, that being said, we have to understand how these storage devices are accessed by the system. So, whenever you have a device that can be accessed by the Linux system, that device will be represented as a file within the /dev directory. So, every hardware, every piece of hardware is represented by a file or addressed by a file that resides in this directory /dev. It's not different for storage devices. Now the difference is, according to the storage device that you have, you can have different ways of addressing that storage device. We do have some different types, but mainly two different types must be understood here, which are SD and HD. Nowadays, it is not very common to see HD devices. Basically, you're going to see SD. But still, if you ever face that, you know what it is, and you have to know it because it may be in your exam. So basically, you're going to see two different types of storage devices, SD and HD. When we had the traditional IDE controllers, those IDE controllers were represented by HD. SCSI and SATA devices are seen as SD. That's why it is so common to see SD devices nowadays. So SATA, PATA, SCSI, they're all represented by SD files in the /dev directory. And then you have a ladder that will represent that specific device according to where it's connected or how it's being controlled by the controller. What that means is, so let's say that you have a old IDE controller. And if you go back, if you had the chance to work with IDE controllers, mostly at the time, the motherboards, they would give you two IDE controllers. So two cables, and each cable being connected to the motherboard. Each cable could be connected to two other devices, storage devices. So if you have two IDE cables, two IDE controllers, in each IDE controller you could plug two hard drives. That means that you could have 4 hard drives. Obviously, there were different situations. You could have more than that, but that was the common scenario. Now, the first hard drive, or the hard drive that would be connected to the first connector in the first controller, that would be a HDA. So that would be represented by HDA. If you have a hard drive still in the first controller, but in the second connector of that same first controller, that would be the HDB. So forth, so on. So the third hard drive that would be connected to the first connector of the second controller, that would be HDC, and then HD, so forth, so on. That does not necessarily mean that the if you have a, let's say, if you have a hard drive plugged in the second connector of the second controller, or the secondary or slave controller, that would be HDD. It could very well be the HDA. So that sequence would be according to the number of hard drives that you'd have connected there. Same idea for SD devices. Now, then you have a number that identifies the partition. Now, the partition itself, or the partition number, that would be or could be determined by the sequence of creation, no matter what other partitions you'd have. So this means that if I have a, let's say, a partition called SDA8, is that going to be the 8th partition? No, not necessarily. If I have HDB3, oh, does that mean that's the 3rd partition? No, it doesn't mean that. So in order for us to understand how the partitioning numbers work, we first have to understand, at least briefly, how the MBR and the GPT controllers or systems work. So first of all, it is still being used, although not that common anymore. But we have basically two different master boot record or systems, boot systems available. We have the MBR, master boot record. We have the GUID partition table. The MBR is deprecated now because of this reason here that you can see right here. Each partition is limited to 2 terabytes, and this would depend on the operating system. But in general, the number of partitions that you'd have available would range from 16 to 64 partitions. Now, this may vary because it depends on the motherboard and the system, the controlling system that the motherboard uses. So if your motherboard uses BIOS, BIOS, then probably you're talking about a master boot record as the booting system. If you have a UEFI controller in your motherboard, then probably you're going to have the GPT booting system. And the GPT booting system was created because of the limitations introduced by MBR. So now we still have a limitation, but it's going to take a while to achieve that limitation, which is each partition is limited to 18 ebytes and 128 partitions. Each partition being limited to that maximum size. So, since the master boot record, the MBR was limited to this size, this partition size of 2 terabytes, but it was also limited to 4 partitions. This means that you could only have, let's say, HDA1, HDA2, HDA3, HDA4. In order to, which is a ridiculous limitation, right? So in order to solve this problem, what was done was you have the possibility of out of one of those 4 partitions, you could define one as a extended partition. Now you can have, for example, 3 primary partitions, and then your last partition, you could name it as extended. And the extended partition could then be divided in several different logical partitions. Counting those 3 primary partitions plus the maximum number of logical partitions, you could have up to 16 or 64 partitions. And that is a problem that you don't have in the GPT system. Now, when you look at that, it may seem very obvious to assume that the GPT booting system or a partitioning system is a lot better than the MBR. And yes, it is. But you have to consider that there is a possibility of incompatibility with your system, with your hardware. So the GPT system is only compatible if your motherboard, your hardware has a motherboard that uses the UEFI controlling system. If you have an old machine, then you'd have to use MBR. Okay, so that's how the partitions are defined in a Linux environment. So we have to keep in mind that you're going to have in the /dev directory files that will identify your devices and your partitions. Now, once you identify the file that represents your storage device, you have to know how to define a format or how to format that file system. For example, in a Windows solution, you have FAT. Back in the day, you had FAT16, then it evolved to FAT32, then it evolved to NTFS. So you have different types of file systems. In a Linux environment, it's not different. Basically, it's the same. The difference is the file systems that you have available. And the first major one was the extended 2, the EXT2. The problem about this file system is that it doesn't support journaling. So it doesn't support the journaling system. And journaling is a very important system because it is what allows the Linux system to recover files when something bad happens. So let's say that due to a power outage, the machine was turned off abruptly. When you turn that machine back on, important files were corrupted. Files that you need to be able to boot your system back on. Well, if your file system or your files are stored in a file system, in a partition that uses ext2, the probability of recovering those files is very low. Why? Because ext2 does not write information from time to time about the files that are stored in that file system. And that's what the journaling system does. The operating system will every now and then check the files and generate a report or journal about those files. If the machine is powered off for some reason, when booting back on, the Linux operating system will compare the files that exist with the information that was reported in that journal. And then it will make it a lot easier to recover those files. Well, observing that problem, the Linux maintainers, they evolved and they implemented journaling system to the X2. So then we evolved to the X3 and following to X4. All these X3 and X4 are just an improvement of the X2 file system. Obviously, there are other file systems developed by other companies or people or institutions. For example, some very famous ones: XFS, JFS, RazorFS, and ButterFS. All of these support journaling. The only one that does not support journaling is X2. Each of them has their advantages and disadvantages. Another file system type that we have is the swap, which is also present in a Windows system, but it's not well known because the way the Windows operating system works, it doesn't ask you information or it doesn't give you information about the virtual RAM memory. However, when you're managing Linux systems, you are supposed to know how the swap partition works, and we're going to work on that. And this is just a comparison among some different types of file systems that we can find in a Linux operating system. So it's a comparison regarding throughput. So you can see here a comparison between the ButterFS, X2, X3, X4, RazorFS, and XFS, where we can see that, at least according to this research here, the ButterFS performed better, at least when you use a higher number of blocks. And another solution that we have available is the Logical Volume Manager, or LVM. The LVM is actually a very nice, very interesting solution. Basically, what it allows you to do is to logically manage, resize, redimension your partitions. Now, this is a solution that is implemented by software. That means that you're gonna lose performance. So the throughput for both read and write operations will degrade. But still, it will give you the possibility of, on the fly, with the system running, you'll be able to redimension, resize your partitions. You can even add a new hard drive to your system on the fly. You can even remove a hard drive that is being used. You can add new partitions. You can remove partitions. Now, the difference between this solution and the not using LVM is that if you're not using LVM, you only be able to, for example, remove a hard drive from a system if you're capable of, if you're not using the files that are stored in that partition or in that hard drive. It's different from the LVM. You can have a system running using those files, and you can still do all that. Now, how does it work? Let's take a look at this image right here. First of all, we have to understand some names or some nomenclatures. First of all, what we have to observe here is when you see PV, which stands for physical volume, that represents a physical hard drive. Okay? So in this solution, what we can see is, let's assume that we have 3 hard drives. So we have PV HDisk 1, PV HDisk 2, PV HDisk 3. Now, these hard drives, or so-called in the LVM language, physical volumes, they can have different partitions, or physical partitions, PP. So for example, each of these hard drives here, they have several physical partitions, or what we call as partitions, what we know as partitions. They have several partitions of 32 megabytes. Okay, now, here comes some concepts involving LVM. First of all, we have the concept of a volume group. A volume group is a group of physical volumes or hard drives, which you can very well have a volume group that encapsulates just one single physical volume, just one physical hard drive. But you can also create a volume group, as we can see here, composed of 3 hard drives. Now, in the LVM world, a volume group represents what we understand as a hard drive. So what you can see here is you have a logical volume group or a logical hard drive that is actually composed of 3 different hard drives, but it's going to be seen by your system as one single hard drive. And then you can split that hard drive into, or that volume group into partitions. In the LVM world, a logical partition is called LV, logical volume. These are the partitions. And then you can say, okay, so this partition here will be formatted. We'll have this file system. In this case, we're using, in this representation, JFS for this file system, X3 for this file system, JFS2 for this other file system, this other partition. Okay, so we have 3 different partitions with 3 different file systems. Now, you can observe here that each partition or logical volume is associated not with one single physical partition, but with more than one physical partition. And even more interesting is that you can associate that logical partition with different partitions from different hard drives. So as we can see here, we have /dev/HLV associated with this partition here, this partition here, this partition here, and this partition here, which belong to the same hard drive, but also including this other partition that belongs to that other hard drive. So when you implement this, you can see here how flexible this is. But also, let's say that you suspect that there is an error, that this third hard disk here is about to die, it's about to crash. Well, you have a partition here, /dev/data, that is using 2 partitions that belong to that physical volume or to that hard drive. And you want to replace this hard drive. What can you do? You can insert a new hard drive, you can plug in a new hard drive, move all the data from here to that other hard drive. Meaning you can include that new hard drive into this volume group. Then you migrate this data to that new volume group, and then you remove this physical volume right here. So it is a very interesting solution. So we saw here how to understand and how to address storage and partitioning in a Linux environment system. We saw how the partitioning works in this system. We saw the different types of file systems, and we also discussed about LVM. Now, in our second class, or in our next video, we're going to see the tools that we have available in order to deploy all that. Thank you very much. Hello, welcome to our second class of our Module 5. And here we're going to see some tools, some commands that we can use in order to manage storage. But before we actually start working on our system, we have to make sure that we have our storage location, our storage device where we can work on. So what you need to do is make sure that first you have your virtual machine stopped. So your Ubuntu system cannot be running, okay? I already have mine running here, but that's because I've already created a new device, a new storage device. But you have to do that first. So first thing that you have to do is stop your virtual machine in case it's running, okay? Because in order to add our second storage device, the virtual machine cannot be running. Once your machine is not running, you simply come here to your VirtualBox, and I'm assuming that you're using VirtualBox. You click on your virtual machine name, go to Settings, and then you move here to the Storage tab, okay? So in your system, in your virtual machine, you see only one hard drive, which in my case, I named it Ubuntu, just as the machine name. So probably just see one here under controller SATA, in my case, ubuntu.vdi. And then you're gonna see here a button where you can add a new storage device. If your system is not running, it's either gonna show here, it's actually this one, or here down below, okay? I use this one, and then I added a new hard drive. You just have to inform the name and the size. So I created, and I'll ask you to do the same, I created a virtual disk of 1 gig, okay? Once that's been created, you can hit OK, come here and start your virtual machine. It's going to start the virtual machine, and then you can start working from there. Now, what are we going to do here? First, we have to remember how the Linux system identifies storage devices, right? And mostly, as I mentioned in our first video, there are other types of files. There are other files names that can be used, but most of the times, the files that represent storage devices, they will be named SD or HD. Most likely SD. So if we come here and do ls/dev, and that's in the /dev directory, /dev/sd asterisk. Okay, so I can see that I actually have two devices. I have /dev/sda and /dev/sdb. Probably this is my second device, the hard drive that I just created. The /dev/sda1 is the partition that I have in my first hard drive, in my ubuntu.vdi hard drive. And this is my new disk.vdi file or storage device. Okay, now, what are the tools that I have available in order to manage these storage devices? The first tool that we have to look into is, and now we are going to perform administrative tasks, which means that we have to be a root user, we have to be an administrator user in order to perform those tasks. So, okay, the first tool, which means that I have to use sudo, or if it's another distribution that you have access as a root user, you have to use su to become the administrator, and you don't have to use sudo anymore. But here we have a Ubuntu distribution, so sudo. The first command we're looking into is fdisk, okay? So the fdisk is the tool that you use to see the devices, the storage devices that you have, and also to manage those storage devices. Manage in which way? You can use fdisk to partition or to define a partition table or redefine a partition table. So if you need to create a new partition, if you need to remove a partition, you're going to use the fdisk tool to do such. Obviously, there are other tools that will allow you to do that, such as gparted, cfdisk. There are so many others. But it is very important to use fdisk, to know how to use fdisk, because this is the one tool that you be 100% positive that it will be there no matter which distribution you're using. So if we do fdisk space -l, it is going to show a bunch of stuff. So, okay, my user password. There. You don't have to worry about those bunch of /devs that /loop whatever files. Okay? And maybe it will depend on the distribution you're using, the version that you're using. This is just one way of addressing image files. So it has nothing to do with what we're studying here. What matters to us are the /dev/sd files, which are, so we can either just scroll down and here we can see our SDA file. So that's my main hard drive. That's where my system is installed. It has 10 gig, right? Each block has 512 bytes. So not the blocks, the sectors. And you have some other information here and how this device is partitioned. So I only have one partition here, which is the /dev/sda. It's a bootable partition. Well, if that's where my system is installed, the only partition where my system is installed, it is a bootable partition, where it starts, where it ends in regards to sectors in my disk. The size in sectors, the size in bytes, in this case 10 gig. ID identifies the file system. So it's a 83 file system type, which is a Linux type, as it says right here. Now, observe that 83 does not identify whether it's X2, X3, X4, Razer. No, it only identifies the system, the compatibility, the system compatibility. So it is a file system that is going to be compatible with a Linux operating system. Then we scroll down and there it is, our second disk. 1 gig, as I defined, the size, right? And we can see that it doesn't show any partition table. So it's not partitioned. It hasn't been partitioned. And this is exactly what we're going to do. So our goal here is to see how to use fdisk and some other tools to manage a storage system in order to partition and be able to store data in that device. Okay, so I can see those devices there, but I want to partition or actually create a partition table in my /dev/sdb device. What do I do? Oops, I forgot. So sudo fdisk/dev/sdb. So you have to inform the disk where you're going to work. Okay, there it is. Now you can see that it has a interactive menu. So M for help, and it's going to give you some options here, right? And the option that we're looking for is letter N, because we want to add a new partition. If you want to delete, you have letter D. So you have all these options here. Okay, so I want to add a new partition. Okay, now, what type of partition is that going to be? Is it going to be a primary partition or is it going to be an extended partition? After you create an extended partition, then you'd be able to create logical partitions. Just to remember you, when do we create extended and logical partitions? We have to keep in mind that, and it says right here, for are free. Since we're considering a system that works with the MBR bootable subsystem. It allows us to create 4 primary partitions. If we need more than 4 partitions, then we have to create one of those 4. At least one of those 4 must be an extended partition, and then we can split the extended partition into many logical partitions. Well, this is not going to be the case. We are just going to create 2 partitions here. One is going to be a traditional Linux partition, and the other, which is we'll define it as X4, and the other one is going to be a swap partition. Okay, so it's going to be primary. What is the partition number? You can pick between among 1 to 4. So this is going to be my first partition, the first sector, the default, and I usually just use the default. This is just a case where you don't want that partition to start at the next available sector. Let's say that you want to leave in space between one partition and another partition, which in my opinion is not very helpful, but you do have that option. There's a bunch of studies where they do this analysis. Does a server perform better when you have that gap between different partitions? Some studies says yes, some studies say no, some studies say, well, that depends. So anyway, I'll just leave it as the default. The very first available sector is where I want my partition to start. So I just hit enter, which is the default. Okay, now, what is the size? You can define it. You can determine the last sector. You can determine how many sectors, considering that it's starting from what you define as your first sector, or you can define in size, and that's what I like to do. So I want this partition to have plus 500 gig, and you have an example right here. Okay. That's not gig, it's meg plus 500 meg. There it is. Okay, there. If I want to see my current partition table, I use P to print. Okay, so now my SDB device has 1 partition, but I still have space available. I am going to use that space available to create a swap partition. So N, I have a new one, it's primary, number 2, it's going to, what is the first sector? The very first one that is available. I just hit enter. And what is the last sector or the size? Well, if you wanted to go all the way to the very last sector, which means use the entire space that is available for that partition, you can simply hit enter. If we observe here, this is the range of sectors. The very last sector is this one, right? And the default is that. So if I simply hit enter, it's gonna use the remaining space. So let's print the partitioning table that we have. Oh, okay, so SDB1 of 500 meg, SDB2 of 523 meg. But there is still something that we have to change here. Observe that this partition SDB2, its ID or its type is still Linux. We have to change it. It's not supposed to be Linux. It's supposed to be swap partition. I can use letter T there to define the type. Partition number, which one do I want to change? It's my second partition, number 2. Okay, what is the hex code for the partition? The partition ID is in hexadecimal. It's not in decimal. If you don't remember or you don't know, you have the capital L option. There it is. The one that we're looking for is 8.2, Linux swap. Okay, so 8.2. Let's see if it worked. Let's print. There it is. Now I have those 2 partitions, SDB1 as Linux and SDB2 as Linux swap. Okay, is it done? Yes, it's done. The partitioning is done. We still have a few stuff to do, such as format and mount, but at least in regards to partitioning, it's all done. But we have to save those changes. That's why we have to do write. There it is. The partition table has been altered. How can we confirm that? fdisk-l. But again, if we, and I'm going to clear the screen here, if we do fdisk-l, it's going to show a bunch of stuff. I only want to see the partition tables, the partitions for table SDB. There it is. Okay, so it's been applied. Now this disk has been partitioned, but it's still not accessible. In order to access a partition, we have to mount that partition. And mounting a partition is associating what is called a mount point with a device or a partition. The mount point is similar to a drive in a Windows environment. So in Windows, we have, for example, the C drive, D drive, E drive, F drive, whatever that is. Each drive corresponds to a specific partition. In the Linux world, it's not a drive, it's a mount point. So, for example, if I want to associate /dev/sdb1 with the /mnt directory, that's what I have to do. However, there's still a problem. I haven't defined a file system to that partition. So we have to define whether it's ext2, ext3, 4, Razor, XFS, JFS, whatever that is, even NTFS in case it's a Windows compatible file system or partition. And how do we do that? We use the MKFS tool. And it's pretty straightforward. MKFS, or make file system, -t to identify the specific file system. And we're going to format the /dev/sdb1 as ext4. There it is, done. How can we be sure whether it really worked or not? Okay, so I'm going to clear the screen here and try to mount it once again. Well, it did not return any error. Probably that means that it actually worked. But how can I be sure? You can use the mount command itself with no parameters. The mount command is not only used to mount a partition on a mount point, but it's also used to display the mount points that you have. And you're going to see a bunch of stuff here. But what is important for us is the /dev/sd devices. /dev/sda1, that's where our system is installed. You must remember that the slash directory is the same as the C drive in Windows. So there it is. Oh, I can see here that my system, which is in the mount point is / is a ext4, and it's a mount point to the SDA1 partition. Okay, so that's where my system is. If we scroll down, we can see that the /dev/sdb1 now is mounted on /mnt, and it's also ext4. Now, one thing that you also have to keep in mind is that when you are mounting a device, you can use options with the -O switch. And you can use options such as R, RW, R stands for read, RW stands for read-write, which will allow a read-write permission. You can use user. So you can take a look at the main page for the mount command, and it will describe to you, it will tell you so many different options that you have available when you're mounting a device. Okay, so you can devise, for example, only these specific users, only regular users can access that partition. Only the regular users and the admin or root can access it. Or do you want to allow guest users to access that partition as well? Do you want to make that partition a executable partition, which means that executable files stored in that partition will actually be executable? So there's a bunch of options that you have available, as you can see right here. And there's a bunch of other options. But here we just used the default options, which will mount it as read-write with read-write permissions, meaning that now that it's mounted, we can actually create files in that partition. For example, I can do touch/mnt/test.txt. Oh, the problem is that it's not mounted to permit regular users, but I can use sudo here, there, /mnt/test.txt. Okay, what happens if I mount that partition or that mount point? Well, the files will still reside in that partition. They're not just accessible anymore. What I mean by that is another tool. Okay, so before I show it, another tool that we have available is df. And let me use the -h switch that will show the unit, the most friendly unit. If it's in K, it will show in K. If it's in mag, it will show in mag. Okay, so we can see here that the /dev/sdb1 is mounted on /mnt. We can see the total size, which is about 500 meg. How much is in use? 2.3 meg available, 445 meg. That represents 1% usage, which is not even that, but it's rounding up. Now, so again, if I access the /mnt directory, I'm actually accessing that partition. But I can mount that partition. And if I do a df, or you can also use the mount command itself, it's not there anymore. What does that mean? It means that if now I list the content of the /mnt directory, the mount point is still there. The directory that is used as a mount point is still there. However, it is not addressing that file or those files anymore because it's not mounted. The partition is not mounted anymore. It's not accessible via that directory or mount point. Okay. Now that this partition is U-mounted, so how did I U-mount a partition? Instead of using the mount command, I use U-mount. And you can simply use U-mount space the mount point. Now, when a partition is not mounted, so it cannot be available. It cannot, well, it can be available for read-only, with read-only permission, not read-write. When a partition is not writable, you can run checks. You can check for errors, for example, bad blocks. To do that, you have to use the FSCK tool. And similarly to the MKFS tool, you have to use the -t option to determine the file system. There it is. So, okay, clean. It checked that partition. It's such a small partition that it just realized that there is no errors very quickly. The tool was able to check that partition. Now, I am going to mount once again there it is.
So I mounted there. I confirmed that it is mounted. It's right there. And we can use the df command to see how much is free, how much is used. But what about in case I want to see the size of the files or directories that reside inside a specific partition? For that, I have the du command. Oops. There it is. So the /mnt directory actually has 13K in data residing in it. If I want to see the size of the files that are in there, I can use the /*. Oh, okay, so I have an empty file, which is the file that I created using the touch command, test.txt, but there is also a lost and found directory, which requires 12K. Okay, good. Now, what about our other partition that we created to be a swap partition? But now, first of all, do we have a swap partition? And there is a command that we can use in order to verify that. First of all, what is a swap partition? A swap partition is a space of your hard drive that you want to leave it there to be used only when, and if it happens, only when you run out of RAM memory or temporary memory. So if your RAM memory if you run out of a RAM memory, then a piece of your hard drive, a partition, will be used as a RAM memory. Obviously, that's not the best scenario. You don't want, so hard drives, it doesn't matter whether it can even be a solid state hard drive. It's still slower than RAM memory. So you don't want to have that, but it's better to use a slower RAM than not having RAM memory at all. So that's the idea. Since this is a RAM memory, or at least a complementary RAM memory, you're not going to use the du or df command, but you're going to use the free command. And once again, you can use the -m to show information in meg. So the free command will show you how much memory, RAM, actual RAM memory you have, total, how much is used, how much is free, and also swap memory. Okay, so my swap memory is not being used. But let's say that you want to have more swap memory, or you either want or you have to. We created that partition, but it's not active. How can we activate that swap partition? First of all, similarly to regular file system where we have to format, we do have to format swap partitions as well. /dev/sdb2. There it is. Now, in a regular file system, we have to mount. Swap memory is not mounted. It is activated. You have to activate it. How can you activate it? Swap on /dev/sdb2. There it is. Now observe that my swap memory just doubled. It doesn't differentiate whether you have just one partition, two partitions, 5 partitions, 10 partitions, it doesn't matter. What matters is the total size. Now I just doubled my swap memory. Okay, good. So we saw how to manage file systems or storage file system and also swap memory. But there is still one thing that we have to be aware of. All this configuration here is temporary. Well, while your system is running, which means that if you reboot your system, you're going to lose this configuration. how can you define it in a sense that it will become available? Doesn't matter if it's running or if I restart my machine. For that, we have the /etc/fs tab file. And the way this file is used is, in the first column, it's the partition name. For example, /dev/sdb1. Now, if you observe here, the /dev/sda1, which is where the system is mounted, it's not identified by /dev/sda1. You have a UUID, which is perfectly fine. If you know your partition ID, you can use the partition ID. But that's not important for us right now because we do have the partition name. So partition name, the mount point /mnt, and let me follow the identification here according to, okay, so let's follow the columns. So mount point, I'm going to do it here, /mnt, type, this is ext4, options, let's do defaults, dump, it's going to be 0, and pass is going to be 0. Now, let's understand these columns here. Okay, that's the device or the partition, that's the mount point, that's the file system. Defaults, in this column, options, we're going to define the mounting options. As I mentioned previously, you have so many different options, whether you want it to be read-only, read-write, executable or not. So you define it there. Dump means, do you want this partition to be backed up after every boot? If you want to, you define it as 1. And then pass is whether you want to verify that partition. Okay, so there it is. I do the same for the other one, which is SDB2. There is no mount point because it's a swap partition. So I say none. The file system, swap. If it's swap, the mounting options is SW 0 and 0. I save this file, and obviously you can use any text editor that you want. I save it, and if I restart my system, those partitions will be available. So these are the tools that you have to be aware of. These are the tools that you have to know in order to manage storage devices and partitions in a Linux environment. Also, these are the tools that you have to know how to use for the exam, for the CompTIA Linux Plus exam. I hope you enjoyed this class, and see you in our next class, which is our lab class. We're gonna do exactly what we did here, but more like a challenge. You'll be presented to a scenario where you have to use most, if not all, of these commands. Thank you very much. Hello, welcome to our module 6, and our topic here is going to be what you can read: File System Hierarchy Standard, or FHS. So whenever you see these three letters acronym, this is what it stands for, at least if you are reading something about a Linux operating system. So FHS stands for File System Hierarchy Standard. And what is this standard? This is a standard that's been created to standardize or to create patterns regarding directories and the hierarchy of directories in the Linux operating system. So our focus here is going to be understand the main directories that we have in the Linux operating system. So understand the structure, the hierarchical structure of the main directories according to this standard. And what I mean by that is that we are not going to focus on understanding directories that are not covered by the file system hierarchy standard. For example, the /snap directory is not covered in the FHS, so we're not going to cover that. Okay, so why do we have the FHS? So the whole idea here is to understand where you should place or find files in the Linux operating system and in its file system hierarchical structure. For example, making an analogy, going to the Windows world, everything begins at the C drive. From the C drive, you're going to have some folders. For example, you can have documents and settings. You can have the Windows folder. You can have the System32 subfolder. You can have program files. So there are many folders in the C drive, so which is where the entire file system structure begins in that operating system. Some folders are optional. Some folders are there by default, but they do not follow the Windows standard. And some folders are there because they have to exist according to the operating system standard. It's the same thing here. So according to the Linux Foundation standard, that's the foundation that actually defined FHS, we have a structure of directories that must exist, and files are supposed to be stored within those directories according to their purpose. So first of all, similarly to the C drive in the Windows world, here in the Linux operating system, we have the /. So this is similar to the C drive. That's where everything starts. And then we have some very important directories in there. So let's take a look at these directories once again, following the file system hierarchy standard. The first directory that we can see is the /bin. The /bin directory, bin stands for binary. And what we can see in that directory, if I list it, I'm going to see a bunch of green files identified in green. We do have some other colors. Actually, these colors are just to facilitate our understanding. They do not actually determine what the file does or what the file is, but it can tell us a little bit about those files. But overall, these files here are all binary files, binary tools. So they're basically just files that will execute something. They're executable. So these executable files will perform a task. Now the difference in these colors are the files that are represented in green are just the regular binary files with the executable permission. The binaries here shown in kind of a light blue, these are links, these are symbolic links. So they're shortcuts pointing out to other files, but they are pointing out to other binary tools. And we also have some files here that are, the background is in red and the characters are in white. These are binaries, but they have the SUID bit enabled. But again, all of them at the end, ultimately, they are executable files. For example, when we run the ping command to test the connectivity, well, this is a binary file that resides here in this /bin directory. There it is. Now, there is a difference between the /bin directory and the /sbin directory. And the difference is the /bin directory stores files or tools that can be used by the administrator, root, and also by regular users. Whereas in the /sbin directory, we can see some administrative tools. Now, it does not mean that regular users cannot execute these tools, or at least some of them. They can. What they cannot do is use these tools to perform administrative tasks. For example, change configuration. So I could use the IP tool to change the IP address. However, since I'm a regular user, the system won't allow me to do such. Obviously, I could use sudo, but then I would be running that tool. I would be invoking the IP tool as the root user. Now, we also have the /boot directory. There it is. And the /boot directory is the directory that stores bootable files. More specifically, the kernel. So we learned that the Linux operating system is a combination of tools, the kernel, and additional tools. This is exactly where the kernel is stored. Specifically, this is my kernel right here, with some other complementary files, but all these other files are complementing the kernel and the boot process, or the files that store information required to execute the boot process. For example, grub, which is the bootloader system. This means that this directory here, without this directory here, I cannot boot my system. Specifically because the kernel is right here. Now, obviously, since in the Linux world everything can be configured, there are situations where you may, for example, dispose of this directory and still boot your system, but you'd have to configure, you'd have to tell the bootloader, for in this example, grub, you'd have to tell grub where it should look for the kernel. But by default, this is where the kernel resides. Then we have the /cd-rom, and it is just a mount point to your media drive. We also have the /dev directory, and we covered that in our previous class. That's where all devices are identified. Just to remember, everything in the Linux world is a file, including hardware devices. So your storage device, your keyboard, your mouse, all of your hardware, all of your devices are represented by files that reside in the /dev directory, just like the RAM memory. Then we have the /etc directory. The /etc directory stores configuration files. So all the any behavior presented by your system is presented as such because the system has been configured to work in that direction, to perform that way. Not all of the configuration are configured in the /etc directory, but most of them. So, for example, if you want to configure your network interface, there is a file in the /etc directory that you have to configure in order to determine your IP address. If you have a server where you're running a web server to store web pages and service web pages, well, there's going to be a configuration file in this /etc directory to determine how that application, how that software is going to behave. Now, once again, it does not mean that all configuration files will be stored in the /etc directory. However, that is the standard. So if you should always do your best, try your best in order to store configuration files in this /etc directory. Then we have the /lib, which is where the libraries reside. Similarly, we have the lib64 in case your system is a 64-bit system. So you have library files in both directories, lib and lib64. We also have the /media directory, and that is where all mount points are supposed to be in order to access external devices. So in order to access, let's say that you have a CD-ROM drive, well, you're supposed to have a subdirectory in a /media that is going to be a mount point to your media, to your CD-ROM media, DV-ROM, whatever that is. Same thing for flash drives. You're supposed to create in the /media directory a subdirectory that is going to be used as a mount point to your flash drive when you plug your flash drive in. External hard drive. So it doesn't matter. Any type of external media is supposed to be accessed via a mount point in the /media directory. You may ask yourself, but what about the /CD-ROM directory? Well, actually the /CD-ROM directory can also reside in the /media directory. But since it is common to see devices, it's always been common to see the CD-ROM drive or DVD-ROM drive as an internal drive attached to your device. They decided to also create this separate folder or directory in the / directory, which is the /CD-ROM. The /MNT, is similar to the /media, however, not necessarily to access external devices. It is just a directory that is there in order to store mount points, directories that will be used as mount points to other media, but not necessarily external media. For example, in our previous module, we created an additional hard drive. Instead of mounting that additional hard drive as using a mount point in the /media, we actually used the /MNT, not the /media. So you can use either of them as a folder that will have the mount point to another device. But just by default, you use /media in case you want to define a mount point to an external device, such as a flash drive, an external hard drive, a CD-ROM, DVD-ROM, those type of stuff. If you're accessing, for example, an additional hard drive, an additional partition, a network, a shared folder available in the network, a Windows shared folder, you're supposed to mount it via the /MNT directory. Then we have the /OPT directory. And the idea of this directory is to store third-party software. Whenever you install a software, most of the times you're going to use the package manager. And we will have another module where we're going to focus on package managers. But the package manager, which is similar to installing a MSI.MSI software in a Windows system, you don't know where the files are going to go to. When in a Windows world, when you install a software using the .msi, which is the Microsoft installer type of file, it will copy the files to some different folders. When you install a software in a Linux world using a package manager, the same thing is going to happen. That package manager will copy the proper files to several different directories or locations. Now, if you don't install a software based on a package manager, you're going to have to download the source. Most likely, you're going to download the source of that software. When you download the source of a software, you have two options. One is, if it's the source, or also called tarball, of a software, but it's a tarball provided by the official maintainer and developer of that software, you're supposed to install it in the /usr/local subdirectory. If it's not an official software, you're supposed to install it in the /opt directory. So that's the difference. That's the difference between installing a software in the /opt and in the /usr/local subdirectory. If it's official software, /usr/local. If it's a third party, unofficial, at least unofficial for your distribution, it should go in the /opt directory. Then we also have the /proc, and we can at once analyze these three here. Oops. /proc, /run, and /sys. Well, back in the day, when the Linux kernel was still in its 2.something version, so in version 2, we are currently in version 4, but when it was still in version 2, everything that was being executed, everything that was running in the memory, in the RAM, would have an associated file residing in the /proc directory. So all temporary information was determined or addressed by a file in the /proc directory. For example, if you have a software running, you'd have a file associated with that process. The amount of information that the amount of RAM that your system has and the amount of RAM that is being used, well, there is a file in the /proc directory identifying that. Information about a specific software, you'd also have files in the /proc. Then in version 3, it started in version 2, but it actually it's been deployed starting in the kernel version 3, where system information will reside in the /sys directory. Processes information reside in the /proc directory. However, they're still making these changes, this separation. It is very common to see files that are supposed to go in the /sys directory, but they are still residing in the /proc directory. The same thing for run. Information about processes that are running, specifically process ID. Every software that is running in a Linux system has what is called a PID, process identification, PID file associated with that process. Previously, those files would reside in the /var/run directory. Then they started to shift to the /run directory. And again, it is also common to see many softwares where that are defining their run files or their PID files residing in the /var/run. Some others have already started changing to the /run directory. We also have the /root directory, and if I try to list the content of that directory, I can't, only if I use sudo. That is because the /root directory is the home directory for that user. Which user? The root the root user. So I skipped the /home directory because I wanted to get here first. So the /root directory is the personal directory belonging to the root user. Similarly, we have the home directories or personal directories that belong to the regular users. So each regular user has its own called home directory in the /home directory. Then we have the /srv directory. And once again, that is a directory that's been changing, at least the focus has been changing. Back in the day, all types of files that are supposed to be served to clients by a server application would store those files in the /var directory. Then they decided to change this standard and move those files to the /srv directory. So for example, once again, if you have a server that is supposed to be a web server, it's supposed to store web pages to be delivered, to be serviced or served to HTTP clients. Well, back in the day, those web page files would reside in the /var directory. Actually, there would be a subdirectory according to the application. So if you had a web server, you'd have the /var/www subdirectory. Then they moved that to the /srv directory. So those files are now stored in the /srv /www in case you want to store web page files. FTP, in case you have a FTP server, the files that are to be served by that FTP server should reside in the /srv/ftp subdirectory. Then we have the /tmp directory, which we already discussed in a previous module. And just to remind you, this is the directory where we have the sticky bit right there. So this directory is a temporary directory. I mean, the directory itself is not temporary, but the files that it stores are temporary. Any file that is stored in that directory will be deleted once the system is rebooted or after a while, by default a week, and it may change according to the distribution. You can actually redefine that. But what matters is the goal of using this directory is to store files that are supposed to, or files that can be removed, deleted after a while. Then we have the, and I will skip to the /var, then we'll go back to the /usr. Then we have the /var directory, and the goal of this directory is to store variable files. Files that vary in size and in content with quite some frequency. So for example, log files. Log files are text files that they're logging everything that happens in a software or in the system, for example. If you log in, it will generate a message, a record in a specific log file. If you have a database, such as MySQL, well, it is a very, the database files change very frequently. Therefore, the database files are stored in the /var directory. And lastly, we have the /usr directory. The /usr directory is also called the second largest structure or file system structure in the Linux world. Why? Because almost the same structure that we have in the / directory will also exist in the /usr directory. Not all, but many of them. So we can see that we have bin, so we have the /usr/bin, we have /usr/sbin, we have /usr/lib, and so many others. These other ones also match some other subdirectories that go in this / directory. Now, these are separate files. They are not links or copies of the files that reside in this / directory. These are independent files. but it is just a substructure that's been created in order to give a better organization to the files. Now, what type of files will go there? I mean, how do I know if a file, a binary file or a binary tool will reside in the /bin or in the /usr/bin? Well, the difference is files that are installed along with the installation of, this is the easiest way to understand it. Files that are installed along with the installation of your system, and they are native tools, they will go here. Native tools, we could mention these tools that are very common. For example, ping, cat, ls, all those basic tools that we know that exist in a Linux environment. Additional tools or programs, tools that you install afterwards will go in the /usr/bin. Same thing for the administrative tools. The ones that are basic for the execution of the system, the tools, the administrative tools that are required in order the system to work, they will reside in the /sbin directory right here. The ones that are once the system is running and you want to install additional administrative tools, then they will go in the /usr/sbin. You can also see some other files here. These are not directories, these are files, and they're symbolic links, which we're going to talk about in another module. But as previously mentioned, our goal here today was to learn about the main directories, at least the ones that are standardized by FHS. I hope you enjoyed this class. Thank you very much. Hello, welcome to this class, and here we're studying our module 7, and our topic is the Linux kernel and its modules. So the idea here is to understand how the Linux kernel works. Actually, we previously discussed that in our first module. So we're just going to review how it works, but our main focus is going to be on the kernel modules. So first of all, let's take a look at this webpage right here, kernel.org. So this is the official kernel Linux webpage. Let's say that you want to download a new kernel. You want to install a new kernel in your system. This is the website that you could go to in order to understand, for example, what is the current version, the current kernel version. What are the changes between the previous version and the current one? Or what are the versions that are under development? Now, before you actually do that, you have to understand what the Linux kernel does. And again, we discussed that before, but just to remind you, we have to understand that the communication between you as a user and the hardware is actually divided in layers. So obviously, an end user cannot directly access the hardware for several reasons. For example, security, and also because, well, the end user won't be able to code the language required to send instructions to that hardware. That would be just unfeasible, unproductive. Even though you can have users that have the expertise, it is just not productive. So and again, for security reasons, management reasons, the interface between the user and the hardware must be made by a system. Okay, now that system, for example, if we compare with the Windows system has the combination of the software that will interface with the user and also what is called the kernel, which is the set of instructions, the platform of the operating system that will make the interface between the software and the hardware.
So keep in mind that you actually have 4 layers here. You have the user. The user is willing to do something. For example, the user is willing to access this website right here. Now, in order to visualize, to access this website, the user needs an interface, which is the software. In this case, it's my browser. And this software will send instructions to the hardware, or it wants to send instructions to the hardware, willing to do something. But again, for security reasons, operation reasons, and facilitation, the software developer does not want to use instructions that will directly communicate with the hardware. There are so many issues in that. For example, let's imagine that your computer has been infected by a virus. Well, what if that virus sends an instruction directly to the hardware, a wrong instruction that is capable of damaging that hardware, for example, the graphical interface? So in order to avoid that, there has to be a subsystem, a platform that is actually interfacing or performing the bridge between that software, in this case the virus, and the hardware. So those are the 4 layers that we have. That's what the kernel does. Now, coming back to our kernel.org website, the kernel is always evolving. It's in continuous development. Obviously, for a few reasons. The main one, it's always striving to get better, to deliver a better product. And that is why we have the versions in the kernel. For example, we can see here that the latest stable version is 5.5.6. Now, let's first understand what existed before, and it changed in the past years. After the version 2.6, it changed. So until the kernel version 2.6, we had this definition or this standard, which would say that, and this is still the same. So the first number, that is the major version. At the time, that's what it was called, the major version. So the major version would only change, and again, it's still the same. It would only change when a drastic change would come. For example, you have the current architecture, and there's been such a huge developments that this system entirely should change the way it works. For example, the operating system or the kernel was being developed focused on servers. Now it's being developed focused on cloud service, cloud operating system. Oh, that's a huge change. Therefore, you have that type of change, this type of versioning. Now, then you had what was called the minor version. Now, the minor version would still deliver some important changes, but not as important. So here you could see, for example, the way that an architecture is supported. Then you'd have the release. This would simply represent some updates. You also have the possibility, and we don't see any version here with a 4th number, right? And the reason is that 4th number, for example, we could have, and we're going to see that, we could have 5.5.6.12, for example. That's because that last number, in this case 12, is defined by the distribution. So let's say that many different distributions are adopting the Linux kernel version 5.5.6. Now, Ubuntu would have their 5.5.6.0, for example, their own version of that kernel. It's the same kernel, but adapted to the Ubuntu distribution. And as they evolve, as they release updates, for example, just simply installing new drivers, or there was a bug in the previous version, they corrected that bug, now they're going to deliver 5.5.6.1, and so forth, so on, 5.5.6.2. So as changes are being made by that distribution, they would release 5.5.6. whatever. Now again, still regarding this distribution, we could have, and actually we do have, another value that is also attached to the distribution and just a description. So for example, if you have the Ubuntu LTS version, you may have a name, which means that you could have 5.5.6.0 dash whatever LTS, for example. Yeah, so each distribution adopt that versioning. Now, as I said, this is standard where the first number represents a huge change, so-called the major version, then the minor version, then the release, and then the stability or stable number, also called ABI. But that was until version 2.6. After 2.6, when we jumped to kernel versions 3.0, that changed. So this number here still represents a major change, but not as it was in the past. For example, the kernel Linux version 2 was around for probably 15 years. Why? Because there was no huge architecture change that would justify going from version 2 to version 3. That happened from version 1, actually from version 0 to version 1, and then from version 1 to version 2. And then they decided to just stop that. So then came version 3, version 4, version 5, which is still the Linux kernel version, but it's not called major version anymore. It's just kernel version. And this second number became the kernel, the major version. And this one became the minor version. Now, this first number still represents a major change, but not as major as it was until kernel 2.6. This one and this one, so the second and the third, are just representing some changes, where actually this one, the second number, represents some significant changes, and the third one is just updates of that second version over here, the second number over here. So that's how the kernel is versioned nowadays. We have to remember that we have a difference in this numbering before the version 3, which means 2.6 before and 3 after. Now, another very significant standard that we had until version 2.6 was the second digit, the second number here, would represent a stable or under development version, which means that you'd see distributions, production distributions with kernel version, let's say 2.0, 2.2, 2.4, 2.6. You would not see stable distributions with kernel 2.1, 2.3, 2.5, 2.7, because those were development kernel versions. Okay, so that's how the kernel is standardized. This is the website, and we have to understand how the kernel treats hardware. So we discussed that the main feature of the kernel is to interface, perform the bridge between the software and the hardware. Obviously, to interface with the hardware, it must know the instructions, it must know the drivers to those hardware. And that's basically what the kernel does. So it implements drivers that have a set of instructions of how to access the hardware. Therefore, it means that we have to understand how the Linux kernel treats drivers. We have to understand how to load drivers or modules. But before, so let's go here to our Linux machine. So
we have to understand that the way that the Linux kernel is going to access hardware is going to be by using drivers. It's the same way that the Linux operating system performs. The very same way. So it uses drivers to access those the hardware that you have. And just like in the Windows system, you have the built-in drivers and you have the modularized drivers or modules. What's the difference between those two? Built-in drivers, they are built into the kernel, which means that they are not external files. When the kernel is loaded, when you boot the system, the drivers are already loaded into the memory, into the RAM, because as it loads the kernel, it's loading those drivers. Those drivers are embedded in the kernel. Now, when you have device drivers loaded as modules, those are external files. Those are files that have to be loaded into the RAM. And this is going to be our focus. That's what you have to understand specifically for your daily basis when it comes to loading drivers and also for your exam. Because drivers that are embedded, built into the kernel, well, they're already there. There's nothing much that you have to do and that you can actually do unless you're going to compile a new kernel. Now, considering that you're using this kernel that you have installed and you want to manage the drivers that you have. So you're going to manage modularized drivers or modules. How can you manage those modules? There are a few commands that you can use to do that. So first of all, let's take a look at this command here. Uname, you could simply use uname, okay? But it's just going to show you the name of your machine. So if you want to see all the information regarding your system and your kernel, you can use uname-a. Now, what is important for us here is right here. That's what we want to analyze first. So as previously mentioned, we have here the kernel version 5, we have the major version 0, the minor version 0, we have the release 23 or the ABI, and this one is the one that is updated by the distribution. So each distribution will have its own update version or ABI. And then we can have a name that is identifying this specific system or this specific version of this distribution. So this is a generic Ubuntu. That's what they called it. Now, that along with this and this. So this distribution, this version specifically is the Ubuntu 18.04, and then we have a description of this architecture. So it's a Ubuntu SMP. And obviously we have some other information here. Okay, great. So we know how to analyze our kernel version. You could also do uname-r, and that is just going to show the the kernel version. There it is. Now, regarding the modules, how do we work with modules? First of all, we have to know the lsmod command, and it went too fast, so let me go back. lsmod, which stands for list modules. Let me do a pipe more here. Okay, so as we can see, in the first column, we have the module name. In the second column, we have the size in bytes. So you can see that these modules are actually very, very small. They are hardly using RAM space. How many devices are required by that driver? And if there is a dependency, and which other module is actually using depending on that driver. So drivers do have a dependency. just like softwares. So many times when you want to install a software, there is a prereq. So you have to install the prerequisite before actually installing that other software. Modules have the same concept. They have the same idea. So you have modules that actually depend on other modules. For example, we can see here the association between sound AC97 codec and AC97 bus. Okay. We can also see sound Intel 8X0 with sound AC97 codec. So this one is used by this one, which means that this one depends on this one. Okay. So we can see that there is a interdependence between a few drivers. Now, and if I just hit the space bar, I can scroll down and see there it is. So all these drivers here, they are loaded as modules. Now, once again, it does not mean that all the drivers that my system, my operating system is using is listed here. That's not what it says. It says that all these drivers here are listed as modules, external drivers. We also have the drivers that are embedded into the kernel. Okay, so these are the drivers. Now, in case I want to load a new driver, so let's say that I need to implement something that requires a module, requires a driver, and that driver is not installed, is not running. For example, let's say that you want to, for some reason, you're going to implement VLAN in your Linux system. So to implement VLAN, you need to load the driver that implements VLAN. So the VLAN technology is actually the protocol 8021Q. So what I need to do is to mod probe module 8021Q. Okay. How do I confirm whether it's working, it's been loaded or not? Well, I ask ls mode once again. It's going to be somewhere around here. Now, if I can't find it, obviously, I can do pipe grep 802, for example. Oh, and there it is. So observe that it not only loaded the 8021Q, but it also loaded GARP, MRP, those two drivers, GARP and MIP. How do I know that? Because used by, so GARP is used by 8021Q. MRP is used by 8021Q. In order to load this module, these other two modules that were not there before have been loaded as well. And that is actually the advantage of the mod probe command over the other one that we have, which is ins. So I have to use sudo insmod. You can also use insmod to load a driver. Now, two differences. One, which was previously mentioned, when you're loading a driver using modprobe, if there is a prereq, modprobe will load the prerequisite drivers first and then the one that you want to load. Insmod does not do that. Second difference, when you're using modprobe, you have to use the module name. When you're using insmod, you have to know the driver, the module file. Now, where do the driver files or module files reside? They are in the /lib/modules, and then you're going to see your kernel version, 5.0.0.23 generic. There it is. Okay, but in which directory? Okay, let's try kernel, and you can see that you have a bunch of subdirectories here that are actually defining according to their their classification. For example, /lib/module/ the kernel version /kernel/drivers, and there you're going to have a bunch of subdirectories. So obviously, you have to know how to navigate. You have to have an idea of where that driver is going to be. Now, obviously, if you know part of the file name, you just don't know where the driver resides, you can also always use the find command. For example, I could do find /lib/modules/my kernel version. I'm looking for a file with name, with name 802. So let's see if we can find something. Well, actually I can find a bunch of stuff, but what is important here is right here. There it is. I could be more precise in my search, obviously. I could do this. So I want to find, starting in this directory, because find is a recursive command. Starting here, I want to find a driver or a module with name, but I don't know the precise file name. I just know part of it, and the part of it is going to be the actual module name. So I use single quotes with asterisk before and after. Let's see. And there it is. Now, which one should I use? This one or this one? Well, we can see here that this one is actually inside this one, which means that this is a directory. So in case I want to load this driver, I am going to do insmod, and I'm going to copy and paste this here. Oh, oops. There we go. Now, so I forgot that I'm in my virtual machine. So let me type it in, modules, the kernel net 812.1q, and then that name over there. Obviously, it says, okay, you can't do it because it's already there. It's been loaded already. So could not insert module, file exists. Oh, that's because we have the 802.1q module driver loaded. What I'm going to do is I'm going to modprobe -r to remove that module from the RAM. 802.1q. And now I'm going to load it again. But wait, now I have a different message. Why? Because again, just like when we are loading a module using modprobe, it will load the dependencies, the prerequisites. When we remove with the modprobe -r, it's also going to remove the prerequisites, the dependencies. Now, if I want to use insmod, I would have to first load those other two modules, which we're not going to do because we can see that we should do it using modprobe. That's a lot easier. But you can see here now that you can use insmod. It's just going to give you more work. So you have those two different commands. In case, let me reload. So there, let me load it again. In case I want to get some information about a module that I have, I can use modinfo. And let me do a pipe more here. Oh, okay, so that module is actually an external module. It's not a built-in driver that resides in that directory, that specific file, version 1.8, the license is GPL. There is a alias to that driver. You can create aliases. Depends, MRP, GARP. So you can see here that in order to load this module, you have to previously load these two unless you use modprobe, as we discussed. Okay, very good. Now, there is still one big problem here, which is when we load a module, we're loading it into the RAM, which means that if I reboot my machine, this module won't be there. It won't be loaded. Why? Because I ran this module, I invoked this module during the runtime. I did not configure it in order to be loaded into the RAM during the boot time. How can we overcome that problem? How can we solve that problem? Well, pretty simple actually. We can edit the slash etc slash modules dash load dot d slash, and then you just need a file in this directory ending with .conf. So you could create a file here. Let's say Linux plus.conf. You could do that. So any file residing in this directory ending with .conf will be loaded during boot time. Now, instead of doing that, I'm going to edit the modules.conf file. There. That's actually why this file exists here, and you can see that it's empty. So what can I do? I can simply insert here 8021Q. There. Now, another important detail is there are some drivers that they give you options. You can use options to that driver. If that's the case, the way that you load the driver is options. So you use the keyword options, then the driver name, then space the options that driver allows you to use. Obviously, it will depend on the driver, the module name. You have to study, you have to read the documentation to see if that module gives you options, what the options are, and how to define those options. Another important feature that you have in this file is the possibility of using blacklist. Now, why would you have such a resource? Why would you have such a keyword? The idea here is to prohibit the kernel from loading a specific driver during boot time. Now, why would you want to do that? Well, for example, let's say that you have a new driver. You just updated, you just changed your, let's say your video board, your GPA. And there is a driver that was being automatically loaded. It's not listed here, so you can't simply go here and remove, say, okay, I don't want to load that driver anymore. Why? Because there are the drivers that are installed as external drivers or modules. But during the system installation, they're going to go in an external file that is loaded along with the Linux kernel. So this is not a built-in module or not a set of built-in modules. They are modules, they're external, they're not built-in drivers, but they are loaded as the system boots, as the system initializes. But how can you prevent that module from being loaded? Well, you can blacklist it here. Then it won't be loaded. Again, now, why would you want to do that? So let's say that you just changed your VGA. And there is a conflict with that former driver that you were using. And you can't prohibit that driver from being loaded. Well, you actually can. You come here and you blacklist it. So that's how you can do it. One example that we have here is you may have it, you may not. It depends on your system. But so let's just take a look at this file here. As I mentioned, there is a file in the /etc/modules-load.d directory that ends with .conf, which means that this file will be loaded during boot time. It's called cups filters. And there it is, lp ppdev parport_pc. So these three drivers are being loaded during the boot time. Why? Because the printing system, which is called cups, is defining these three drivers to be loaded. So we saw here in this class what a kernel does. We saw how we can identify a kernel version and how it works when interfacing with the drivers, so with the hardware. So to do that, it can use built-in drivers or it can use external modules. We also saw how to load modules. We learned that there may be a relationship of interdependence between drivers. We can use a command, in this case modprobe, that will overcome that dependence. Or you can also use insmod. We also saw how to configure a module or a set of modules to be loaded during boot time, and also how to prevent a module to be loaded during boot time. I hope you enjoyed this class. Thank you very much. Hello, welcome to our Module 8, and our goal here is to understand the booting process, the Linux boot process. And one of the features that we have to understand is another software, or actually a couple of softwares that are required in order to perform the booting process. More specifically, talking about the Lilo bootloader and also the Grub bootloader. And after that, once the kernel is requested, invoked by one of these two softwares, then we're going to have the Linux boot process. So we're going to understand this boot process. And once the Linux booting process starts, we are going to have the main process being invoked by the kernel, which can be the init, systemd, or upstart. So we're going to see and understand how this booting process works. Okay, so first we have to just keep in mind it's not operating system specific. This is hardware specific. That's how the traditional desktop or servers computer operate. When you power on your machine, so let's assume we're talking about our own machines. When you power on your machine, that machine has a software attached to its motherboard. It can be a BIOS, basic input-output system, or it can be the Unified Extensible Firmware Interface, UFI. Either one, they will be the first software to be loaded by your hardware. Now, there is a difference that we have to understand between these two subsystems. Basically, we can keep in mind that the UEFI is the evolution of BIOS. So BIOS was the very first booting subsystem implemented in motherboards. Now, obviously, because of the evolution of hardware and software, the BIOS was not able to keep up with this evolution, and some limitations arrived. For example, the type of hard drive that it would support, the number of partitions that it would recognize, the hardware architecture, for example, moving from 32 bits to 64 bits. So due to this evolution, so manufacturers had to evolve, they had to adjust their motherboards in order to, for example, recognize the CPU, the keyboard, the booting process, how the booting process would work, the different types of hard drives, the different types of file systems. So all these evolutions that came with time. So we moved to the UEFI. Now, what the UEFI or the BIOS is going to do basically is run a set of tests. That is their first step. They're going to run a set of tests checking, for example, how much RAM your hardware has, or if you have a keyboard. So a bunch of hardware checking tasks will be performed, including detecting the hard drive or any type of storage device. Now, once those tests are performed and the BIOS or the UEFI is capable of detecting the storage device, the location where it should look for a bootable operating system, then it would address the booting process to that device. So for example, you could have the MBR master boot record, or you can also have the GUID partition table. Now, following the same idea
of difference between BIOS and UEFI, we can make the same analogy to compare MBR and GPT. MBR had a few limitations, and we discussed this in one of our first modules, module 2, if I'm not mistaken. But just to recap, basically MBR has a few limitations in regards to the number of partitions that it will allow you to create in your hard drive or in your storage device, the maximum size of that device that it would recognize, and the GUID partition table actually supports everything that the MBR supported, which means that if you have GPT and you have a old operating system, for example, Windows XP, which does not support GPT. So if you have a system with GPT, well, Windows XP would actually work because GPT does support MBR. It actually implements a deprecated MBR. And it recognizes so much more storage space, and also it allows you to create so many more different partitions. This is valid for the MBR and also the GPT. The operating system that is being used will dictate how many different partitions you may create. But since we're talking about our focus is on Linux, so if we analyze MBR, we have a limitation of 16 partitions. It doesn't mean that we have 16 usable partitions, but you can divide your hard drive in 16 partitions. And the GPT will allow you to create up to 128 partitions. So the way it works is you power on your machine, some tests will be performed by the BIOS or the UEFI, then it will look for a storage device. Let's say that it's just the traditional device where you're gonna have a hard disk. So the BIOS or the UEFI will point out to that device and search for the MBR or the GPT in that device, which is also a bootable system. It's a system, a software that has information of how to initiate an operating system. So then the MBR or the GPT is invoked. Now, the way that the MBR or the GPT will work, it will be two different options. One, it will simply search for a bootable partition and load the operating system that is installed in that bootable partition. Or it will look for a bootloader. The bootloader is another software that has information or is supposed to have information of possible operating systems or just one operating system. So let's say that you have a dual boot machine. You want to install Linux and Windows in your machine. The most traditional way to do that is to install in the MBR or in the GPT a bootloader, and that bootloader will display a screen for you, a menu for you, that will give you the option to select which operating system you actually want to boot, Windows or Linux. So this bootloader software has to have information about the information on the possible operating systems that you have installed in your machine. So then you're going to see that that menu, and you're going to pick the proper operating system that you want to boot, Windows or Linux. Okay, we're analyzing Linux. Now, how is this bootloader going to invoke and load that operating system? Well, we have to remember that the Linux operating system is basically a kernel. That's what the Linux OS is. It's a kernel. But it also comes with a set of other softwares. But what is important here is to load the kernel and also the modules or external drivers that are required to initiate and deliver that operating system for you, make that operating system usable. So we have to remind from our last module that we have two different options, two different ways of installing drivers. They can be built in, which means that once the kernel is loaded, these drivers are loaded as well because they're built in the kernel, or they can be external drivers or external modules. Either way, when you request the bootloader to boot that operating system, in this case Linux, this bootloader has to have the information required to load the kernel plus those modules. Two different files, at least two different files. So you're going to have the kernel file and also what is called the init.rd or initial RAM disk file. Once those two files are loaded, then the drivers, ideally the drivers that are required in order to boot the operating system, will be loaded, and the operating system will be able to initiate the booting process and finalize it. Now, just to give you an idea of what type of module or drivers the bootloader has to address in order to make this operating system usable is, for example, the Filesystem drivers. So let's say that your Linux system is using a storage device, the hard drive, with partitions in ext4. There's another partition in btrfs, and also we have the swap partition. Okay, these are all drivers. The information that is required to access the file system is actually deployed as a driver. It's a device. Devices are addressed based on drivers. So this is the type, your network interface, your graphical interface. So any type of hardware has to have a driver, and the bootloader is responsible for finding that file and loading that file into the RAM, or those files more specifically. So load the kernel and the drivers, and then finally load the first software. Nowadays, you actually have the possibility of using one of these three initial processes. You have the init, you have systemd, and you have upstart. The init was the very first initial process deployed in the Linux operating system. It came since the beginning. It's been there since the beginning, since 1991, all the way to 2010, 2011. Then some operating systems started to shift to systemd, and others to upstart. Some others actually migrated from init to systemd and then to upstart. Some, they went from init to systemd, and some from init directly to upstart. Now, nowadays, systemd became a default, at least for the majority of the distributions. Take it Ubuntu, Debian, CentOS, Red Hat. So the majority of the Linux distributions are using systemd. So basically the difference between these processes is their performance and their capability to implement on the fly, deploy changes on the fly, which basically that's the difference between systemd/upstart and init. Basically, systemd and upstart, they're very similar. It's more of a configuration difference than anything else, but both of them, they obviously, since they were developed recently, let's say, they perform a lot better. They have some new features that the init process didn't have. Now, once the kernel invokes the init process or the systemd, whatever that is that your system is using, and these processes, whether it's init, systemd, or upstart, they're called the parent of all processes. That is going to be process number one. It's always going to be process number one. And there is a hierarchy between processes. There may be a hierarchy of processes in the Linux environment, which means that you have the possibility of having one process that is parent to other processes. But one thing that is common to all processes is that all of them will be children to the init or the systemd or the upstart process. So then the one of these initialization processes will invoke the other processes, such as, let's say that you have a web server. So there is a service, there is a process that has to be initiated in order to bring your web server up. You also, but before you bring the web server up, you need your network configuration set up. So the network interfaces will be configured by a process that has to be invoked by one of these three processes. So all the other softwares, all the other processes, they will be invoked by the initial process, whether it's init, systemd, or upstart. Now, there is also a difference of what is called run level. And run level is a concept more related to the init process than systemd or upstart. However, you still have the possibility of defining run levels just because the developers wanted to keep a compatibility between systemd and upstart and the init process. So people that come from the very initial versions of the Linux operating system, they would migrate from the init, let's say, to the systemd initial process more smooth. So what is actually the run level? The run level is basically a configuration of a set of services or softwares that are supposed to initiate. So basically, you're creating groups. You are saying, I want to, when I start my system in this specific run level, let's say run level 2, this set of softwares here are supposed to be loaded during the booting process. If I start my system in run level 3, then another set of softwares. Run level 5, another set of softwares. So basically, each run level is defining which softwares should be loaded and also which softwares should be unloaded or stopped. That is a concept very much used in the Linux world. Started and stopped. So you have run levels defining softwares that are supposed to be started and other softwares that are supposed to be stopped. Now, by default, and it's totally configurable, but by default, run level 0 means you want to shut the machine down. You want to turn it off. Run level 1 means you want to boot the operating system, but as a single user, which means that the operating system won't have a bunch of features such as network support. You won't be able to use the network. You won't be able to perform multi-user tasks. Then you have the run level 2, which is only implemented by Debian-based operating distributions. So, for example, Gentoo, Debian, Ubuntu, Mint, these distributions that are Debian-based. And it means that the run level 2 for these distributions will load a full set of softwares, including the graphical environment. And then you have run level 3, which is a full set of softwares for other distributions such as Red Hat, Mandriva, SUSE, CentOS, and many others. A bunch of softwares will be loaded, including network support, softwares that use the network. However, the graphical interface is not going to be loaded. And to complement this run level 3, we have run level 5. Also, to those mentioned distributions, it will do the same, but including the graphical interface. Run level 4 is not used, so they reserved it for future use. And then we have the final run level, which is run level 6, which means I want to reboot my machine, not shut down, but reboot. So according to the run level that you pick, the run level that you define the machine to be booted, it will finalize loading those softwares according to the run level, and then you have either the console displayed for you so you can log in and start using the machine, or the graphical interface. So that is how the Linux booting process works. So just revise it. You have power on your machine. A set of tests will be performed either by BIOS or UEFI. It will then, one of these two will then invoke the booting system, which can be, it can support MBR or GPT, which will point out to the bootloader. There are two, and I'm going to discuss that in our next video, but there are two main softwares, bootloading softwares, at least in the Linux world, which are Lilo and Grub. One of these bootloaders will load the operating system that you pick. Since we're studying Linux, let's focus on the Linux operating system. Basically, to load the Linux operating system, it will load the kernel and the initial RD, which is a set of drivers. Once all the drivers or modules that are required to read basic information, basic device, hardware devices are loaded, then the very first process is initiated, the very first software is loaded into the RAM, whether it's the init, systemd, or upstart. And one of these initial processes will invoke a set of other softwares according to the run level that you defined. So that is how the Linux booting process work. I hope you enjoyed this class. And now we're going to see some tools that we can use in order to define the run level and the softwares that we want to associate with each specific run level. And we will also see how this entire process works. I hope you enjoyed this class. Thank you. Hello, welcome to Module 10, and our goal here is to talk about and learn a little bit about how the Linux operating system treats devices, how the kernel actually accesses devices in the Linux environment. Now, before we actually analyze those files, before we actually understand how those devices are identified and accessed via files, we have to understand the different types of files that we have in the Linux environment. In a previous module, actually in previous modules, we talked about how Linux treats everything as a file. It doesn't matter what it is, it's represented by a file in this environment. So we have what we call files. In the Linux world, it's treated as regular files. We also have directories, which are files of the type of directory. So we have different file types according to what that file has to do. So those are two file types that we previously discussed. I previously mentioned the symbolic links as well, and we're going to see it here today. And then we have some other types, such as the pipe. So a pipe file is a file that represents a connection between two softwares, two tools, two programs. For example, when we use, such as here, ls pipe more, I'm connecting two softwares, I'm connecting two tools. When I do this, the output of one tool will become the input of another tool. So there must be a link between these tools, and which means that a file must be created to connect those two tools. That file type is called pipe. So that is another type of file that we have. Similarly, we also have the socket files. The socket files are the files that actually represent a connection, a network connection. For example, if you have a web server, when a new client connects to your web server requesting a web page, for example, a socket file will be created to attend that client. And then we have two other types of files. We have block and we have character. Both these two file types represent devices in the Linux environment. And obviously there is a difference between these two types of files. A character device is a device that communicates in series, which means that each byte is transmitted at a time. Whereas in a block device, you have a block of bytes being transmitted. So, for example, if you perform a remote connection, let's say that you telnet another machine or you SSH another machine, each key that you stroke will represent a byte. And that key, that letter, for example, will be transmitted at each time that you hit that key. So let's say that you're going to type hello. As you press H, and a character represents a byte, so that byte will be transmitted. As you press E, E will be transmitted as a byte, then L, then L, then O. So each character, which is a byte, will be transmitted as you hit that key. It's different from a block device. A block device will transmit in chunks. So it's not just a single character, it's by blocks. So that's why you have that differentiation here of a character device. Those are the ones that transmit in characters or bytes, byte by byte. And we have the ones that transmit blocks by blocks, blocks of bytes. So some examples here we can think about, and we're going to see that, is, for example, the hard drive. When you're trying to save a file, a hard drive is a block device. That means that the file that you want to save in your disk won't be sent byte by byte, letter by letter, but a chunk of bytes will be stored in your hard drive. And it's different, for example, when you're using your display or your mouse, which are serialized or character devices. So let's take a look at these files. First of all, we have to remember that every device has a corresponding file in the /dev directory. So if we list the /dev directory, we're going to see many files that are representing specific devices. For example, the audio system is actually a little bit different because it's not represented by just one single file. You have a bunch of files because you have the channels and you have the interruption that will be used to communicate with that device. So you have the type of the spectrum. So each different information that you have available in a audio device will be represented by a different file over here. That's why we can see here so many audio files here. There are some others down there, such as mids. There are so many files representing your audio interface. But let's take a look at the most important ones here. Let's start with the /dev/bus directory. That is actually a directory. So if I do ls-l/dev/bus, we're going to see that I can have more than one directory there, but at least I'll have the USB. So my buses, my USB buses are going to reside within that directory. And I can see that here that I actually have two USB ports, which are identified by the files 001 and 003. Now, here, the first bit in the I know structure is the bit that actually identifies my file type. Again, we have regular file, which is represented by a dash. We have a directory represented by a D. We have a pipe represented by P. We have socket represented by S. We have a symbolic link represented by L, as in link. And then we have our two device types,
which are C as in character and B as in block. As we can see here, these two devices are character devices. So my USB ports are character devices, which actually explain why, one of the reasons why the USB port cannot be as fast as the hard drive. So another information that we see here, and it is very important, is these two numbers right here. A device in Linux is accessed and controlled by the kernel according to those two numbers right there. They're called the major version and the minor version, or major device ID and minor device ID. These two numbers are the numbers that will identify to the kernel what is the proper driver that should be used to access, control that device. So the kernel has a bunch of drivers. Which driver should the kernel use in order to fully and properly access that hardware, that component? So here we have the major driver version 189 that tells my kernel that there is a group of device drivers. In this case, this group is identified by 189, but it's a group. But at least the kernel now knows that, okay, out of all my device drivers that I have, to access this device, I have to load a driver, use a driver that resides within this specific group. Now, which of these specific drivers that I have in this group should I use in order to access that device? Okay, so that's 0. Oh, so it knows that we'll use that specific information to access that device. Then we have 189, 2 to access my other device. Now, let's go back and take another look at the /dev directory. We also have the CD-ROM file here, but it's a little bit different because let's take a look at it. It's not quite a block, neither a character device. We can see by the color, which is a light blue, identified in light blue, and it's a symbolic link file. That's because, just to make it easier for users, the kernel maintainers, they decided to create a symbolic link that identifies that specific device, which is the CD-ROM drive. But the CD-ROM drive is actually accessed not by using the /dev/CD-ROM file. It actually uses the /dev/sr0 file. So if we take a look at the /dev/sr0 file, oh, now we can see that this file here can be controlled by this driver, and it is a block device, as expected from a CD-ROM drive. And if we keep scrolling down, same thing for DVD, as we can see up here. We also have the /dev/fd, and if we actually take a look at it, it can hold a number of files. And this one actually, /dev/pts/0, is the one that will actually identify, in case you have it, your floppy disk. It can also, in some systems, it can be identified by a symbolic link called /dev/floppy, which does not exist here in the Ubuntu system, at least not in this version. Another one that we have right here. There. That's our RAM memory. So if I decide to, for example, if I dump a bunch of zeros into this
file. If I do, for example, if I do a cat any file and I redirect this to /dev/man, obviously I would have to be the root user in order to do that. This can crash my system and force my machine to reboot. Because what I'm doing is I'm using my administrator privileges to just dump something random information, random data into my RAM. There is no memory allocation being performed, so no memory control, which means that everything that I have running in my memory will at some point be exploited. I will have a buffer overflow happening right there. My machine is going to crash. If we continue, then we're also going to see right here. That's the file that we saw, that it actually represents our CD-ROM, and we also have our storage devices, which is our partitions. Let's remember that the /dev/sda and /dev/sdb are the storage devices, the hard disks. Within those hard disks, we have our partitions. So in the /dev/sda, I have just one partition. Same thing in the /dev/sdb, I only have one partition, /dev/sdb1. There you go. And I also have my terminals, my consoles, TTYs. And those are the most important files. Now, we also have this /dev/input directory, and here we can see our mouse. So these are some of the files that are identified, that are important to have and to know in the /dev directory. But most importantly, we have to understand the difference between a block device and a character device right here. Now, let's say that for any specific reason, you have to create a device file, a file to control, to access, represent a device. You can't do that. You have to use the mknode command or mknod. Obviously, you have to be the administrator to do such. So let's say that I want to create a device file called /dev/mydevice. It's a character file. The major driver is 4, the minor driver is 10. There it is. There it is. I created that device. Now, obviously, it doesn't mean that you actually have a device. But it means that in case, for some reason, you are not being able to access a device because for some reason you lost the file that has the instructions to access that device. That's how you can manually create that file. Now, that is not, nowadays, it's not very helpful because you have some other tools to allow you to verify if you have devices that are not being addressed by the kernel. For example, you can install the makedev package, which I already have running. So all that you have to do is to, if you have makedev installed, you go to the /dev directory and you run the makedev command right here. What it's going to do is it will search for all the devices, all the components, all the hardware components that your machine has. And in case there isn't a file, a device file, either block or character, addressing that file, the makedev command, the makedev tool will create that for you. So this is how the Linux operating system treats devices in specifically character and block devices. We also saw how to identify how the kernel will address that specific device based on the major version, the major driver, and the minor driver. And if needed to, you can run the makedev tool to rebuild those device files. I hope you enjoyed this class. Thank you very much. Hello, welcome. This is Module 11, and our topic is Package Managers. Before we actually learn how to work with the main package managers that we have to understand why we would use these so-called package managers. And we also have to differentiate the main types of package managers, which are basically the standalone package managers and the internet-based or online-based package managers. But like I said, first of all, we have to understand why we would use such types of softwares or tools. So the reason is, back in the day, well, it still exists, it is still used. There are situations where this is the only resource which is installing softwares based on their tarball, which is a compressed file containing a bunch of source files with the tool source code. But back in the day, before 94, when we didn't have package managers, and this is not only in the Linux world, but also in the Unix world itself entirely, when we did not have the package managers, when you needed or wanted to install a software, you'd have to download a compressed file, which is called tarball. That tarball, which is similar to a zip file. And we're going to actually discuss the difference between zip files and tarballs and some other types of compressed files. But that's not important for now. What is important here is we had this compressed file or this package file that would have a bunch of source code files, which is basically the software with their source files and all the files that are required in order to compile, install, and run that software. So the problem with that was, as we can see here, first of all, a package of source files was or is required. You have many steps, so there are many steps involved. For example, you have to download that tarball, so you have to know where that tarball is available. You have to download it, you have to decompress it or depackage it to extract the files. After that, you have to run a configuration step, which is basically asking for that tool to verify if your machine has what it requires, and also check your architecture, your version, your operating system version, and your machine architecture. So basically, since this tarball contains source files have to be compiled. So there is a compiling step. In order to compile files, the files are compiled according to your architecture, according to some prerequisites or dependencies, according to the specific operating system, even according to the operating system version. So there are a lot of variables that must be met in order to be able to actually compile a software. So first you would have to run this configuration step. In this configuration step, you'd also be able to determine a bunch of different setups. For example, where do I want to install this software? This software has many different resources. Do I have to enable all these resources? Let's say that no, I don't need everything that software has to offer me. I only want to install these specific resources. So you can determine that. So basically, it's a configuration of a installation. After that, then comes the compilation step. And the compilation will be where you're going to invoke your compiler in order to read all those source files and generate the executable files, for example, or the header files, or any files that are required in order to that you have to install in order to run that tool. After you compile, then comes the installation process, which is basically copying the files to their proper directories. Now, this is related to another issue. Since there is no standard, because each person or each company that creates the source of a software, they can determine how that software is going to be installed, or they can determine whether they will create a script that will allow you to configure where those files will be installed or not. So there is no standard, which means that you can have one software that once compiled and installed, files will be copied to a specific location. Other softwares can copy the files to other location. You can have different permissions to different files. You can have a software that once compiled and installed, it will create users required to run that software, other softwares that won't automatically create those users. So again, since there is no standard, there is no management, it can become quite complex to manage softwares that are installed via their tarball or via their source files. And again, you also need to download the file or the tarball in order to install that software, which can result in another problem. That software will only have the source code or the tool to do what you want it to do, which is that specific tool. If that specific tool relies on other softwares, if it expects your machine to have other softwares, you have to make sure that those other softwares are installed. Now, this is not only a tarball problem, because package managers can also present that problem, but it's a lot easier to solve, and that's what we're going to discuss. So, because of that, because of all those different challenges, in '94, Debian created this package manager called Debian Package Manager, or DPKG. And basically what the Debian package manager does is, based on the source files of a specific tool, it will compile and determine a bunch of patterns, a bunch of steps and tasks that should be done once a package is installed, once a software is installed. So all those steps that we mentioned, that is required when you're installing a software via its tarball, it's not the same here anymore. Now, you still have to find that package. So let's say that you want to install, for example, the Apache web server. Okay, you do have to go online, find where the package, in this case, if it's a Debian package manager, if it's a Debian package, then it's going to be a .deb file. So you still have to go online, find that .deb file, download it. But once you download it, that package already has instructions such as, first of all, the files are already compiled. They are already executable, or whatever type of file that is, but they don't have to be compiled anymore. It's already pre-compiled. But the problem about having compiled files is that files, once they are compiled for a specific architecture, for a specific operating system, for a specific version, which means that you have to download the specific package, in this case, the specific deb package for your specific architecture and distribution. There is a level of compatibility between different distributions. For example, you are allowed, and most of the times it works, you are allowed to install a deb package that's being created for a Debian distribution, for example, for Debian 10. Well, there is a very high probability that same package will work in case you try to install it in a Ubuntu 18.04, because they come from the same base. Ubuntu comes from Debian. They are also in the same version of software, not specifically, but very similar. It's not like a Debian 10 compared with a Ubuntu 12.04, for example, which is very old. So obviously their versions must match at some level, but that is possible. Also, that package already has instructions of where to copy those files, what are the users that are required. In case that package also has dependencies, you can verify that. So what other packages does this package depends on? So once you find that out, you can just run a simple command to check that, then you can go online and download that other file. Now, in order to install package files, you have to use the proper package manager. So like I said, if you have a Debian distribution, well, most likely that you'll be using the dpkg package manager, which means that you have to download .deb packages. Let's say that you have a .deb package, but you're running a CentOS distribution. CentOS distribution uses the RPM, the Red Hat Package Manager. There are ways, or at least attempts, to convert deb packages to RPM packages. However, that's far from accurate. It can work. It might work in a few situations, but it's not reliable. So you should avoid doing that. So make sure that you have the proper package manager and the proper package. And here are some commands that we can use in order to work with Debian packages. So the command that we use in order to manage Debian packages is dpkg. That's how we invoke the Debian package manager, dpkg. So let's say that you just downloaded a .deb package. How can you install it? dpkg, right here, dpkg space -i space the file name .deb. That is going to install that package. You can do the same in case you want to update. So let's say that you have that package, once again, going back to our example, let's say that we have the Apache web server running and it's, let's say, version X. Now you just downloaded a new version and you want to install that new version. Well, you can simply do the dpkg -i that new package that is going to update that package. Another option is using the uppercase U. So dpkg -uppercase U will also update. You have other options here. If you want to remove, you can use the -r, the lowercase -r. There is a difference between the dpkg-r and dpkg-P. And the difference is, let's say that you have a package, you have a software installed and you want to remove it. You can use dpkg-r or -P. The difference is, if you want to maintain the configuration files, just in case, let's say that you're removing that package, you're removing that tool, but you want to make sure that you have a copy of the configuration files because you might need those configuration files in the future. So you should remove it using the dpkg-r. If you are positive, absolutely sure that you don't need any of those files that came along with that package, you can use the pkg -P. Not only configuration files will be removed, but all files associated with that package. Let's say that you're uninstalling, removing the MySQL server or the MySQL DBMS. Well, if you do a dpkg -P, not only the software will be uninstalled, but the database entirely, all databases. So all files associated with that tool. In case you want to see a list of all packages that you have installed, all packages that are being managed by your Debian package manager, you can use the pkg-L.
if you're looking for a specific package, then you have the pkg-l space the package name. Now, if you do this, you have to be certain of the package name, or you have to know the proper package name. You cannot just guess or know part of that name. You have to know the proper package name. That is why usually people use dpkg space -l pipe grep and then part of that software name. Let me give you an example. Let's say that you want to verify whether you have MySQL DBMS installed in your machine. Well, probably that package will have MySQL in its name, but you don't know if the package name is MySQL or MySQL-server or MySQL-DBMS. You're not quite sure. So you should do dpkg space -l space pipe grep MySQL. That is going to list all the packages that have MySQL in their name, which means that whether it's MySQL or MySQL-server or MySQL-DBMS, it will be listed just the same way. Then you have some other options. For example, dpkg space -L. It will list the files that were installed once a package was installed. Once again, when you install a package or a software, that software is not composed of one single file. It's composed of a set of files. The -L option will list all files associated with that package that you're mentioning. And then you have some other options there. Actually, you have more than these options here, many more, but these are the most important options. Now, the Debian Package Manager, dpkg, was created in 1994. Then, Red Hat created the Red Hat Package Manager in 97. It's the very same thing as the Debian Package Manager. It does the same thing. It's just a different software. It works a little bit differently, but the idea is to do the same, to replace the need for tarballs, compiling and installing tarballs. And here you can see a list of options when using the RPM Package Manager. So similar to dpkg, you're going to use RPM, and then you have a set of options. In case you want to install RPM space -I, basically you only need -I age and the file name. But usually you use IV age because you want that installation to be verbose. You want to see the installation process, follow the installation process. And then the RPM file. RPM files have the .rpm extension. Now, once again, same thing. You have to go online, find that .rpm file, download that file, and then you install it. And then you have, similarly to the dpkg, you have options to install, to update, to remove, to list the ones that you have available, to see the package that contains a file, or to see the files that are contained in a package. So you have the same options here. Now, we are focusing on the Ubuntu distribution, but the CompTIA Linux Plus exam requires you to know not only the Debian Package Manager, but the Red Hat Package Manager as well. So you have to at least know the main options, the main commands when using RPM. Now, these two package managers, they are a lot better than using a tarball. However, they still require you to go online and find the, let's say, .deb or .rpm file or package. And if there is a dependency, you have to go online, find those dependencies, find those .debs or .rpm files as well. In order to overcome that challenge, overcome that problem, right after Red Hat created the RPM, Debian came up with the APT, which is the Advanced Package Manager. And the Advanced Package Manager has two main characteristics. It still uses the DPKG Package Manager, but now it's let's say, an online Debian Package Manager. Now, pay attention to this. You still need the DPKG Package Manager. Actually, the APT uses the DPKG Package Manager. It's not a replacement for the DPKG. You still use DPKG, but now the difference is you have another tool running on top of DPKG where you can use this tool to only say, this is the software, this is the tool that I want to install. It will go online, find that package, find those .deb packages that you need, download those .deb files, and then invoke the DPKG tool to install that package. So basically, it's cutting short not only one, but two steps. The first one is it's going online and downloading that .deb package that you had to manually download. The second one is, in case there is a dependency, this tool will also find what those dependencies are, go online, download those dependencies, and then install the dependencies first, and then install the actual software that you want to install. So, just to give you an example, let's say that you want to install the Apache Web Server. And let's say that the Apache Web Server the package is called HTTPD. It depends on the distribution, but let's just assume that this is the package that we're looking for. So if you were using the DPKG software, you'd have to go online, download the httpd.version.deb file. You download it, manually download it, then you do dpkg-i space httpd-version.deb. You'd have to specify the file name. Now, let's say that there is a dependency. This package depends on, for example, a set of libraries, a set of APIs. Well, it would show you, okay, this package depends on glibc-devil, for example. Okay, now you have to go online, find where to download the glibc-devil.version.deb. Well, let's say that there is more than one dependency. Then you'd have to stay in this going back and forth. You go there, download, you try to install it. There is another dependency. You go there, download, try to install. So it is very time consuming. With APT, you would just say apt-get or apt-install. You can use either apt-get space install or apt-install and the package name. For example, apt-get space install httpd. What is that going to do? It's going to go online, download that file. Is there a dependency? Yes, there is. It would go online and install all the dependencies, install those dependencies, and then install this one. So, just one basic command, you just have to sit down and wait a few seconds so that the entire tool is there, ready for you, all configured, with all users, everything done. You can just start using it. So that is the APT. Then, and this was in 1998. Then in 2000, Red Hat did the same, just as they did after the DPKG package manager was created. They came a few years later and created the RPM. 98, Debian created the APT. In 2000, Red Hat created the YUM. Same thing, the same way that you use APT, you're going to use YUM.
with some different options or parameters, but it does just the same. So here is a yum command cheat sheet that's been created by Red Hat. And both of these cheat sheet here, both of these cheat sheets here will be made available for you because they are free, they are online, they are public, so you can take a look at them and see so many options that you have available. For example, you can do yum install vs ftpd in case you want to install the vs tpd FTP server. In case you want to verify if there are new updates to the packages that you have installed in your machine, you can do yum update and it's going to update the packages that you have. If you want to update a specific package, you can do yum update and that package name. So that is how you can use package managers in the at least use the most known, the most famous package managers that are available. There are many others. These four are not by any means the only options that you have available. There are many options, but these ones are the ones that are widely adopted. Because most distributions, they are either Debian based or Red Hat based. The ones that are Debian based, they use dpkg, and on top of dpkg as the online package manager, they use apt. If it's a Red Hat based distribution, let's say CentOS, Fedora, then they use RPM, and as an online package manager, they use yum. So I hope you enjoyed this class. In our next video, we're actually going to see in practice how to use those tools. Thank you very much. Hello, welcome to Module 12, and our topic here is going to be networking in the Linux operating system. And before we actually see the tools and resources that we have available in the Linux system regarding networking, we have to at least briefly review how addressing and routing works in this system. Well, actually, regarding the protocol, and then we'll focus on the Linux operating system itself. So our first goal, and this is our topic in this lecture, is going to be the Internet Protocol. So you may remember that when it comes to networking or network communication, there are several different protocols, and actually several different protocols within a stack of protocols. But our focus is going to be the TCP/IP stack, mainly on one specific protocol, which is the Internet Protocol. Reason being, this is the protocol that is adopted by the Internet, and that's the protocol that is adopted by most of the networks, whether they are local area networks, whether they are wireless networks, or even wide area networks. So we have to make sure that we understand the Internet Protocol, because basically this is the addressing and routing protocol used by most locations, most networks. So the Internet Protocol is the protocol adopted by the Internet to do addressing and routing, which means that this is the protocol used to allow different devices, network devices, to communicate among themselves. And since we have so many different networks, these networks can be connected. So different networks can be connected by actually in different ways, but the standard most commonly is to see routers. And again, there are routers for different protocols, but most of the routers that we have are IP-based routers. That's why we have to understand this type of addressing. Okay, so the Internet Protocol it has two main versions: IPv4, IP version 4, and IP version 6. Our focus is going to be on IPv4 for a very simple reason. Although the IPv6 protocol has been around for a few years now, it's been adopted especially by core networks. But it's still not common to see the IPv6 protocol on regular networks, let's say local area networks or any type of last mile networks. So the IPv4 protocol is a protocol that allows you to use over 4 billion different addresses. And that is why this protocol has been created, because every device does have a physical address. For example, if you're considering a Ethernet network, you do have what is called the MAC address, which is a physical address of each Ethernet interface or device network. However, the physical numbering of a network device can only be used for local addressing, which means that you can have inside the same local area network, you can have different devices with different MAC addresses. However, in order to interconnect different local area networks or different networks, then you have to go to the next layer, which is layer 3 or the internet layer. So to be able to allow people to actually interconnect different local area networks or different networks, another protocol had to be instantiated in the internet layer. So that's why the IP protocol was created, and it allows you to logically define an address to a network device. So when they designed the IPv4, they created the way that you could address or define an address to a device was based on octets, a sequence of bits, actually 32 bits, represented in 4 octets. Each octet is a set, an array of 8 bits. That's why it's called octet. And then since you have 32 bits divided in octets, you have 4 different octets. Considering that it's 32 bits, that means that you have a base 2 to power to 32, then you have a possibility of over 4 billion different addresses. That means that you could have over 4 different IP addresses spread around the world. Each octet, you have 8 bits, 2 base 2 powered to 8, it gives you 256 different possibilities. And that's how a IP address is represented. So you have 4 octets. Those octets can be converted to decimals, just to make your administration as a network admin easier. It's a lot easier to work with decimals than working with bits. Now, how does the Internet Protocol work in regards to routing? Just a very simplistic representation. We have this video here, not this video, but this image here, where let's say that you want to send a message to someone, you want to send a letter to someone. Well, let's say that you want to deliver a letter to your neighbor. Well, if it's our neighbor, you can just go there by yourself and deliver it to that neighbor, right? Because that destination is within the same area that you are, so you know how to get there. Now, it's a little bit different if you have to send that letter to someone that you know, but you just don't know how to make that letter get there. Or you might know how to make it get there, you just can't go there and deliver it yourself. Well, how do we do that? How do we send that letter? Simple, very simple. We contact the mail service. For example, in the US, you can deliver that letter to the USPS, so to the United States Postal Service, give it to them, and they will do whatever has to be done in order to make that letter reach the destination. So this is how communication works in the internet, and actually in all types of network. So you have a source. That source has a destination, wants to deliver a package and information, data to the destination. If the destination resides within the same network, well, you can do it yourself. But if it's residing within a different network, then what you're going to do is your device will send that data, that package, to the default router or a specific router, and we're going to discuss that more. But you have to send it to a router, which is another device, a layer 3 device, that will know how to make that package reach the destination. Now, we're representing this communication between source and destination using only one single router. But that's not how it may work. There is a very high probability, of course, it depends on many different factors, but there is a probability that we're going to have several different routers between source and destination. So what you as a source will do is you deliver that letter to your router. That router will analyze, it will ask this question: can I make that letter reach the destination or package reach the destination by myself? Yes, I can. The router delivers it. No, I can't. The router will send it to the next router, which will then deliver it to the next router until that package reaches a router that actually knows that destination and delivers it. Now, I mentioned that the IP address is actually represented in 32 bits, and it's divided in 4 octets, each octet being a sequence of 8 bits. So let's take a look at how we can represent that type of information. So here we have 1, 2, 3, 4, 5, 6, 7, 8 octets. 8 bits. The first bit, and let's keep in mind that this is base 2. So going from the right to the left to the less significant to the most significant bit, we have the power. It's base 2, but since this is the first and the numeration, the power starts in 0. So base 2 powered by 0 equals 1. Then base 2 powered by 2 equals 2. Base 2 powered by 2 equals powered by 3. Base 2 powered by 1 equals 2. Base 2 powered by 2 equals 4. Base 2 powered by 3 equals 8. So here we have the power. Power 0, power 1, power 2, power 3, power 4, power 5, power 6, power 7. So and then we have the representation of that bit in decimals. So a bit that goes here will represent in decimals, decimal 1. Here, number 2. Here, number 4. Here, number 8, 16, 32, 64, 128. Now, it's important to understand that because, for example, we see so many different IP addresses, and this is a very common one because this is what is called a reserved IP address or also a private IP address. Now, why do we use these type of IP addresses? For example, one decimal here, another decimal here, another decimal here, and another decimal value here. What are these or this decimal value here representing? Well, we have to understand the value of each position to combine these values and represent that decimal there. What it means is that actually 192 is the combination of 128 plus 64. That means that I have to have these, I am actually setting these 2 bits here at 1. 128, 1, 64, also 1. That means I'm going to sum these two values, which will equal 192. So this is the binary representation that will give me this decimal representation here. The next one that I have is 168. Well, that's because I'm setting 128 plus 32 plus 8. If we sum that up, we're going to have 168. Then we have 1 right here. Well, that's just the first bit right there. And 10, out of the possible values here, 10 is the combination of 8 right here plus 2 right here. That means that from the right to the left, I have to set the second bit right here and the fourth bit right here in 1. There it is. So this is the binary representation of the decimal 10. And this may be a little bit confusing so far, but the reason why we do that is because that is what is used in order to define networks. Which network do my IP address or which network do my device belongs to? Because we have a separation of networks. We have different networks, or we can also have subnetworks. For example, if I go back here, and if I have this IP address right here, 192.168.1.10, and if I ask, okay, tell me an IP address that falls within the same local area network, for example, the same network. You could say 192.168.1.50, for example. Well, that's because you know that by default, if you have IP addresses beginning with 192, which is, back in the day, it would be classified as a Class C network, that would mean that you only have a different IP address or a host address when you change the very last octet. If you change any bit within the first 3 octets, then you'd be changing the network. But that was back in the day when we did not have what is called the mask or the subnet mask, or we didn't have the classless interdomain routing, the CIDR notation. So the CIDR notation was actually created in order to allow you to use another sequence of bits to define which bits would define a different network and which ones would define just another device within the same network. Okay, let's take a look at it. First of all, when we use the CIDR notation or the masks to define networks and IP addresses, we have to consider that bits within the mask address, not in the IP address mask, not in the IP address. Bits 1, they represent the network. Bits 0 represent the host. Okay, it's still very, very confusing. So let's take a look at how this actually works. Again, we're using the same IP address here, 192.168.1.10. In binary, that's the representation right there. 1, 1, then a set of zeros. Then in the second octet, you have 1, 0, 1, 0, 1, 0, 0, 0. In the third octet, you're going to have a sequence of zeros and just the last bit, 1. In the last octet, you're going to have 0, 0, 0, 0, 1, 0, 1, 0. Now, the mask. According to a traditional Class C, you'd have this mask.
255.255.255.0, and that's how you represent this mask, this decimal mask here, as a binary mask. Now, according to what we just saw, bits 1 represent network, bits 0 represent node or host. What it tells us is that when we perform the AND operation, the logical AND, between the IP address right here and the mask address right here, the resulting address will determine the network that node belongs to. So, if I have this IP address here, which is represented in an array of bits right here, if I perform an AND operation between this IP address and let's say that I define this mask here, what I'm going to do is perform AND between 1 and 1. Well, it's 1. 1 and 1. It's also 1. 0 and 1. And between 0 and, it doesn't matter what the other values are, if it's a 0, the result is going to be 0. So 0 here, 0 here, 0 here, 0 all the way. I don't even have to look at these other bits down here, because if I have zeros here, the result is going to be a sequence of zeros. Okay, so the AND between the first octet, the IP octet, and the first mask octet is going to be this sequence here. We do the same thing for the other octets. 1 and 1, 1, 0, it goes 0, 1 and 1, it's going to be 1, 0, it's going to be 0, 1 and 1, 1, and then a sequence of zeros. We do the same thing here. And now, this is the most important part. Same thing, 0 and 0, 0, 0 and 0, 0, 0 and 0, 0, 0 and 0, 0. 1 and 0, 0, 0, 0, 1 and 0, 0. Observe that this last octet here is different from this last octet here. Now, what is important is the bits that are in the mask represented by 0 are actually representing the host, bits for host. So when I perform the AND between this IP here and this mask, it tells me that this node 192.168.1.10 belongs to network 192.168.1.0. It also tells me that all IP addresses that fall within this network will communicate with that IP address right there. So for example, earlier I mentioned another IP address, 192.168.1.50. Well, the only thing that is changing is in the last octet right here. And 50 is going to be 32. So it's going to be this one, 32 plus 16. That is going to, and then, so 32 plus 16, that's going to be 48, and then this one, it's going to be 50. But what is happening is, I am changing only bits that are used to define different host, not different network. If I perform the AND between 50 here and a sequence of 0, the resulting network is also going to be the same network 192.168.1.0. That is what makes us have those two IP addresses in the same network. And what that means is that those two nodes with those IP addresses, .10 and .50, they do not need a router in order to communicate between themselves. So when 192.168.1.10 wants to send a packet to 192.168.1.50, that source will deliver it to the destination by itself. It won't need a router. Now, it's different. For example, if I have 192.168.1.10, the same one that we were using, now willing to deliver to 192.168.1.130. Well, if we had that same previous mask with the last octet here being 0, then yes, the resulting network would be 192.168.1.0. But that's not the case. Now I'm saying that this other machine here has IP address 192.168.1.130, okay, but the mask is 255.255.255.128. What does that tell me? When I convert this to bits, I can see that I still have one bit here that represents network, not host. When I perform the AND between the IP address and the mask, this is the resulting network. That means that the IP address 192.168.1.10 belongs to the network 192.168.1.0. And this IP address here, 192.168.1.130, belongs to 192.168.1.128, which is a different network. So this is how IP addressing and routing actually work. When you have two or more devices trying to communicate among themselves, if they fall within the same network, they directly deliver data to each other. If they are in different networks, then we need a router. And we are going to see how the Linux operating system actually allows you to control that, how you can define IP addresses, how you can define masks, how you can define networks, and also how you can define routers. We're even going to see how to configure a Linux machine to work as a router. That is one other very good advantage of the Linux operating system. You can use it to work as a router, and it's not difficult at all to make that kind of configuration. So these are some concepts that we need in order to proceed in working in the Linux environment, especially focusing on networking. I hope you enjoyed this class. Thank you very much. Hello, welcome to Module 13, and our focus in this module is going to be Linux security. How to secure a Linux system. And there are a few tools or systems that we are going to analyze during this class. The first of them is going to be sudo. Then we'll take a look at the Pluggable Authentication Modules subsystem, or PAM, followed by the inetd and xinetd and app armor. This is actually one is the evolution of the others. Then we're going to look at the SSH protocol, focusing obviously using a tool to implement that protocol. So we're going to take a look at the OpenSSH server, which is the implementation of the SSH protocol in the Linux system, along with the SSH command line tool, which is the SSH client. And lastly, we'll take a look at IP tables. So let's start with sudo. And by now, we already know how to use sudo. It's actually a very simple tool, very straightforward, very friendly. We used it several times. Actually, we use it almost all the time. Whenever we have a administration tool or command that we have to invoke, since we are using, as you can see here, a regular user, and we can actually identify that by the user ID, it's above 999. That means it's a regular user. Regular users cannot run administrative tools, but I can do that if I precede a command with sudo. For example, if I try to list
the content of the /root directory, which is not permitted, as we can see. But if I precede this command with the sudo command, then I have to inform my password. There it is. Okay, so now I can. That's because actually my user, my regular user, Linux, invoked that command. But then the sudo tool, because that's what I said, I want to run this command here, pass this command actually as a parameter for the sudo tool. So what I'm doing is my regular user is actually invoking sudo. Sudo will see, okay, can this user here, Linux, invoke this command? And if it can, whom is he going to run it? As whom is it going to run it? So, well, to run ls/root, you have to be the root user. This means that the Linux user will only be able to run ls/root if this user here is configured in the sudo tool as a user allowed to run commands as root. So how can we verify that? Okay, the simplest way is there. When you have the sudo tool in your system, in your Linux system, it will create a group called sudo. Every user that belongs to the sudo group will be allowed to run any command in the system as root. So this means that if there is another user, not just the one that you created during the installation process, but let's say that you create another user, so you use user add or add user tool to create a new user. And now you want to allow that user to, well, basically you want to make it a administrative user as well. Well, you can simply add that other user to the sudo group as well. But users that belong to the sudo group will be allowed to run any command as root. What if I want to configure, for example, a few commands, a few tools? I want to allow that new user to run only these specific commands. Then you have two options. One is editing the /etc/sudoers file, but that's not recommended. And the other one is running the vsudo command. This is recommended. It will open the /etc/sudoers file. And the way this file is configured, or the way that you can configure sudo is, you have four options, four columns here. You can configure a user and a command or a set of commands per line. For example, this first line here, I am saying that the root user from any machine, all machines, it doesn't matter which host name he's using, can run as any user, all users, any command, all commands. Well, that's pretty obvious, right? The root user is supposed to run everything. But now if we scroll down, we can see here that we have the percentage sign, which stands for a group name, not a username. So there is a group called admin, and users that belong to the admin group will also, from any machine, be allowed to run all commands. And once again, for the sudo group, users that belong to the sudo group, which is that configuration that we just saw, if I add a user to the sudo group, same thing. It will be allowed to run all commands. But let's take a look at this configuration that I added here. Here I'm saying that this specific user, Linux. So you can specify user or group. If it's a group, I have to precede the group name with percentage. Can, from any machine, as any user, run. Now I'm saying that the Linux user can run /usr/bin/passwd space anything, asterisk, that means anything. But I'm associating this user with this specific command.
That's not really the case because my Linux user actually belongs to the sudo group, which means that this user will be allowed to run anything. But if I use another user here, for example, Ubuntu, if I create my Ubuntu user and I do this, I'm saying that the Ubuntu user will only be able to run /usr/bin/passwd. Let me give you an example of when you'd use that. Let's say that in your company you have an intern, and that intern is supposed to run the backup scripts every day. Well, to run a backup script, you must have some level of permission. Let's say that to run this specific backup script, you have to be the root user because it's going to copy files that only the root user has access to. Obviously, you're not going to give the intern the root password. What can you do? You say that his user, which is a regular user, will be allowed to invoke, and then you have the path to the script, to the backup script here. That intern will be able to invoke the script as the root user, but he's not logging as root. Then, as you can see down below, right here, you hit Ctrl X to exit, and it's going to ask you, do you want to save these changes? Why? Okay, this is the file name. Yes, I'll just hit enter. And done. It's configured. So that's how you can use sudo in a more advanced way. Now, another very useful and important resource that we have in regards to security in the Linux system is the pluggable authentication modules. It's called a subsystem because it's such a powerful tool that controls or can control steps of several different other softwares. For example, if when I start my machine, my Linux machine, if it's configured to boot into the graphical interface, I will face a login software, a login interface, a login screen. That login screen is the authentication screen for the GDM. GDM is the GNOME Desktop Manager. That is the graphical interface that comes in most of the Linux distributions. So if you want to use the graphical interface, probably you're going to face GNOME or KDE. Well, so that varies, but those are the major ones, and which is not important right now. But what matters is you're facing a screen that is the authentication system of a specific tool, or it's the authentication tool itself. Now, that authentication tool is just the interface. It will just ask for your username and password. It's not the tool that is actually taking care of the authentication process. The authentication process is taken care by the pluggable authentication modules subsystem. In a Linux world, PAM takes care of sessions, different steps of many softwares, not all of them, but most of them. So what I mean is, if we take a look at the /etc/pam.d directory, we can see some files here. This is how PAM is going to take care of the authentication process, authorization process, and session opening process for these tools. AT, which is the scheduler. For example, change password, although it's not very much used, usually you use passwd. You also have cron, you have cups, which is the printing system. And let's take a look at for example, the GDM auto login. So the GDM auto login is the system that will take care of how a user can authenticate and check if that user is actually authorized to open a GDM session. So PAM is the software that is taking care of how a user can log in my system, into my system.
It's also because there is a difference between authentication and authorization. Authentication is simply the step where you are informing your username and password. PAM, that system, in this case, that tool, for example, GDM auto login, will simply receive those credentials and pass it over, hand it over to PAM. PAM will simply, at first, verify if that login and password are correct. If it is correct, then it's past the authentication phase, moves forward to the next phase, which is authorization. So the authorization module will verify if that user is actually authorized to use that system. Because I can have, for example, I have 20 users in my system. They're all valid, but I just want 2 or 3 being able to actually open my graphical interface, using my graphical interface. Well, you have 20 users that will be able to authenticate, but only 2 or 3 users that will be authorized to use that system. And then I have the session opening, which controls, that's the PAM module that will control how that session will be made available. For example, do you want that user to be able to have access to some specific features when opening that session? Do you want to allow that user to use the browser when opening a new session? Do you want to create environment variables when that user opens a new session? When a user opens a new session, how long can that user remain inactive before being forcibly logged out? So it's all session related, and PAM can control that. So PAM has several modules, several different APIs, libraries that will allow you to control a bunch of stuff. Now, additionally to those 3 different phases, you also have PAM modules to control password change. So let's say that a user wants to change its password. If you want to define, for example, that a password must be at least 16 characters long, among those 16, there must be at least 1 capital letter, 1 lowercase, at least 1 number, at least 1 symbol. You have the PAM modules to control that. So for example, if I added the /etc/pam.d/passwd, which is the command that we use to change a user password, we can see that it is actually invoking the common password file. So let's take a look at the common password. So we can see here, let's find this line here, for example. When a user tries to change the password, the PAM Unix module will be invoked. You can configure more than 1 module for the same phase. In this case, when a user tries to change the password, not just PAM Unix module will be invoked, but also PAM deny and also PAM permit. Oh, and there is another one down here, PAM GNOME keyring. So you have different modules because each module has a specific capability, has a specific set of possible configurations. If there is one configuration, one setting that you want or you need and is not available, for example, in the PAM Unix module, well, we'll have to find the module that actually deploys that feature that you're looking for. And then you add another line invoking that module. Now, clearly, you have specific configurations for specific modules. You have to search for the documentation to know how to configure the module or the modules that you want. And you can always refer to the kernel.org website, which is the official Linux kernel website, and the PAM modules are described there, at least most of them, the official ones. Now, PAM is a very useful resource, but there are some features that cannot be controlled by PAM, because PAM can control authorization, authentication, session, and password changing, but it cannot control how a service or software will run. For that, we have other solutions. The first one, let's say the ancient one, the first network service controller that we had was the Inetd, and it's not available anymore, at least not by default. There. But if you want to install it, you can. And it's this one right here. Now, all these tools, whether it's the inet, Xinetd, or AppArmor, what they do is they will allow you to set up different features regarding network services. For example, let's say that you have not Telnet because it's very old, but let's say that you have SSH running, a SSH server running in your machine, or you have a web server such as the Apache HTTPD software running in your machine. There's a bunch of different configurations for security reasons that you may want to establish. For example, when I have my Apache HTTPD web server running, I only want to allow up to 50 users simultaneously. I only want to allow clients establishing connection from this range of IP addresses. I only want to allow 5 concurrent connections actually transmitting. So there is a bunch of security and performance features that can be established. Now, if that software allows you to implement those security that you're looking for, that's great. But you cannot be certain that all softwares that you use will actually allow you to establish those features or those policies. Because of that, you have a centralized network service controller, which once again can be INET, very ancient, very old, very limited. Then it evolved to Xinetd, right here. And as the description itself says, replacement for Inetd with many enhancements. And then we have another tool that is the improvement of Xinetd, but focusing even more on security, not so much on how to manage the services, how to control how the services are running in your machine, but more security related, which is the AppArmor. Right there. And in modern Linux distributions, you can have 2 default network service controllers. You can have the AppArmor, or you can have the SE Linux, Security Enhanced Linux. Most distributions nowadays are using AppArmor, although there are some that are using SE Linux. The default in Ubuntu 18.04 is AppArmor. Now, if we look at /etc/apparmor.d, we can see the configuration files for different services. For example, we may remember from our last module that we checked for the DH client process. We wanted to know if our network was configured to automatically and dynamically receive network configuration, such as IP address, DNS server, router, or if we had to manually configure those network information. And we saw that DH client was actually running.
The app armor is actually controlling the H client. And other services that you may install, you may run, are also being controlled by app armor. For example, TCP dump, cups. As you install additional services, additional network softwares, you will see additional files here in the etc/apparmor.d directory. Now, another very useful tool that we have, actually it's a protocol, Secure Shell, SSH. And it's not installed by default. There it is. We can see that it says none, so it's not installed. First, let's understand what the SSH is. SSH is simply a secure shell, a protocol that will allow you to perform remote access to a SSH-enabled machine, which means that you have the client SSH and you have the SSH server. So you have the SSH client, the SSH server. The server must be the machine that you're willing to access. So let's say that you want to get access to a SSH, to a Linux machine. You have to make sure that machine has the OpenSSH-server package installed. Now, if you are the client, you can see here that by default, it comes with the SSH client. What it's going to do is you'll be able to establish a remote connection from your machine. You'll be able to get access to the console, so the command line interface, and also the graphical interface if you want to. So we have to keep in mind that SSH is not only, although most of the times that's how it's used, but it's not only used to get access to the command line interface. You can also perform remote access to the graphical interface. Now, what is the difference between SSH and, for example, Telnet, which is a very old protocol also used for remote access? The difference is that Telnet does not implement cryptography. SSH does. So that is why whenever we talk about security in Linux, we have to consider SSH, because it allows you to remotely access a machine. For example, from your home, you have to access the company server to do something. For example, once again, issue the backup script, run the backup script. So you have to get access to that machine and start that script, run that script. But if you're using Telnet, all commands, every key that you hit will be transmitted through the internet or through the LAN, whatever you're using to get access to that machine, in clear text. Obviously, that's not what you want. You want that communication to be ciphered. SSH does that. So the simplest way to run SSH is SSH and then the IP address of that server. For example, I want to access this machine. Well, I can't. The port used by SSH, port 22. Why can't I? Well, I don't have the OpenSSH server package installed. Okay, so let me install it. There it is. Now, what if I try to SSH my machine? Oh, so now let's take a look at what's going on here. The authenticity of host, and then there is the IP address, can't be established. So it's not that port 22 is closed. It's just saying, okay, the key fingerprint is, and then there is the fingerprint. There is a signature that uniquely identified that machine that I'm trying to access. So basically what it's saying is, okay, this fingerprint here is not recognized, which means you are accessing this
SSH server, which has this fingerprint. But this is a new fingerprint. I cannot verify the authenticity of this fingerprint. Do you still want to continue? Do you want to add this fingerprint to our fingerprints database and make it a reliable server? Basically, it's warning you, saying something like, you are trying to access a server, but I cannot actually confirm that is the server you're willing to access. You may be suffering a man-in-the-middle attack, for example. But let's say that you do know that, okay, this is the server that I'm trying to access. I just don't have that server's fingerprint yet because it's the first time I'm accessing it. So if you want to continue, you answer yes. It's going to ask for the user password. And there, you're connected. I am going to disconnect, exit, and I will try to establish that connection again. Now, it's not saying that the fingerprint is not recognized anymore. It is. It's in my database. And then I pass the password. I inform the password. If it matches, then there it is. I'm connected. Now, let me disconnect. Okay. When I do SSH space the IP address, yes, I am in this machine, and I am actually trying to establish a connection to the very same machine. Yes, that is correct, but it's just for display purpose. Basically, if you're trying to access another machine, you'd just inform that other IP address. So it doesn't matter if I'm using my own IP address. I'm still using the SSH protocol to remotely connect to my own machine, to the same machine. But it's through the network, via network, port 22 SSH connection. Now, there are a bunch of other features that I can use here. First of all, let's say that I'm trying to access a server, but I don't want to connect to that server via SSH using my current user, which is Linux. There is a very high probability that there is no such user in that server. I have my Linux user here in my machine, but I'm trying to access a SSH server that has other users. Well, in that case, you'd have to inform that other user at that IP address. Let's try. So now I have to inform the root password because that's the user that I'm trying to log in. But no, I can't. Although the password is correct. Let me just make sure. Let me cancel this. So let me redefine the root user password. And let me try once again. Nope, I still can't. Why? SSH has a configurations file. And that is where you configure how your SSH server is going to operate, how your SSH server will accept connections or not. And there is a bunch of different parameters that we can configure here. For example, in case I want to change the port my SSH server will listen to, you have to uncomment this line and change this port number. In case, let's say that you have two different interfaces, network interfaces, you just want your SSH to listen to one interface. You uncomment this and you inform the IP address of that interface right here. And there is a bunch of other possible configurations here. Here, permit root login. If you want to allow root users, clients to connect using the root user, then you have to uncomment this line and change it to yes. However, you're not supposed to accept that. You're not supposed to allow that. There are two different proper ways of allowing SSH clients. One is
that guy will have to use a regular user. For example, I'm logging in as a regular user Linux. And now that I got access to that machine, remote access to that machine with the regular user, then I can either invoke administrative tools using sudo, or I use the su command to become root. So if you have the root user password, then you can do su space dash. It's going to ask for that user password. And now I am root. That is one. Another one is configure the pair of keys. So you can do SSH keygen -t RSA or DSA. It doesn't matter which standard algorithm, cryptography algorithm you want to use. Nowadays, RSA is the default. You hit enter. It's going to say, okay, do you want to generate, can we use this file here to hold your private key? If you don't want this file name here, and you can see that it's in a hidden directory, .ssh, dot means it's hidden, and the private key is going to be stored in that file. I'm going to cancel this. Then it will generate that private key along with the public key. So if I take a look at my /home/linux/ssh directory, it's empty. So let me create it. Yes, define a password for your private key. Okay, I defined that password. And now it generated the private key and the public key. There it is. Private key and public key. Now, what do I have to do in order to be able to remotely access using SSH and using my pair of keys and not a user password? The private key is yours. Now, this is where it may get a little bit confusing. Since we're trying to remotely access a server, you may think that you have to copy the private key to the server because it's a server. Servers have private keys. That is not the case. You have to keep your private key with you. It's a private key and it's yours, so it should not go anywhere else. The public key is the one that you have to copy to that server. Once you copy this file, the public key, to that server, then you have to copy that file to a file called authorized keys. So I would have to copy this file to the SSH server, then I access that server and I copy that file to, I do a cat. Okay, so let's say that I copied via network, I copied my id rsa.pub file to my user's home directory. Now I have to do a cat and redirect it to, the /home/linux/.ssh/authorized keys, like that. Now I have my own private key, I have my public key, and I copied my public key to the server that I want to access. I get access to that server, and I copied my public key to the authorized keys file. Let's say that I need to access 5 different servers. You're going to copy the same public key to those 5 different servers and copy the content of that file, public key, to the authorized keys files of all those 5 servers. Now, one question that is very common is, okay, I generated my private key here and I have my public key here in my local machine. and I need to copy the public key to that remote server. Well, I can't use CP because CP copies a file from one directory to another directory in my own machine. It's a local copy. If I want to perform a remote copy, then I can use SCP. SCP is the CP command, but performing it via network and using SSH protocol, which means that you're copying a file through the network, and that copy is done using cryptography. The way it works is SCP, the source, in this case where the file is and the file name. So it's in my home linux.ssh. What is the file name again? ID rsa.pub. I want to copy this file to the server 10.0.2.15. Now, to copy this file, I want to use my Linux user. And where is this file gonna go? I want it to go to /home/Linux. Now, it is actually asking me for my private key passphrase because I created my private key, and also that server already has my public key. But if that's not the case, it will just ask for your user password. It would copy the file, then you would access that server, copy the public key to the authorized keys file, and then you'd start using your private key. Okay, and lastly, we have to take a look at the IP tables, which by default comes in most Linux distributions. IP tables is simply a tool that will work on the layer 3, which means that it's analyzing all packets, network packets, or datagrams, as you want to call it. All network packets that is arriving to your network interface or leaving your network interface or passing through your network interfaces. So for example, let's say that someone is trying to establish a SSH connection to your machine. Well, then you have packets coming in because that remote node, that remote machine, is sending packets to your machine. For example, just to try to establish a connection. Just trying to establish a connection means there are packets coming in. Now, in order to accept or not that connection, you have to at least send a response to that client or possible client, which means that you are sending packets. So input, output. But there is also the forward chain. It's called chain. Forward chain is when your machine is working as a router or gateway, which means that packets are coming in and those packets do not have your own machine as the final destination. Your machine is being used as a gateway or router, so your machine has to receive those packets and then forward them to the destination. So let's say that you have two different networks, network A, network B. And this machine right here is the router or the gateway used to connect those two different networks. If a client from network A needs to send a packet to a client from network B, it will actually need to send that packet to this machine that we see here that is working as the router. This machine will receive that packet, forward from one interface, forward that packet through the other interface that is connected to network B. So, if we take a look, if we use IP tables with the -L option, we're going to see all the rules that we have. In this case, we have none associated with the filter chains. We can see here three chains: input, output, forward. Input chain. The rules that you associate with the input chain will be rules applied to packets that have your machine, in this case, this machine, as the final destination. Packets that are sent to my machine. Now, rules that you associate with the output chain will treat packets that are being generated by this machine and being sent out. My machine is the source. Packets that are arriving to my machine but does not have my machine as the final destination, and my machine will just have to forward those packets, will be treated by the forward chain, which means that the rules that are associated with the forward chain will be applied to those packets. Now, what are these rules? The rules are nothing more than a pattern that you create trying to match specific required packets. For example, once again, SSH. I have my SSH server running here right now, right? Let me install the Nmap tool. This is another very important and resourceful tool. It allows you to scan ports, verify which, well, actually it allows you to do a bunch of stuff, but mostly its most important feature is showing open ports. So let me Nmap, let me port scan my own machine, which is this one. Okay, I can see that I have a web server running, port 80, and I also have port 22 running, open. That's my SSH server. Okay, since I do not have any rules in my input chain and my policy is accept, which means that, well, if there is no rule matching a specific packet, the default policy will be applied, which is accept. So, well, I don't have any rules in my input chain, which means that all packets that are sent to my machine will be accepted, at least in regards to my firewall. That's what iptables is. It's a firewall. It's filtering packets. Okay, so that means that anybody from any location, any machine can try to connect to my SSH server. Now, just make it clear, the authentication and authorization process is taken care by the OpenSSH server package itself, which is actually using PAM. So it doesn't have anything to do with iptables. Authentication, authorization goes up there in the application layer. iptables works on the network layer. So if someone tries to SSH my machine, that person will be able to do so. There. Let me exit. What if I create a rule? So I am going to create a rule. This rule, I want to add that rule to my input chain because I want to add a rule that will treat packets being sent to my machine as a final destination. And I want to treat packets that are going to port 22. And I want to make sure that if that source is 10.0.2.15, this should be dropped. Okay, so let's take a look at it again. I want to add a rule to my input chain, which treats packets that are sent to my machine, coming from this IP address and having port 22 as the destination, which is the SSH port, should be dropped, which means that guy cannot get a connection. Let me list my IP tables rules once again. Okay, so now, there, I have that rule. Let me try to connect once again. Nope, doesn't work. So I have this new rule that blocks me from doing that. Any other IP address. So let's say that I try to do the same, but using my loopback IP address. Yes, it works. There it is. Let me go back. So I blocked this IP address right here, but I did not block this one. So then I was able to. Okay, if I do the same rule now to blocking 127.0.0.1 and I try to do it again, no, I can't. Now, there is a bunch of different combinations that you can apply with IP tables. You can specify source IP. You can specify source MAC address, destination IP, destination MAC address, source port, destination port. You can use protocols. You can block or accept based on content of a packet, but you have to use modules. And that is another very useful resource that we have in IP tables. It supports so many different modules. So if you need to, or if you're curious, search for IP tables modules. You're going to see so many different modules. Just to list a few examples, you have a module to specify a range of IP addresses. You have a module to specify the content of a packet. You have a module to specify MAC addresses. So many different modules. You have a module to specify the TCP flag header field. You have a module that will allow you to say, okay, if I have a packet that is associated with a previously established connection, I can just accept that packet because the connection associated with it has been established in the past, so that's okay. So many different modules. And just analyzing the policy here, the proper way to configure a firewall, Linux firewall using IP tables is to actually do the inverse. For the forward and the input chains, you don't have to do that for the output chain. But for the forward and input chains, you have to define the policy as drop and not accept. So use -P, the chain, which is, for example, input, and then the default policy. Oops. There. IP tables -P, the chain name, it's case sensitive, it's case sensitive. Now we can see here that my policy is drop. Well, which is actually, right now, my machine cannot do anything. Why? Because it's dropping everything that comes to my machine. For example, if I try to browse, well, when I'm trying to browse, I'm sending a request, so it's using the output chain, but that server, once receiving my request, will reply to my request. That reply will fall within my input chain, and my input chain is dropping everything. Why everything? Because I only have two rules here, and both rules are drop, which means that they're useless. And they're associated with the SSH protocol. So IP tables is receiving a packet sent by a server, and that source port is port 80. That's the web server port. So there is a packet coming from port 80. It's looking for a matching rule here, a rule that matches that packet. No, this one doesn't match. This one doesn't match. There's no more rules in my input chain. What does it do? It will implement the adopt the drop policy. So, what is the proper way to do it? You define the policy as drop, and then you add accept rules according to what you want to accept. For example, I want to add a new rule to my input chain. Packets that are TCP packets coming from source port, source port 80. That's how web servers reply. You send a request to their port 80. They will use port 80 to send that reply. So when that packet comes back to my machine, that packet has port 80 as the source port. And now I accept it. Okay. Well, it's not very helpful yet because I just have this rule, accepting whatever comes from port 80, but it's still not very helpful because my machine has to use the DNS protocol, so many other types of packets that I have to allow. But that is how you do it. And then you start adding rules according to the type of that packet that you want to allow. If your machine is a router, you have to add rules to the forward chain as well. Okay. Now, let's say that I already have all the rules that I need here. But the IP tables rules, they're loaded into the RAM. They're not saved by default, which means that you have to configure your system in order to load those rules when the system reboots. How can you do that? The easiest way, at least in my opinion, is you apply the rules. Once you have those rules, you do iptables-save, and then you send it to a file. Let's say just firewall. If I look at the firewall file, there it is. The rules are in there. They're not exactly as the commands. You don't see IP tables here. So there is a specific format. It's been generated by the IP table save tool. Okay, but it's just saving those rules in a file. What do you have to do? You have to make sure that once your system is booting, you run the IP tables restore with the last sign and the file. So to save the current rules in a file, IP table save. To load the rules that have been saved in a file, IP tables restore. And then you configure your system to load this file during the boot process. There are different ways of doing it. For example, you can configure the /etc/rc.local. You can create a script and configure systemd to load that script. There are different ways of doing it. So this is one way, using iptable save or using iptables restore. Another way is creating a script, and that's the subject of our next module. You create a script with all the commands that we use in our command line. You save those commands, iptables commands, in a file, save that file as a script, and configure that script to be executed every time your system is booted. So we saw here how to use several different security tools that we have available in a Linux system. We started by using sudo. Then we analyzed the pluggable authentication module, SPAM. And then we took a look at the evolution of the network services controllers, going from inetd then to xinetd. We looked at the APP armor And we also mentioned that App Armor has kind of a rival, which is the SE Linux. Then we saw different ways of using SSH and configuring a SSH server. And lastly, we took a very good look at the IP tables, which is the default Linux firewall. I hope you enjoyed this class. Thank you very much.
Hello, welcome to this class. And in this module, module 14, we're going to learn how to write bash scripts, or also called shell scripts. Now, the idea of writing a script is basically a way of automating your tasks, your daily tasks, which means that almost never you will just write a script because you need to write a script to run a command or just a set of commands or random commands. You're writing a script because you want to do something in a automated way. For example, let's say that you need to run backups on daily basis. If you just have to run one single command to execute that backup, then you can just schedule that command to be invoked by cron or AT or any scheduling tool. However, if you need more than one command to do that, you have to make sure that most of the times those commands, they will have to be run in a specific order, in a specific sequence. Sometimes one command should only be executed depending on the result of another one. So as you can see, you have a sequence of commands to be executed, but they're interdependent. So there is a condition there, which means that you have to have all those possibilities well thought, well considered, and you must put that inside the script, which is basically a sequence of commands, but that script also allow you to write those conditions. If needed, it will also allow you to write a loop. So let's say that you need to run a specific test for a period of time or for a number of times until you reach a specific condition. Once that condition is met, then that script is done. But obviously, before we actually start writing our automation scripts, we have to first learn how to write a script, how it works, and how to write it. So, I created here in my /home/my username /scripts, in my home directory, I created the scripts directory. The first script we're going to create, so I have a set of scripts here, and the first script we're going to create is script1.sh. Now, first of all, do shell scripts or bash scripts have to have the .sh extension? No, there is no such thing as extensions in the Linux operating system. However, it's a convention to include that extension into your script file so that when you or any other person sees that file, that person will know, oh, okay, so this is a shell script, this is a bash script. And what is a script in regards to the type of file, in regards to its content? A script, and it's any type of script, is just a text file. Once again, a text file with a sequence of commands that you use. Now, specifically talking about shell scripts, sequence of commands that you can use in your shell, in our command line interface. For example, the date command. I can just create a script, create an empty file, an empty text file, using, let's say, vi, pico, nano, mcedit, any text editor that you want to use. So you can create that new file and just write in there date. and then you have to run that tool. But let's see how it works. Okay, so what we're going to do first is create this script1.sh. Okay, now the first thing that we have to observe is in any type of script, the first line must come with the pound, exclamation point, and then the interpreter. That is the tool, that is the software that is going to be invoked in order to interpret this script. So, if you're writing a shell script, the first line here must be the pound, exclamation point, /bin/bash, because this is the path to the bash tool, which is the terminal, the tool that runs our terminal. That's the bash. Let's say that you're going to write a Perl script. Well, there you go. So you'd have to do pound, exclamation point, /usr/bin/perl. That should be the first line. Let's say that you're writing a Python script. Oh, I don't have Python installed here. But if I did, then that would be the path, which is also going to be /usr/bin/perl, /python. So that is the first line. The reason is, when you invoke a script, when you want to run it, you don't want to say, I want to use bash to run this script. You just want to say, I want to run this script. Now, how is the system going to know which interpreter, which software it's supposed to invoke in order to read that script? That's this line right here. Okay, and then you have the commands. For example, first I have here a echo, which is going to show the standard message when you're starting writing code, hello world. Then I'll have another command, date. And then I'll have another command, ls space tilt /, which represents my home directory. Okay, so I save this script. I'm not saving it here, but yeah, I have to save it. Now, if I try to run this script doing this, permission denied. Why? If we remember, what makes a file executable is the executable permission, which this file does not have. There, and there. So remember, every time that you write a script, once you save that file, you have to give executable permission to that file. Now, the way that you invoke the script is, well, if you are in the same directory that the script resides, you're going to use / and the script name. There. So, hello world, that's the result of the echo command. Then I have the date, and then I have the result of the ls, and we can confirm here. There you go. So that is a very simple script, a very simple way of writing a bash script. Now, there is a possibility that you write a script that will just have a sequence of commands. But, of course, we have so many other resources, and we have to take a look at those other resources. That is why you're going to write the script2.sh. Now, a very important resource that we have when writing scripts is the use of environment variables. So as we can see here, I am creating a variable called var. And if we remember, when we're creating an environment variable, we do not use the $sign before the variable name. We just use the variable name. In this case, it's var. So var receives hello world. And then I'm printing that variable's content. Now, to invoke the content of a variable, I use the $sign. I precede the variable name with the $sign. So we can see here that basically what I'm trying to do is to print two different information: the content of the variable and the content of the PWD variable. So let's see. I already have the permission of execution here, which means that I can simply try to run this script. There it is. So this is a very important resource, and you're going to see that we're going to use this the entire time. So let's move forward to our next script, which is script 3. And here in script 3, we can see some different types of variables that are very helpful when writing shell scripts. These are variables, most of these variables are related to parameters, the parameters that are passed to the script when invoking the script. So the first variable that we have here is the pound variable. The pound variable, as you can see by the text that we have here, it will show you the number of parameters. So let's say that I invoke this script, and then the script name is script3.sh. So let's say that I type /script3.sh space A space B space C space D. So I have 4 parameters. This variable here, the content of this variable is going to be 4. If I want to see all parameters and I don't have to know how many parameters I have, I can simply use the asterisk. It will show you the number, it will show all the parameters that have been informed. If I want to invoke or retrieve the value of a specific parameter, I'm going to use variable 1, number 1. The second parameter, number 2. The third, number 3. The PID of that script can be retrieved by using the $sign variable, which can be invoked by $sign. The first $sign is because you want to retrieve the content of a variable, and then the variable name, which in this case is $sign. Then I'm running a command that is a valid command, date. Well, I can use the question mark variable to see the result, the status of the previously executed command. Since date is a valid command, it's going to return 0. If I try an invalid command, it should return 127. That is the status code for invalid command. So let's take a look at the execution of this script. And once again, I do have my permission of execution right there. We can see that the script name is displayed in green. So I can simply run script3.sh. But if I don't give any parameters, there, number of parameters 0, all parameters none, first, second, third parameters, they're all empty. However, obviously, the script was executed, which means that I have a PID 3155. I have the result of my date command and the status of the last command, which was this one right here. Well, the status is 0. That's because it is a valid command. However, ASDKFLKAS is not a valid command. So the status was 127. Let me invoke this script once again, and let me inform here A, B, C, D as parameters. Oh, so the number of parameters 4. All parameters A, B, C, D. The first one, A. The second, B. The third, C. What about the fourth? Well, I did not write a line to invoke to retrieve the content of the fourth parameter. If I wanted to, I had to mention the $4 variable. Now, let's make use of some of these materials that we saw. Let's move to the script 4. But now the script 4 is a little bit more advanced because we're going to use conditionals. And this is just, as you can see, the comment here. So any line that you want to insert as a comment, you can simply precede that line, start the line with a pound. So this is a comment, which means that the script is not actually going to run what you write here. And as you can see, it is a script to show you how to create a simple string-based conditional. String-based conditional. Why do I mention that? Okay, first, I have a echo here, which is echo and a question. Do you like candies? Let me insert a space here. Do you like candies? And then I'm invoking the read command. What does the read command do? It will wait for the input from the end user. It will wait for the end user to type something. Once that user types an information and hits enter, that information will be stored in the read, in this case, in the answer variable. So I'm reading the input and storing in the answer variable. Obviously, you can name the variable whatever you want. Now, this is the syntax or the structure of a if conditional. If, bracket, now I'm invoking the content of the variable because I want to compare the content of that variable with a text. This is a string-based conditional. Very important. You must have the space before equal, the space after equal. If you do this, your conditional is not going to work. So, I'm comparing, is the content of answer equal to yes? If it is, then do this. Echo, I'll send you some. And then I have to finalize my if. I'm finalizing my conditional. Observe here that since this is a string-based conditional, I'm using two equal signs to compare the content of my answer variable with this string right here. Also observe that the string is between double quotes. You could also use single quotes, but it must be between quotes. If I wanted to check whether the content of my variable is different from no, for example, I could do this. This is how you compare if a string is different from another string, or the content of a variable, considering that the content is a string, is different of another string, which is not the case. I want to see if it's equal right there. Okay, so let's run and see what happens here. Do you like candies? No. Well, it did not show anything. Well, it didn't because I don't have the condition there. I'm not testing whether the content is different from yes or equal to no. I'm testing if it's equal to yes. If it is, it shows I'll send you some. Okay, but what if the answer is no? So we have the extension of the script for. Same thing, read the answer. If it is equal to yes, then echo, I'll send you some. What if it isn't equal to yes? What if it's different? Then I have else. Well, if it's not equal to this, else, anything else, for any other value, it is going to show good for you. And always remember, I have to finalize that. Do you like candies? Yes. I'll send you some. Do you like candies? No. Good for you. Do you like candies? Whatever. Good for you, that doesn't make any sense. So we still have to enhance, to improve this script. We have to test if it's equal to yes, if it's equal to no, or anything else, if it's equal to whatever it is. So let's take a look at script 6.sh. Equals to yes, I'll send you some. Else if, you can either use else if or, as you can see here, elif. They're the same. So now I'm testing another condition inside the first condition. If it's equal to this, do this. If not, else, right? If it's not equal to yes, but I still have to do another test. It's not equal to yes, but I still want to test if it's equal to no. So else if answer equals no, echo good for you. Now for anything else, then I have my else sentence here, invalid answer, and I finalize my if. Do you like candies? Yes. Do you like candies? Oops. As you can see here, but let's go back there. No. Good for you. Do you like candies? Whatever. Invalid answer. Okay, now I have a complete script. It is testing all the possibilities. So as you can see, conditionals are very important because that's how you can test the output, the result of a tool, the result of a command. For example, once again, backups. If you're writing a backup script, most of the times that backup will depend on something. For example, I will only perform that backup in case new files have been added to that directory, that specific directory. I will only add this incremental backup if the full backup was executed yesterday or last Sunday. I will only run this incremental backup on Tuesday if the incremental backup on Monday have been executed. So it is a very important resource. Now, what if I want to test, write conditionals, but at this time not using text, not using string, using numbers? Okay, I have a script here that will ask for the person's age. How old are you? Now, it will behave differently depending on that person's age. If the content of answer is lesser than 18, LT lesser than, I could use LE lesser than or equal. I could use EQ, which stands for equal. I could use NE, which stands for not equal. I could use JT, greater than. I could use JE, greater than or equal. So there is a bunch of combinations when writing conditionals, comparing values with numbers. Okay, so is it lesser than 18? If it is, print, wow, a kid learning bash scripting. What if it's not? Okay, if it's not, I still want to compare to check that age. Else if is the content of answer lesser than 35, it will show seeking the dream, huh? Now, you may think, oh wait, it's checking whether the content of answer is lesser than 35. But what if it's 15? That means that if I have a kid that is 15 years old, it will show this message and then also show this message. No, that is not the case. Why? Because I have a else if here. This condition will only be satisfied if it does not meet this condition here. So the script will only reach this part here if answer is not lesser than 18, which means that it must be greater than or equal 18 and also lesser than 35. Then it will show this. Now else, which means if it's not lesser than 18, if it's not lesser than 35 or between 18 and 35, it will show, I bet you know your stuff, huh? Okay, so let's take a look at it.
How old are you? I am 10 years old. Wow, a kid learning bash scripting. How old are you? I am 18. Seeking the dream, huh? I am 39. I bet you know your stuff. I am 90 years old. I bet you know your stuff. Okay, good. But let's improve this. What if I want to write the same script, but I want to enter a loop to make that script be executed as many times as the user wants, until the user actually says, I want to close the script, I don't want to run it anymore. So you need a loop, instructions to create a loop. First, we're going to look at the while. There are different ways of writing while. This is one. First of all, I'm initiating the leave variable with no. And then I start my while. And my while depends on a test. The syntax of while is while the content, while the condition is still true, it will execute whatever goes within that while loop. Now, what is my condition? I want to run this loop, I want to stay in this loop while the content of leave is different from yes. Observe that I initiated leave with no. So it will test, is the content of leave different from yes? Yes, it is. It's different from yes because it's no. If it's different from yes, it's going to do. So we have the same thing. Ask for the age. If it's below 18, show this message. Between 18 and 35, show this message. Above 35 or equal 35, show this message. Now, at the end, I am going to write exit script and read what the person enters. That information will be stored in the leave variable. And then I'm done with my loop. When I end my loop here, it will go back all the way up to the beginning of my while. And it's going to test again. Leave. Is leave different from yes? Let's say that here, in the first iteration, the person entered exit script. No. So it will test. Is leave, the content of leave, different from yes? It is different. So it will run this again and ask again, do you want to exit the script? And the person answers no. It will go all the way back here. Is it different from yes? Yes, it is. It will run this again. Exit script, and the user answers yes. It will go back up here. Is the content of leave different from yes? No, it's not different from yes, which means that it's not supposed to run whatever comes within the loop anymore. So it will leave that while loop. Now, observe that similarly to if, you have to use the brackets, the semicolon. Now, instead of using then, as in if, you use do. And when you're done, you don't use fee. You don't close the loop with fee. You finalize it with done. Do, done. Okay, so let's run script8.sh. How old are you? I am 39 years old. I bet you know your stuff. Exit script? No. How old are you? I'm 15. Wow. Exit script? No. How old are you? I am 20. Ah. Exit script? No. I am 45. Exit script? Yes. Done. Now, obviously, our condition is testing the content of a variable with a very specific string, which means that if I use y instead of yes, it's not going to work. It doesn't know that y stands for yes. So we have to use the string that is being compared there. There you go. Now, another condition, another loop that we have available is for. Similar to while, there are different ways of using for. And if you know any other coding language, programming language, you know that the basic syntax of for is how you want to initialize that loop. Usually you initialize variables. Then you have the condition to leave that for, to leave that loop. And then you have, in case you want to execute the instruction in every loop, that's the third parameter, which usually is the incremental, is incrementing a variable. And it also works here. But here we're going to look at a different way of implementing the for loop, which is for a variable and then the list of possibilities for that variable. So for I, variable I, in the list of possibilities. And this is, I can list the possibilities or I can write a command. And if I'm writing a command, I have to use the back quotes. So, for I in, and then I have the command between the back quotes. The command that I'm using here is sec, which stands for sequence. The sequence command, the sec command, will create the sequence according to the standard that you define. So I want to create the sequence of numbers between 1 and 10. It is going to, let's take a look at it, sec 1, 10. It's going to write 1, 2, 3, 4, 5, 6, 7, all the way to 10. So here, for I, in this list of possibilities, it will do echo I. The first loop, the first interaction, I will be will have the value of I is going to be my first possibility within the list of possibilities. My list of possibilities is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first interaction, I will be the content of I will be 1. The second interaction will go to the second option of my list, which is number 2. In the third interaction, the content of I will be replaced by the third option of my list, which is number 3. So it will list from 1 to 10. Let's take a look at it. There you go. You could also do, for example, ls. Let's see what it's going to do. There. If I run the ls command, what does it do? It shows the content of my current directory. And the content is the scripts that I have. Script 10, script 1, 2, 3, all those scripts. What I'm doing here is, for each possibility of the result of the ls command, I want to echo each of those possibilities. That's what it's going to do. Now, we can do the same thing using while, but now I'm not going to use sequence. I am going to use a variable and I will increment that variable. So instead of using sequence, I'm initiating I with 1. I want to repeat that loop, the instructions within the loop, while I is lesser than or equal to 10. Okay, so the value of I is 1. Is I lesser than or equal to 10? Yes, it is. It's lesser than. So do echo I, which is 1. But now I want to increment I by 1. So I will receive the content of I, which is 1, plus 1. Now I, the content of I is 2. It will go back here. It's going to test. Is y lesser than or equal to 10? Yes, it is. It's going to echo I, which is 2. Increment in 1. Now I has value 3. lesser than or equal to 10, yes. It will keep doing it until I reaches 10. 10 lesser than or equal to 10. Yes, it is, because it's equal to 10. It will still do this. But now it's incrementing I once more. It's going to go up to 11. Is 11 lesser than or equal 10? No, it's not. It's going to leave the loop. Let's take a look at it. There it is. The same result of the script 8. Oops, not 8, I'm sorry. Script 9, which I changed. So let me go back there, bring it back to sequence 110, 9, oops, script 9, script 10. They do the same thing, just in different ways. So, in this class, we saw how to write some very basic scripts. We saw how to actually initiate a script. We saw how to use variables, how to write conditionals, and then how to write loops, how to create loops. And the combination of loops and conditionals is what makes scripting such a powerful tool. In our next module, automation, we're going to see different ways of writing scripts to automate our daily tasks as sysadmins, network analysts, or anyone that is facing Linux environments, working on Linux environments on daily basis, and they need to automate their tasks. I hope you enjoyed this class. Thank you very much. Hello. Welcome to our last module, module 15, and the focus here is going to be on automation using scripts. Basically, this is going to be a different module because we're not actually going to introduce new content, but we're just going to use the some of the resources that we've learned so far in order to create scripts to automate our daily tasks. So, what we're going to have here is just a lab with 3 simple exercises, but all these exercises, they require you to remember a different number of tools that we saw during the course, and especially focused on scripting. So let's go straight to it. Letter A, it asks you to write a script to monitor hardware resources being RAM, CPU, and storage. If any of the resource usage is above 90%, log this status into the /var/log/resources.log. The log entry must inform the date, time, the resource type, and its value. If you want to write a separate script for each resource, you can. That's not what I've done. You're going to see that I wrote just one single script to monitor all those resources. But again, you can do it separately. So let's just review what we have to do. We have to write 3 or 1 script that will monitor the usage of the RAM, the usage of CPU, and the storage usage. Now, the storage usage is specifically associated with the root partition. We're not going to care about any other partitions that your system could have. So we're supposed to monitor the RAM usage, the CPU usage, and the root partition usage. And we have to write a script to check that value and compare if it's greater than a specific percentage value, in this case 90%. Now, it's important to realize that we don't have one single command that will just show you this is the usage in percentage. This is the usage of your CPU. This is how much RAM you're using. We do have commands to show that type of information, but you have to customize how it's displayed, how it's given to us. because it's either not going to be shown as a percentage, or it's going to be shown as a percentage, but maybe how much is free and not how much is actually in use. So we're going to see, we have to analyze how to come up with that one specific number. Because remember, in order to write our script, we're going to, in this case, we're going to have a conditional that will simply check, is this value greater than that other value? And then, if it's above 90%, we have to write some information into a log file. In this case, we're going to create a /var/log/resources.log. Okay, so let's take a look at the script that I wrote right here, and then we go back and forth analyzing the commands. First of all, I am creating a variable here called limit. This variable should have the number that you want to compare. So in this case, we have to check if the, let's say, the usage, the CPU usage is above 90%. So I'm going to give the number 90 to the limit variable. Now we have to start thinking about the tools that we have available in order to gather that information. Let me go back to the terminal here. First of all, let's check how much CPU is being used in our system. For example, we saw the top tool. The top tool will show you a bunch of stuff, including this information right here, idle. This is how much of your CPU is in idle state, how much is not being used. So this value here is actually the opposite of the usage. So let's say that idleness is in 90, let's round it up to 98%. That means that my CPU, I only have 2% of my CPU being used. You could use top, and there is a way of running top in a non-interactive way, but personally I prefer vmstat. Vmstat also shows us a bunch of information, and the reason that I like it is because it shows us information about RAM, swap, and CPU. And system usage here is associated with CPU. And again, we have the idleness right here. That's the value that I need. But there is one problem with vmstat. Usually the first and maybe the second lines of it are not very accurate, which means that I can say, I want to run the vmstat, I want to fetch this information every 1 second, and I want to run it 3 times. So let's take a look at it. There, there, and there. Okay, so it measured my information, my resources, the first time. A second later, a second time. A second later, a third time. Now, it is much more reliable. This line here is much more reliable. And this is the value that I need. So if we analyze this resource, I have to gather the last line. I have to fetch the last line. Well, we may remember that we have the tail command that allows us to retrieve only the last line. And we also have the okay, so the last line will give me all this, but that's not what I want. I just want this single column here, which is column number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we have the awk command that allows us to say, okay, I want to retrieve that specific column according to the column number. You're going to see that whenever you're writing automation scripts, you're going to have to learn new tools. Although you already have a number of tools, a number of commands in your toolbox, you'll be constantly learning new stuff. And this is a very useful command that we have. So now let's go back to our script. And here it is. vmstat 1.3. I want to retrieve only the last line, and I want to filter for the 15th column. This is how you do it using AWK. AWK, single quotes, brackets, print, $, and the column number, and then you close the single quotes. Now, this is a very important detail. When writing scripts, shell scripts, if you want to execute a command, you just write the command. If you want to store the result of that command in a variable, you have to have the variable receiving equal the command between the back quotes. So this, including the back quotes, it will execute the vmstat13 tail that pipe tail -1 pipe awk print 15th command. It will execute this command. It will return a value, which is the idleness of my CPU, and store, let's say that my CPU is 95% idle. It will store 95 in the CPU variable. Now, I don't want the idleness. I want the usage. Therefore, I'm going to write a math computation here. I want to do 100, because that's how much of CPU usage I may have at most, minus how much is idle. So 100 minus, let's say, 95. Then it will return 5 here. And then it will display CPU usage, my CPU usage. Then I have to compute my memory usage, my RAM usage. And we saw the free command. We can use the free command, and this is the trick. We cannot use this information here. Why not? Because when we use the free command, the amount of RAM that it's being displayed as free is not the only amount that is actually free. We have to remember that whenever you open a software, you open a tool, that tool will be pulled into the RAM, which is going to use the RAM. But if you close that tool, it's not going to simply free that space of RAM. It will put that in cached. So the RAM is free, but it's been already allocated, which makes it a lot faster in case you want to open a new tool, because the amount of RAM has been already allocated. That is a plus in the Linux operating system. However, we have two options. We can either sum up this value with this value, or we can divide the usage here by the total here. Because the usage here is not in percentage. So we have to divide this by this. Then we're going to get the percentage. But there is still one problem. If we simply divide this by this, it won't return the percentage value. It will return, for example, let's say that it's 50%, it will return 0.5. So we have to multiply this by 100 and then divide by this value. And again, we have 3 lines here. I need to gather 2 information. Both of the information, the data that I need, are in the second line, where there is a string here, mem. So I can use the grep command along with the free command. So I pass free to grep using pipe, and then I grep for the line that has the mem string. Now in this line, I have to gather the third column and the second column. Okay, so let's go back to our script. First, I have my total RAM variable. What it's going to do, run the free command, pipe to grep, filtering for line mem, and then I pass that line to AWK that is going to retrieve only column 2. That value will be stored in my total RAM variable. I do the same thing, but now for the third column, and store it in the used RAM variable. Now I compute used RAM times 100 divided by total RAM, and I store that value in my RAM variable. Now I have my memory usage in percentage. And I print that. Okay, now I have to check my root partition usage. Well, we saw that we can use the df command in order to see the partitions that we have and how much usage they have. I want to filter for this line, the line that has SDA1. Obviously, you have to know what file represents your root partition, which, once again, you can simply run the df command. If you want to use that -h, that's fine. Okay, so my root partition mounts to my SDA1 file or partition. Okay, so this is the line that I have to filter for, where I have SDA1. And the df command already shows the usage in percentage in this column right here. See, use percentage, 64%. So I have to retrieve only this line and search for this column here, which is column number 1, 2, 3, 4, 5. Okay, let's go back to our script. So df-age pipe grep SDA1 pipe awk print column 5, but there is a problem. We saw that my CPU usage, my partition, root partition usage is in 64%. I cannot make comparison, number comparison, using signs. So I have to chop that value, 64%. I have to chop the percentage sign off. So I'm going to use the cut command that we already saw. And we can use cut with the -d option that is used to specify the delimiter. My delimiter is going to be percentage. So when I use a delimiter, I am saying, okay, I want to split the information that I have and use this delimiter as the column separator. Now I have to define the column that I want to retrieve using the -f option and the column number. Well, I want to retrieve the value that comes before the first percentage. So that's the first column, -f1. There you go. And then I print that value. Now, I am not going to use nested ifs because one information does not depend on the other. They are not interdependent. I cannot have, for example, I cannot check my RAM usage according to the CPU usage. I cannot check my root partition usage according to my RAM usage or according to my CPU usage. They're independent. So I have to write 3 fully independent ifs. My first if, I want to check if my CPU variable, which is this one right here, is greater than my limit, which is 90%. But it's not in percentage. If it is, then I have to write a message, which is going to be date, but since it's a command, we have to write it between back quotes. So it's going to print the date and then the message CPU usage above my variable, and I included the percentage here. And then I insert the value, the actual value, my CPU variable, between parentheses. But I don't want to display this in the terminal. I want to save that information in the /var/log/resources.log. Now again, this will only be executed if my CPU usage, right here, is greater than my limit, right here. Then I do the same, I close my if. Why don't I have an else or else if here? Because if it's not above 90%, I don't want to do anything. So I just close my if. And then I do another if for my RAM. Doing the same thing, I just change the message and the variable here. And the same thing for my root partition. I just change the message and my variable right here. There. Now, let's run this script. Since this script has to save information into the /var/log/resources.log, which is a file that resides within the /var/log directory, we have to run this script as root, as the admin user. Because only the admin user, only the root user can save files or change files in the /var/log directory. So what I'm going to do is I will run this script as root using sudo. CPU usage 1%, RAM usage 58%, root partition usage 64%. Now, let me run vmstat13 here. Oh, now it went up. Let me run it again. There. So we can see that in this situation, my CPU usage was in 1%. Now it's in 3%. My RAM, if we multiply this by 100 and then divide by this, we're going to have 58%. We can see that this is a little bit over half of this, which shows that that value is correct. And we also have 64 right here. That's the exact number that I need. Okay, now, if I have this file here, I'm going to clear it. Obviously, nothing has been saved in that file because all those values are below 90%. But what I'm going to do here, just to test whether I can save that information in the log file or not, I'm going to change this to 10%. And that is the reason why I created a variable here, a variable with the value that I want to use as limit. Because if I don't do this, I would have to change, I would have 90 here, 90 here, 90 here, 90 here, 90 here, 90 here. I would have to come here and change all these numbers. Now, since I'm using variables there, I am simply going to change it to 10% here and save it. I'm going to run it again. And let me take a look at this /var/log/resources file. CPU usage is below 10%, so you can see that it did not log the CPU usage. But my RAM and my root partition usage is above 10%. One is 58, the other one is 64. They've been logged. Okay, very good. But now, if we go to letter B, schedule the script written in A, this script here, to be continuously executed every 10 minutes. Okay, whenever we write automation scripts, not every time, but most of the times, you want that script to be executed frequently. How can we perform periodic scheduling? Well, we have cron. So what am I going to do? I am going to edit my /etc, my /etc cron tab file. And here, I am going to do */10 any hour, any day of the month, any day of the week. The root user is going to run my resources.sh script. Now, well, actually, I have to inform here the path, which is /home/linux/scripts. There. So remember, whenever we want to do something every, let's say, 10 minutes, in the minutes column, which is the first column, I'm going to write */10. Can I do 0, 10, 20, 30, 40, 50, yeah, that's it. Yes, you can. That's perfectly fine. But what if you have to run it every minute? well, every minute is easier. You can just do this. But every 2 minutes, would you write 0, 2, 0, 4, 6, all the way up to 58? No, you wouldn't. So you could do *2. That's a lot easier. That's not the case. It's 10. Okay, there you go. So that's how you solve letter B. Letter C, write a script to backup the /etc and the /var/lib directories every day. So you just have to write a script that will copy files to a specific destination and run that script every day. Run that backup every day. Also another backup, but now backing up the /home directory, copying that, running that backup only on Sundays. This is a little bit different. Again, you could write 2 separate scripts, but I wrote a single one. Whenever we are running backups in a Linux system, it's very common to use the tar command. The tar command can be a packager, which is a tool that will just create a package, a tarball, a file containing other files without compressing those files. But tar also allows you to compress that content. So with tar, you have a bunch of options. The options we're going to use here is C, to create a tarball. We want to create a tarball. I want to compress that file using the gzip algorithm represented by Z. You could use J, letter J, if you wanted to use, for example, the bzip2 algorithm. But I'm going to use gzip, which is represented by Z. And then F, to specify the file, the tarball, that will keep all the files in there, the destination file. And then what you want to include in that tarball. So according to the exercise, you should do /var/lib here. And you can pass as many parameters as you want. So the first parameter here that comes after the option F is the tarball, the file that will contain the other files. After that, you're going to use spaces to separate the files or directories that are going to go backed up into this tarball right here. So what I'm doing is including a copy of the /etc and the /var/lib directories into this file. And that's it, at least to perform the backup of those directories. Now, what about running this backup every day? Well, that's going to go in the cron scheduler. But I'm using the same script to also back up the home directory. And it's going to save it, copy it into into the home.tar.gz file. But there is one catch. This command here can only be executed if it's a Sunday. How can I verify that? If you run the date command, you can observe that it shows the day of the week. If I want to retrieve just one specific information regarding a date, I have to use the plus percentage and then a letter that is associated with that specific information. For example, D, that's the day of the month. M, that's the minute. Capital M, month. I want the day of the week, but I want it as a text. I can use lowercase a, which will show the short version of that day of the week, or I can use capital A. There it is. So today's Tuesday. I want to compare with Sunday. So remember, between back quotes, if date plus percentage capital A equals, it's a text, so I have to have the space here, 2 equals Sunday. Then I am going to run this command right here. But, so let me run this script here. There, I'm going to have some issues here because I don't have the permission. But what matters is, okay, so I have the full backup.tar.gz, and I can check the content by doing tar t v f and the file name. There, you can see that we have /etc files in that file, in that tarball. But I don't have my home.tar.gz here. That's because it's a Tuesday, it's not a Sunday. So I am going to remove this file and edit my backup script once again. And I'm going to change this to Tuesday. There. And I'll run it again. There you go. Done. Now, I have to edit the etc cron tab and add it here. I want to run this script every day at 5 in the morning. So minute 0, hour 5, every day of the month, every day of the week. User root is going to run /home/linux/backup.sh. There it is. So, we saw here just 2 scripts, but we used conditions, we used variables, we used a different number of commands. So you can see that basically automating your daily tasks using a Linux system simply depends on your capability of using conditionals, loops, variables, and a bunch of command line tools that we have available. I hope you enjoyed this class. Thank you very much. Hello, welcome to our container management module. The goal of this module is to introduce you to how you can use and manage. Specifically, we're going to focus on Docker. That's the tool that we're going to focus on. But the idea is to learn how a container and container management works. And the reason why I highlight that although Docker is the tool that we're going to use, the focus is not specifically Docker, but it's container management. The reason why I highlight that is because the CompTIA Linux Plus exam requires you to understand container management in general. What that means is, although Docker is kind of the default software that we see for this purpose nowadays, there is also some other alternatives, some other solutions, such as Podman. So now the good thing about that is that all the parameters, all the resources that you have available in Docker, they're there, and you can actually use the same parameters for Podman. So what that means is, once you learn how to work with Docker, you can just start using Podman at any point in time. But before we do that, we need to understand what a container is. And it's actually quite simple. So you can see a container as a small instance, a small appliance, a small instantiation of a specific tool or operating system. So let me give an example. Let's say that you want to use a specific operating system. Let's take an example. If you want to run an Ubuntu instance. Okay, well, when you think about that, probably what you want to do is to install the Ubuntu distribution in your machine, right, and start using that. Okay, but there are situations where maybe you can't, or you don't want to actually install in your hard drive. You don't want to have that operating system directly installed in your computer because, well, you may have to
do some partitioning. You may have to repartition your hard drive. You can't stop that machine. Or maybe this is just, you just want to run that distribution, for example, Ubuntu, for example, because you want to try some stuff. You just want to learn. So there is no reason in doing a full installation if you just want to run some tests. Okay, so as an alternative to that, it is very common to see people using virtual machines. And yes, virtualization is a pretty good solution, pretty good alternative to that situation. Let's say, again, a situation where you want to run an operating system for any specific purpose. Very good. But there are also some issues there. First of all, maybe you are going to create and install that virtual machine just because there is a specific software that you want to use. Well, that is a problem. You're going to use a bunch of resources just because you want to use one specific software, one specific tool, a specific application. And there are some other limitations here as well. For example, network connectivity. So if this application that you want to run is a network application, well, the network connectivity will go through the operating system that is running in that virtual machine. So it may require you to also do that kind of configuration, network configuration. So the level of complexity here may increase. That is why you have this container alternative, which is basically you may determine the application that you want to use, and you can simply say, for example, if you're using Docker, you can simply say, hey, Docker, I want to download this specific application and I want to run an instance of this application. This is such a fantastic tool because once you say this is the application that I want to run, Docker, for example, will be able to find where it's hosted. Actually, you need to tell, hey, Docker, this is the application that I need, and it will search for it. If it is out there, if it is if there is an available instance, an available container for that application, Docker will tell you, hey, here it is. Do you really want it? And if you do, Docker will download it. And then you can simply say, okay, now I want you, Docker, to run an instance of this container. And Docker will do just that. Now, like I said before, network management. Docker is even capable, and it's not specifically Docker, but the container management tool that you're using will be able to even configure the network for that specific application or for that specific container instance. Meaning that if you are going, and this is something that we're going to see, if you want to run an instance of a web server, for example, specifically the Nginx web server, well, the container management tool will also be able to assign network configuration, specifically an IP address to that container instance. It will basically configure the entire network for that machine, for that instance. But not only that, it will also perform the required configuration so that when an external request, an external network request gets to your host machine, it will be forwarded to that container instance. So basically, the client that is trying to access that resource then does not even know that that is a, for example, Docker instance. Okay, so before we actually see how we can configure that, we need to, well, it is not a requirement, but I strongly recommend that you first, you do create a membership for you. You do register to get credentials in the docker.io database. Specifically, you need to access hub.docker.com. So let's take a look at that. So here we are, hub.docker.io, and as any registering process, this is a pretty straightforward, simple process. Once you access this website, you're going to click here on register, and you need to create an account for you, right? So username, email, password, and they will simply send you an email to confirm that. Now, why do you need to, well, again, you don't actually need to create an account, but it's highly recommended that you do. First of all, in theory, you only need a Docker account if you actually want to create a Docker database for you in the hub.docker.com. Well, why would you do that? In case you want to create your own container and have a repository so that you could upload that container that you created so that other people will be able to actually also instantiate that container. And this is out of our scope, right? So the CompTIA Linux Plus exam does not require you, they do not understand that you do need to know how to create a container and make that container available. They do want you to be able to manage containers, existing containers, and that's what we're going to focus on. Okay, so I strongly recommend that you do this for one specific reason, because there are some containers that they require authentication, and we're going to take a look at that. In our next video, the first thing that we're going to see is how you can use your credentials to log into the Docker database. Okay, so that then it doesn't matter what type of container you want to instantiate, you want to download, you will be able to do so as long as you have that Docker account. Now, obviously, I'm talking about public containers. There are some private containers that they're not only requiring you to have an account, they will only allow a specific list of accounts to interact with them. But again, that's not the case. We're not going to focus on that. Okay, so please create that account for you if you don't have one, and let's move forward to the next video. Thank you very much. Hello, and this is our second video in the container management module. Okay, so let's go ahead and get started with it. The first thing that you need to make sure is that your docker.io package is installed. Now, observe that there is also a package called Docker. That is not the package that you want. Well, you do want that as well, but it will come as a dependency when you install docker.io. So make sure that if you don't have docker.io installed, you go ahead and install it. Again, it depends on the distribution that you're using, but if you're using Debian-like distributions such as Ubuntu, this is the command that you want to use. Sudo apt-get install docker.io. Then you have Docker installed in your machine. Okay, very good. Now that you have that, you can just go ahead and run the docker login command. Now, the problem is, if you simply do this at this moment, it will fail. You won't be able to do it. And the reason is, by default, Docker will only accept the administrator, the root user, or users that can run sudo to actually manage Docker containers. Well, but obviously this is an absurd, to be honest, right? You should allow regular users to use the Docker tool. If they do want to run any instance, they should be allowed to do so, obviously, as long as there is some control over it. And the solution to that is basically to include the user that you want to allow to use Docker in the Docker group. And that can be achieved by doing sudo group add Docker. Most likely you get this message. If you've installed docker.io, most likely your system will already have the Docker group. Okay, so you just need to make sure. Once that's done, you're going to run the sudo g passwd-a, then the user that you want to add to the Docker group. Okay, and by doing that, as you can see, I am adding my personal user to the Docker group. Okay, then all that you need to do is to say, now you're not going to use sudo, okay? With your regular user, as you can see, you're going to run new group Docker. And what you're doing here is, okay, so let me go back here. Observe that by default, if you run ID, your user has as its main group the group that was created alongside with your user. So if you create a user called new user, a group called new user as well will be created, and that will be the main group for your user. But in order to run Docker commands, you must specify that your user, at least when you're trying to run those commands, those Docker commands, your user must be part of the Docker group. The Docker group must be your user's main group. Therefore, you're going to do new group Docker. And observe that once I do that here, now my main group is Docker. It's not my personal group anymore, although I am still part of that group. Okay, once that's done, now you can do Docker login. And well, here you can see that my login succeeded. That is because I've done this in the past. I've already authenticated in the past. And when you do it once, for the first time that you authenticate, it will create in your home directory a subdirectory called .docker, and in there will be a file called config.json, and your authentication will be stored in that file. Observe that the password is hashed. Okay, now if it's the first time that you are authenticating, it will ask for your username and password. Pretty straightforward. Okay, now how can we actually start using Docker? Well, what is the container that you want to download and run? So you can use Docker with the search command. And let's say that I want to run an instance of the Apache HTTPD web server. Well, I can run it this way. I can do this search this way. Docker, search, and then the distribution, operating system, software, application, whatever that is that you want to instantiate. Okay? Now, obviously, and I'll do a pipe more here, you might have a bunch of different containers for that same specific applications in different sources, in different locations, right? Therefore, and as you can see here, you can see that list. So for example, for the same HTTPD container here, I have another one over here. I have another one over here, and a bunch of those HTTPD containers. Therefore, you need to observe that before the container, the name of the container, you have the location, the resource that is actually storing the database for that specific package. So by default, if you don't specify where it will download and instantiate, well, download, not instantiate yet, it will download the first one in your list that matches the name that we specified. Okay, if you do want to download, for example, this one, then you have to specify that you want to download the Docker pinata/HTTPD. So what I am actually going to do here is Docker pull docker.io/public i/HTTP. And observe that the only thing that I did differently here was to specify where I was pulling it from, as you can see over here. So again, the command is Docker with the pull parameter, and then where you want to download it from. So I am pulling from that location. When I did that, observe that there is a bunch of pulls going on here. That is because any container is broken down into pieces just to optimize not only the download, but also the storage for that specific package. It's similar to a peer-to-peer communication, right? Where you have pieces of that same specific package scattered across the network. Well, the difference here is that most likely this is not scattered across the network, but it is broken into pieces. Okay, now that I have it here, if you want to confirm, you can run Docker images. and it will list all the Docker images that you have, all the Docker container images that you have downloaded. Observe that this does not mean that you have that Docker container instantiated. It's not running. Only the image is there. Okay? So from here on, you can start actually managing that container. But before we do that, there is a few things that we need to understand. And the first thing is, okay, so I downloaded this Docker image, right? I have this container image over here. What if I want to see some configuration or some information about this image, this Docker container, before I actually deploy it? Well, you can actually run docker inspect and then the name of the package, the name of the container. Oh, I'm sorry. Actually, I forgot that I need to specify docker.io/public i/httpd. And since it's going to show me so much data, so much information, I'm going to do a pipe mark here at the end. There it is. So as you can see, a bunch of information, the ID of that image, some other stuff here, the host name assigned to that machine that will be executed, or that instance, some configuration such as environment variables configured to that instance. So as you can see here, a bunch of information, right? The Docker version. Also, you can also find the version of the application that are going to run. An interesting information here, which is CMD. This actually specifies the command, the tool that will be executed once you instantiate this container. So when you instantiate this container, a terminal, so the shell, the bourne shell, will be executed with the -c option and also these other parameters here. That's what is actually going to execute to run the Apache web server. So there it is. And if you observe, there is no network configuration listed here. Well, obviously, that is because the container has not been instantiated yet, right? So if it's not running, it doesn't have a network configuration. Okay, now there is one problem here. If you analyze, when I did this, I was actually saying, hey, I want to see information of this specific container, but this is a local container, which means that I have already downloaded the image, right? If I try to inspect, for example, and let's actually try to inspect a container that is not here yet, but we are going to use it, which is the Nginx. Well, I can't, because there is no such container image in my machine. In case you want to inspect an image, a container image, before actually downloading it, you can do so, but you're going to have to use another tool called Scopio. There it is. Now, in order to use Scopio, you have to specify the location, the full URL where the image is hosted. So in this case, I know that one possible URL for the Nginx is in Red Hat, right? However, since for the Red Hat, the private Red Hat database, we don't have Nginx there, I'll just pick another tool that I know that is in their public's repository, in their public registry. Okay, well, repositories in container management, they're not called repositories actually, they are called registries. Okay, so let me access the registry.access.redhat.com/ubi9. That is another package, that is another container that is up there. So let me go back there and use pipe more. So there it is. You can use Scopio to inspect a specific container. And there you have it. Okay. So the good thing about this type of solution, this type of tool, is because you can actually inspect a container before you download it. Okay. Okay. Now, now that we know how we can pull an image and also inspect the image, let's actually take a look at an image that we are going to instantiate, we're going to use. So let's pull Nginx. There it is. Again, since I have not specified its specific location, it downloaded the first hit that you can see when you do a search. And this is actually hosted by docker.io itself. Okay, if I do Docker images, I should have two images there now. So as you can see, I have my public i/httpd and my Nginx container. Okay, now, how can I instantiate this container? Well, you can do Docker run, and you want to run it with the -dt options, okay? And this will force the instance to run in the background, okay? Now, instead of using the name of the image here, you have to use the image ID. Although the image ID has a long ID, too many characters, you can actually simply use the first characters. Well, sometimes using only the first character works, but it is recommended that you use at least the three first characters. That is because there is a very high probability that you're going to have two images that begin with the same value, right? In this case, I don't. This one is 6, this one is 2, but just as a tradition, you should use at least the first three. So I'm going to use 6b3. Okay, now, if I run docker ps, I can see. So ps is similar to the ps command in Linux. You use it to list the processes, but the Docker processes or the instances, the running instances that you have. And as you can see, I have this instance here. This is the container ID, and observe that we have two different IDs here. One thing is the image ID, as you can see here, and another thing is the container ID. It is important to understand that because there are commands, there are situations that you have to use the container ID, there are situations that you have to use the image ID. So for example, if you want to instantiate a container, you have to use the image ID because the container is not there yet. It hasn't been deployed. Now, once you have deployed that container instance, now you're going to use commands with the container ID because you do have a container ID for that specific container instance, as you can see over here. Okay, now that I have it running, I can, well, it's running, it's there, that's really nice. And you can also use Docker. Now you can actually start managing that image. For example, if you want to, you can stop that image. And again, you're going to use the container ID now. And similarly to the image ID, you only need the three first characters. So I would use 60F. I'm not going to do that because I do want to have my my container running. Okay. And before we actually see if that container is actually running, working, another important parameter that we have in Docker is Docker RMI. Observe that there are two different Docker parameters for deleting instances or images. If you want to delete an instance, you're going to do Docker RM. However, that won't delete the image. If you want to remove an image, you're going to use the remove image, RMI. And in this case, observe that I don't need this image here, right? I just downloaded it for teaching purposes. So since I don't need it anymore, let's take a look at if it actually works. Okay, so it says that yes, it is working. So let's see if it is actually working. So let me do Docker images. And now you can see that I only have that one. Okay, very good. Now, going back to our instances,
I can see that Docker is running here, the Docker instance of Nginx. Well, and if it is properly running, Nginx is a web server, which means that it should have an IP address. How can I see that IP address so that I can actually access it? Well, we must remember that we have the Docker inspect parameter. Okay, and sorry, there it is. So too much information here. Okay, what if I do grep IP address? Well, it did not return anything to me. And why didn't it? Well, if we actually specify the name of the image, observe that it is not associated with a specific instance. So again, this is one of those situations where we need to actually specify the instance, the container ID, not the image. So let me do it again. There it is. Docker inspect and then the container ID. Now, as you know, it's going to show a bunch of stuff. It is helpful because the information that we're looking for is actually at the bottom. But if that's not the case, if you're looking for a specific information and it's not there at the bottom, you can actually filter for that, right? So let me use the -I option here because I do not want it to be case sensitive. And there it is. So the IP address is 172.17.0.2. Well, if that actually works, I should be able to open my browser and see the web page that is being hosted by that specific web server. So let's take a look. Let's see if that actually works. So here we are. Let's see, 172.17.0. I think it's 2. And there it is. Welcome to Nginx. This is the web page being hosted by the Nginx web server that is running by that specific instance. So that's how you can actually download and deploy container images, container instances, specifically Docker instances, but just keep in mind, it really doesn't matter whether it's Docker or Podman. They both work with the same parameters and actually for the same Docker images hosted online. I hope you enjoyed this video, and in the next one, we're going to see how we can actually interact with the container instance itself, how we can actually access a running container instance. Thank you very much. Hello, welcome to module 17, and this is our first video in this module. And the topic of our new module is Kubernetes. So it is very common to see enterprises, companies that are using Docker. So as you saw in the previous video, in the previous module, you know that the idea of using Docker is to have an easier way to manage applications, but not only to manage, but also to deploy, and you can also configure, you can customize those deployments. So it's much easier to use that type of resource instead of creating specific virtual machines to run specific applications. Instead of having that architecture, you simply run those instances or containers. And we're going to just briefly review it here. Now, the problem with a container solution such as Docker is that depending on the number of containers that you have, the number of instances that you have, it may be quite tricky and complex to manage. And on top of that, you have some other challenges, such as, okay, how can I balance, how can I create a cluster for this specific application here, this specific instance? So Kubernetes is there to do exactly that. So as you can see here, why would we use Kubernetes? In case you need to run some software on a set of nodes, as I mentioned. So for high availability or
load balancing purposes. In a situation where the configuration is repeated on all nodes, well, why have that when you can have a solution such as Kubernetes that can do that for you? You do one configuration, and that configuration is replicated to the other participating nodes. In a situation where you want to auto-discover new nodes, when new nodes information should be added to config file and propagated, and the idea is to have those containers along with a container orchestration system. And this is exactly what Kubernetes is. It's a container orchestration system. So, as I mentioned, it's a container orchestrator, but you can also see it as a cluster manager in case you want to do exactly that, in case you want to create a cluster among those Docker instances, for example. Now, I'm mentioning Docker, but it can be any type of container management software. It places containers on nodes, but in a more customized, dynamic, and automated way. It recovers automatically from failure, so that's why I mentioned earlier high availability. So let's say that you have a specific Docker instance. Let's say that you are running a web application, a web server, as a Docker container. Okay, what if that instance goes down? Well, if you're simply running Docker, for example, or Podman, what's going to happen is it's going to go down and you're going to have to detect it, go there and manually fix it. Whereas when you're using Kubernetes, you can define, hey, I want all these nodes here to share this specific instance, this specific container. If one goes down, then the other one is taken over, or the other ones are taken over. Also, you have some basic monitoring, logging, and health checking, and it enables containers to find each other. Now, as I mentioned, in order to fully understand how Kubernetes work, we have to understand Linux containers, or containers in general. Okay, so first we need to recap the difference between a container system and virtual machines. And as you can see here, when you have virtual machines, basically what you have is the hardware, right? So you have the bare metal, you have you may have the operating system in case it's a type 2 hypervisor, or you have the type 1 hypervisor running on top of the server, and then you have the virtual machines running on top of that. When you are using containers are isolated, but they also share operating systems and the files, the libraries, the binaries that are contained by the operating system. So basically, the main difference is that a virtual machine, right, requires you to determine how much hardware resources will be designated to each of your virtual machines. Whereas a container is just a small application. Well, it can be a complex application, but it's not a full-blown machine. It doesn't require its own, you don't have to specify how much CPU, how much RAM you need for each of those, and storage for each of those virtual machines. So it is an application running on top of your operating system. Now, usually you're going to deploy those containers, those applications, those instances in a very specific, customized way, which means that it is going to save resources. So when you use a container management system such as Docker, the Docker images are read-only templates from which Docker containers are launched. Only top layer is writable, and only changed layers need to be transferred. Now, that is important because what you can see here is that the transactions that are being performed by that management, by that container management system can be quite complex. So that is why a software such as Kubernetes can be so helpful. Therefore, what does Kubernetes do? First of all, scheduling.
So it defines where the container should run. And obviously, we need to understand what a container is. And we are actually, our very last slide here is dedicated to differentiate those three concepts, right? So you have the node, you have the pod or pods, and you have the container. And now the difference between a pod and a container has been covered in the previous module, but let's just briefly recap. A container can be associated with that specific software that you want to run. Now, this software can be just a small software, and it can be a more complex software such as an operating system. But it's that specific instance. Whereas a pod, as we're going to see, can be defined basically as a group of instances, but with a few more features, which we're going to cover in a second. Okay, now, Kubernetes. Scheduling. So where should my container run? It is capable of determining where the container should be deployed. Imagine that you have not just one node belonging to that Kubernetes network. You actually have you want to have a set of nodes. So where should the container be deployed? It also manages lifecycle and health by keeping the containers running despite of failures. It is also capable of determining where the containers are at a specific moment. Obviously, in order to do all that, it needs monitoring. And for security reasons, obviously, it does also implement authentication and authorization. So it is capable of controlling who can do things in those containers. It can aggregate. So it has the aggregation feature, composing sets of containers into jobs. What that means is that it's basically deploying those softwares, those applications as processes. And that's what actually allows Kubernetes to be able to scale in such a proper way. So making jobs bigger or smaller according to the specific situation, which also relates to provisioning storage. Now, I mentioned that we have here a few concepts that need to be understood. We have to be able to differentiate a node, a pod, and a container. Well, the node is basically the machine, can be a virtual machine, can be a physical machine, but it is the machine that will run Kubernetes. Now, you also have pods, which, as I said, you can associate it, you can relate to it as a group of containers. But it does more than that. So pods are the basic building block of Kubernetes. They are the smallest deployable units that can be created and managed in Kubernetes. So a pod is a group of one or more deeply coupled containers. And the reason why we say deeply coupled containers is because they share network, share storage, and they may share other information, such as an IP address. Now, to each pod, we assign a specific dynamic IP address. Therefore, what you can see from here is that, let's say that you have a pod. So you have a group of containers that are being managed by that pod, right? What happens if and it's all those containers, let's say that they're all deployed in one single node. So the same machine deploying that specific pod with those specific containers. What if that pod goes down? Well, another machine running that same pod, a copy of that same pod, which means a copy of those same containers, will take over that IP address. So although each pod will get a specific IP address, the other pods can take over that IP address. And also observe that the instances, the containers that are running inside that specific pod will have that same IP address. Therefore, we need a service. So a service in Kubernetes is an interface to a set of replicated pods, which acts as a load balancer. It provides an abstraction layer so that you don't need to worry about containers location. So exactly what I just mentioned, that's how we can implement high availability and load balancing using Kubernetes. And obviously, we also need a networking service. That is because if you think about it, you have a physical node, a physical host that is assigning a specific IP address to a pod. Therefore, a pod is a software, but it's seen by the other nodes in the network as a host. So, and also there may be a bunch of containers running inside of that pod or being managed by that pod. At the end, if you look at the architecture or the topology here, you may have a regular node such as a workstation in your network that needs to get access to those containers, but they're behind a pod. That's what has the IP address, and the pod is behind the host node that is hosting that pod. Therefore, you have to have some sort of bridging control and a forwarding control for that communication to work. That's why we need the networking service. So the pods are scheduled on a flat shared network across all nodes. Each pod can communicate without proxies and translations with other pods within the cluster. So observe that NAT and proxies are not required for the communication among pods within the cluster. Now, obviously, as I mentioned earlier, if you're talking about the communication with other nodes, well, that is necessary. So several plugins are available in order to deploy just that. So a networking service, which in Kubernetes is called a networking plugin, has different implementations. Now, different companies, different people designing these plugins. Here is a list of a few, but there are so many others. We're going to see, and obviously each of those plugins, they have their own characteristics, they have their own features. So you're going to see that in our next video, in which I will show you how to install and configure Kubernetes, we're going to use Calico. But again, it will depend on your need, it will depend on what you see that is the best solution, the best plugin for your reality, for your own scenario. Obviously, you have to go through those plugins, a description of those plugins, to better understand which one will be the best fit for your scenario. So again, to summarize, we have to understand the difference. We have to be able to differentiate nodes, pods, and containers. Containers are packages of applications and execution environments. Pods are collections of closely related or tightly coupled containers, whereas nodes are computing resources that house pods to execute workloads. So these are some concepts that we need to understand before we move forward and we see how to actually deploy Kubernetes, which is what we're going to do in our next video. I hope you enjoyed this one. Thank you very much. Hello, welcome to our CompTIA Linux Plus update course. The following videos that you're going to watch are videos that were created to update you and prepare you for the new version of the CompTIA Linux Plus exam. As you probably know, currently CompTIA Linux Plus is in its 5th version, and they are designing in the year of 2025 they will start applying its newest version, which is going to be version 6, also known as XK0-006. Okay, and there is a few things that were added. There were a few things that were removed compared to the previous version, version 5, and there were a few things that were actually brought back from version 4. Okay, so one of the things that you should know for this new version is the concepts involved in open source and free source and free software, and also licensing. Okay, so just a few concepts that we need to understand. The first thing is the difference between open source and proprietary software. Okay, so open source software and proprietary software. So as you might know, proprietary software is a software that belongs to a specific company. Now, observe that belonging or being a proprietary software does not mean that you have to pay for that software. Okay, well, most commonly, yes, that is the case, but not necessarily. A proprietary software is a software that you cannot modify, you don't have access to the source code. So again, it belongs to a company, and that company has full control of the source code of that software. On the other hand, an open source software is a software that the source code is open. And what that means is you can actually do a bunch of things with that source code. You can investigate it so that, for example, you really want to understand how it works. You want to modify it. You can also do that. So as you can see, open source licenses, okay, or softwares that are licensed or released as open source, or softwares that are licensed by a license that determines that it is an open source software, are used to ensure software freedom, allow users to, observe this, run, study, modify, and redistribute that software. And this is actually very interesting, okay? Because many people, when it comes to open source software, they think about the ability to study the code, modify the code, run, whether it's the original source code or run the software after making modifications, but you can also redistribute it. Now, yes, there are different licenses, and we are going to address that, but there are different licenses that determine how this software can be redistributed. Again, we're going to talk more about that. And it requires that any derivative works remain open source. Okay, what that means is, again, if we redistribute that software, but we redistribute after making modifications, so we are creating a derivative of that software, okay? We are creating a fork of that original source code. If that's the case, this new release, let's say, or this new fork must remain open source. You cannot get a hold of an open source software, make modifications to its source code, and then release it as a proprietary software. You cannot do that, okay? Open source licenses allow software to be freely used, modified, and shared, as I mentioned, and it ensures that the source code is accessible and can be built upon. Okay? Now, as far as the licenses, there are many different licenses out there. In the Linux world, and obviously for the CompTIA Linux Plus exam, this is the most important license that you should understand, you should be aware of, which is the General Public License, or GPL, okay? So the Linux kernel is licensed under the GPL, the GNU GPL, okay? And this is a copyleft license. Well, and there is actually a big confusion, a huge confusion surrounding the definition of a copyleft license, okay? So copyleft licenses, you can see it as kind of the opposite of copyright, because if you recall, copyright means that the owner of, let's say, a song, okay, or the author of a book, right? Well, what it guarantees is that that specific product, that copyrighted product, cannot be copied, cannot be redistributed, okay? It cannot be modified, right? And as we saw, an open source software, or software that is licensed as an open source software, actually guarantees that that's exactly what the user can do. But then you have another definition which guarantees these other determinations, which guarantees that you can run, you can access, you can modify, and you can redistribute. And there is a fifth rule that guarantees the other four. That's why it's called copyleft, which is, again, the opposite, kind of the opposite of copyright, okay? Copyleft licenses require that any derivative works be distributed under the same license. Now, observe that there is a difference here. When we talk about, again,
an open source software, it determines that the derivative of those of that specific software must remain open source, right? Well, when it's a copyleft license, when it's licensed under a copyleft license, it not only guarantees that it will be an open source software, but it also guarantees that it will remain under the same license, okay? Well, whereas a permissive license, not a copyleft license, such as the MIT license, the Apache license, the BSD license, okay, they allow greater flexibility in how the software is used and distributed. What this means is, if you get a hold of a software that is under the Apache license or the BSD license, for example. Well, what that means is if you make modifications and you redistribute that modification, you can actually change the original license as long as it still remains as an open source license. It is licensed as an open source software. You can change the license. So for example, you could get a hold of a software that is under the BSD license, okay? And then you could make modifications, release that modification under the Apache license, for example, okay? So here are some examples of open source licenses. Like I said, the GPL, the GNU General Public License, that is the most famous one in the Linux world, because this is the license that dictates the Linux kernel or the core of the Linux system. It is a widely used copyleft license that requires any derivative work to be licensed under the same terms. MIT license, it's a permissive license that allows for a wide range of uses, including commercial use with minimal restrictions. Apache License 2.0, another popular permissive license that grants broad rights to use, modify, redistribute the software. And BSD license, a family of permissive licenses that are known for their simplicity and flexibility. Now, observe that all of these licenses, they define how you can access, modify, redistribute, and that sort of stuff, right? There is nothing here that determines, or at least not for most of the licenses, okay? Not all, but most of the open source licenses. There is nothing saying that a open source software must be free of charge, okay? So there is a difference between a free software and a free of charge software. What that means is a free software is a software that you can do exactly the same stuff that we just mentioned here, okay? Again, it does not mean that it's free of charge. If we take, for example, the Red Hat Linux distribution, okay? The Red Hat Linux distribution, although it is an open source software and you can actually make modifications, you can access their source code. It is an open source software, okay? And if you make modifications, you can still redistribute that software. But you can, if you download Red Hat, at some point it will ask you for the purchase of a license. Okay, well, that license that you can purchase is to get their support. So if you want to have the Red Hat support, if you want to use their official repositories, they charge for that. But the Linux distribution itself, they do not charge for the Linux distribution itself. Okay. On the other hand, you can actually have a Linux distribution that you charge for it, not for support, but for the distribution itself. Okay. Now, it's also important to note that there are a few licensing initiatives. Most importantly, there are two, the OSI and the FSF. Now, the OSI is not the ISO OSI model, okay? The Network Communication Reference Model. It has nothing to do with the ISO OSI stack model, okay? The Open Source Initiative is an organization that promotes open source software and provides a list of approved open source licenses,
Okay, what this means is if you access the OSI website, you can actually see a list of all the open source licenses that are recognized by OSI. Okay, the Free Software Foundation is not only to document or provide you information about open source, okay? Because that's the goal of the open source initiative. The Free Software Foundation is much more focused on promoting free software, okay? So they promote free software, which is software that users have the freedom to use, modify, and redistribute, okay? Now, the licenses approved by the OSI and the FSF are often referred to as free and open source software licenses, or simply FOSS licenses. So again, observe that there is a difference between open source software and free software, okay? Open source software means you have access to the source code, you can make modifications, but they can be more restrictive. You have more let's say, licenses that give you more freedom in regards to what you can do with that code and how you can redistribute it. But you also have some more restrictive licenses. The idea of free software is to promote the software that will give users freedom to use, modify, and redistribute. The difference is they are promoting the idea of, hey, we want you, so if our software is under a free software license, we're basically saying that we actually want you to use, to have access to the source code, try to identify mistakes, make the software better so that you can improve it, make modifications, and redistribute a better product. So there is a difference there. Okay, and it's really important that you know these definitions for the CompTIA Linux Plus exam in its newer version. Okay, I hope you enjoyed this video and see you in the next one. Thank you. Hello, welcome to our CompTIA Linux Plus prep course, and in this video we are going to address architectures, CPU architectures. And although it may seem, when you look at the topic, right, it may seem like something that should not be covered by the CompTIA Linux Plus exam, but it is actually very important, and that is the reason why CompTIA decided to bring this topic to the exam, okay? Because they do not actually require you to understand the details of CPU architecture. So they do not necessarily need you to understand, for example, the difference between the two main ISA architectures or the instruction set architectures, which are the CISC and the RISC architectures. But it's also important that you do know that, you do understand at least a little bit of it, because this will lead you to understand the CPU architectures that, or at least the main CPU architectures that are out there, and it will also help you understand why you have to find the right file so that you can download the right file and try to install that Linux operating system, okay? So the thing is, maybe you had this issue before where, let's say that you have a Mac OS X, you have a Mac computer, such as a MacBook Pro, just an example, right? And you search for Ubuntu Linux, download Ubuntu Linux, okay? And then it downloads a file, and part of the name of that file is x86-64. So it says something like Ubuntu desktop x86-64 whatever .iso, right? So you download it and then you try to install it. It doesn't work. The reason why it doesn't work is because you downloaded a Ubuntu version that does not support that specific CPU architecture. What that means is the operating system cannot speak the language that the CPU understands. It does not understand the instructions or how it should form the instructions to send those instructions to communicate with that architecture, that hardware architecture, that CPU architecture, okay? Now, the first thing that you need to understand here is, again, there are two main instruction set architectures or two main ISA architectures, CISC and RISC. Okay, the CISC architecture, that is the most common one. It's been around for many years, and CISC actually stands for complex instruction set computing. Okay, and what it means is you have a CPU that understands the hardware CPU, the hardware CPU unit. It understands instructions, okay, assembly instructions, hardware instructions. But it also understands more instructions because it will actually be capable of receiving different instructions, different functions from the hardware language, okay? And then it will translate that function to the more detailed or actually the simple instructions that can be sent to the CPU so that the CPU can send information to the main memory and retrieve data from the main memory. On the other hand, the RISC architecture is a simpler architecture as far as instructions. That type of CPU does not support many functions. It does not know many functions, many methods. It only knows some basic instructions. The benefit of it is that you have a CPU that performs better compared with the CISC architecture. Now, the reason why the CISC architecture became so much more popular than the RISC architecture is because although it is a more complex, the CPU understands a more complex set of instructions, it makes the life of the programmer, the hardware coder, or the hardware assembler a lot easier because this assembler can use less instructions. It can use more, let's say, human understandable instructions, okay? Now, it became more and more popular over the years, over the decades, because hardware capacity, CPU capacity evolved so greatly that although a RISC architecture performs better, the CISC architecture still performed very well compared to the softwares that exist. So it would not make any sense to make use of an architecture that makes the life of the hardware developer a lot harder, and there is practically no gain in doing that. With that being said, again, the CISC architecture became more popular. So, for example, the Intel 32-bit CPUs that you used, let's say, 10 years ago, right? 15 years ago, 20 years ago, that was the 32-bit architecture that became a standard, right? If you remember so as you can see here, right, if you remember of any of these CPUs here, these are CPUs that had the 32-bit architecture. Now, over the years, the quality and the capacity of the hardware CPUs increased greatly. So they saw the opportunity to, instead of using CPUs or assembling CPUs that only supported 32 bits, it could only exchange 32 bits, blocks of 32 bits at once between the CPU and the main memory. So they saw the opportunity to increase that to 64 bits registers. Okay, so in one block, you could transmit not only 32 bits, but 64 bits. So that's the architecture that became common, and this is what you see nowadays, right? All these CPUs nowadays. This is a technology or architecture that was designed by AMD, and although you may have an Intel CPU, that Intel CPU probably implements the AMD architecture as well. Okay, so the x86-64 is nothing more than the traditional CISC architecture for 64-bit CPU registers, and that is what you see most commonly nowadays. On the other hand, you may also see the ARM architecture. It's becoming more and more popular because of the Mac computers, right? So if you have a MacBook Air, MacBook Pro, most likely you have a M1, M2, M3 chip. And if that's the case, it is a ARC64 architecture, also known as ARM64 architecture, okay? So that's why if you have a Mac computer with the M1 chip, for example, and you downloaded the Ubuntu Linux x86 64 architecture, you try to install it in your Mac, it did not work, okay? You also have some other architectures here, but they are not important, okay? For the CompTIA Linux Plus exam, you have to understand the x86-64, the ARM or ARC64 architectures, and also the x86, that's the legacy architecture for Intel AMD processors in their 32-bit registers version, okay? Now, just one other important information, or at least useful. As you can see here, multiprocessor machines. All of the above architectures may come in a multiprocessor flavor, often called symmetric multiprocessing or simply SMP. This is not a problem for Ubuntu. It can handle multiprocessors just fine. Now, this is not something that is because when you read this, it may seem like, well, Ubuntu is better than the other distributions because it supports the multiprocessor architecture. Well, that is not the case, okay? Because multiprocessors or SMP does not mean that it is a different architecture. It's just a machine that supports more than one processor of a specific architecture. So, for example, you may have a SMP machine with x86-64 architecture. Okay, so it's a machine with 2 or 4 processors, for example, in that architecture. So it does not change anything as far as architecture. Okay, it does change how the CPU is controlled, or the CPUs are controlled, but as far as instructions and architecture and registers, nothing changes. Okay, so what that means is you do not need to download a specific Ubuntu version if you have a multiprocessor machine. Okay, I hope you enjoyed this video. Thank you very much. Hello, welcome to our CompTIA Linux Plus prep course, and in this video we are going to address the Graphical User Interface, or GUI. This is another topic that was previously excluded from the CompTIA Linux Plus exam. It was actually part of version 4, excluded for version 5, and now they're bringing it back for version 6. So it is now one of the topics for CompTIA Linux Plus version 6. And although differently from older certification exams, such as one of the first versions of the Linux Professional Institute Certification 1 or LPCI 1, back in the day, you actually had to know how to configure at the time the X Windows server, or the X server, or X11, or Xorg, whatever you want to call it. Wayland was not present at the time, so we'll talk about that. But you actually had to know how to configure it. That is not the case anymore. You only need to understand what a graphical interface is, examples of desktop environments, examples of window managers, and examples of display managers, roughly speaking. But also, you must understand, you must be able to tell the difference between these. So let's start with the idea of a graphical user interface. Well, obviously, as you might know, back in the day, the Linux system, just like FreeBSD and Unix systems, generally speaking, they did not provide you with a graphical user interface. That means that you you only had access to the console, to the terminal. So everything that you would do using the terminal, the command line interface, right? Even browsing, for example, there are command line based browsers as well. But obviously, since the Linux system started to become popular, they saw that they would have to actually make it more appealing and easier to use for end users, right? That's when they came up with the idea of providing a graphical user interface similar to the interface that you have when you use Windows or Mac OS X, right? Now, the way that they designed the proposal was by creating a server known as the X at the time as the X11 server, or simply X server, and we'll talk more about that. But you had this server, and then you'd leverage a client server architecture where the client would request the server to form the window, to form that graphical interface, and once that image was drawn, for example, then it would send back to the user, to the client. Now, the way that they implemented that was by combining these three different solutions here: a desktop environment, a window manager, and a display manager. The desktop environment is nothing more than the actual GUI interface that you use. So again, similar to what you have in a Windows system, that desktop area, and then you have icons, you have applications that you can open. When you open an application, it will open a window with a graphical representation of that specific tool, right? You have the cursor, so you have all the apps there that you can access and use using the cursor and using your display monitor, right? Some examples of a desktop environment. We have the GNOME, which is the current standard. If you use for most Linux distributions, GNOME is the default desktop environment. But you also have some popular ones such as Cinnamon, Unity, Mint, and KDE or KDE Plasma. Actually, Mint is not that popular anymore, so I would say that most commonly you have GNOME, Cinnamon, Unit, and Plasma, and you have their logos here. So this is GNOME, this is Cinnamon. Obviously, you have Unity here and KDE Plasma. Okay, they changed their name from simply KDE to KDE Plasma. Okay, now in order to, let's say, build that environment, that desktop environment, you need again, according to how the X server system or the X server protocol was designed, you would need a window manager to assemble those windows, to determine what colors are used where. And all that interface that you see is actually managed by a window manager. Okay, and here you have a few examples of window managers. GNOME, for example, the GNOME desktop environment uses Mutter as a window manager. Cinnamon uses Muffin, Unity uses Compiz, and the KDE Plasmas use KWin. Okay, now in order to access that desktop environment, you need a display manager. The display manager is the solution that will take care of logins, verifying credentials, but also triggering, right, loading the desktop environment that you are willing to use. So for example, if your system is using GDM, right, GDM will ask for your credentials. If you provide the correct credentials, it will launch, for example, the GNOME desktop environment. And in order to assemble all those windows that you're going to use in your desktop environment, in your GNOME desktop environment, it will communicate with Mutter. And Mutter will be responsible for assembling those windows that it should assemble. Okay, some examples of display managers, we have GDM. GDM is the display manager for GNOME, used by GNOME. LightDM is the default display manager used by Cinnamon and Unity as well. And SDDM is the default display manager used by KDE Plasma. Okay, now I mentioned that the architecture implemented at the time by Linux systems is kind of unique when compared with the other solutions that you have, such as the Windows system. In a Windows system, the graphical user interface is the system itself, right? And what that means is the applications that you want to run, that you want to launch, they are controlled locally, but by the operating system. Okay. Now, when this idea of a graphical user interface was designed for the Linux system, it was designed as a client-server architecture. So what that means is you have a client, which is the machine that is, or the user, or the operating system that is willing to launch an application. Now, this application is actually controlled, or how the application is going to be designed, how it's going to be built, is controlled by a X server. So you have an actual network, client-server network architecture. It communicates through the network. So the client will request the server to assemble the images, to assemble that screen, to assemble that video format. The server, the X server, will assemble that image and send it back to the client. Well, what happens there is, at the time, it was a good solution because that would provide you with the chance of having one server, and that one server taking care of multiple sessions. Now, observe that it would not only be able to take care of multiple applications, right? But it was also capable of taking care of multiple sessions. So you could have one machine or many machines at the same time using one single X server, right? You did not need one X server per machine that you wanted to use a graphical user interface, which at the time was a very interesting idea because you could also use the network data communication techniques in order to control, for example, who could access or invest in your network performance, and that would increase how your X Windows systems would work as well. So as you can see, the X Windows server, and actually it's X Window and not X Windows server. So it uses the X11 protocol, and the X.org or simply Xorg is the current application that implements the X11 protocol, okay? And like I said, it's a client-server architecture. Now, in 2017, well, it was actually designed a little bit earlier than that, but in 2017, Wayland is another graphical user interface manager that started to become popular, and in 2017, it's actually started to replace the X window system. Okay, now observe that up to this day, Wayland, although it became the standard, you still have the option to transition back to the X window system. And it's, for example, in Ubuntu, right? In the next video, I am going to show you that if you simply want to use X Windows Server instead of Wayland, you can very, very easily do that. Okay, you can move back and forth. So the thing about Wayland is that the application communicates with the compositor directly. So there is no network communication. You have a local communication between two different applications. Okay, so you have a pipeline between two different applications. The compositor, which is the application that will assemble the graphics, it would be similar to the window manager in the X Windows system architecture. Okay, but again, it does not involve network communication. So it's similar to having everything that is happening here, but without that X server in between, okay? So you have an application compositor architecture, and that represents a local communication or a local pipeline. When I mention communication here, I do not refer to a network communication. Okay. Now, Wayland is newer, more performable, and a safer solution. The X Windows system has always been known for the many security flaws that it has. Okay. Now, although it seems like Wayland is better than X Windows Server in all regards, which might be the case, but there is one problem and one reason why so many people still use the X Windows Server system. And that is because being it so stable, because it's been around, not stable, but so present, so predominant, because it's been around for many, many years, more than 20 years, right? So it's the documentation is vast, that's one. And another one is there are some applications that they were developed to integrate with the X Windows system. They are not supported by Wayland. So that's one reason why so many people still transition back to the X Windows system. Okay? Now, another thing that the CompTIA Linux Plus exam requires you to understand is that aside from the local graphical user interface, you also have the possibility of performing remote access to share graphics. So a graphical user interface can be remotely accessed. Well, probably you've heard or used one of those solutions, such as VNC, the Virtual Network Computing. Probably this is the most common tool to perform remote graphical user interface screen sharing. It will also allow you to remotely control someone else's computer. So if someone has VNC in his or her computer and that person needs some help, you can also, using the VNC client, access that machine and control their graphical environment. Okay. Similarly, you have the XRDP. Now, XRDP, that is the Linux free version or free application that allows you to access RDP. RDP is the remote desktop protocol deployed and used by Microsoft, right? So Microsoft has their own proprietary remote access protocol and remote graphical user interface sharing protocol called RDP. If you need to access a Windows that is running RDP, but you actually use Linux, you can use the XRDP app, okay? Another interesting tool for remote desktop access is the No Machine, or simply NX. No Machine is interesting because you need an application on both ends, but the good thing about it is that it does not export the entire graphical user interface. It was designed to share resources such as files or specific applications. The good thing about that is that you reduce a lot of network traffic. Okay, so it makes the communication faster, and that's why NX became so popular, because it is a very performable tool, and it's available for most of the modern operating systems. And another tool that is very much used is Spice. So Spice, similar to Vim, Spice stands for Simple Protocol for Independent Computing Environments, and the idea is it will provide you access to hypervisors. Virtual machine hypervisors, that software that control virtual machines, that control virtualization, right? So you can use Spice to remotely access hypervisors and remotely access virtual machines instantiated by these hypervisors. Now, Spice became very popular because, as you can see, it is compatible with the most important, let's say, and widely adopted Tier 1 hypervisors or Type 1 hypervisors, such as VMware ESXi, Microsoft Hyper-V, Xen Server, and Linux KVM. And as far as remote access desktop remote access, the CompTIA Linux Plus also requires you to understand something called SSH port forwarding. Now, SSH port forwarding, although this is not a technique that was, or a solution that was designed specifically to allow remote desktop access, it can be used for that purpose. Now, obviously, we first need to understand what SSH port forwarding is. And it's nothing more than using the SSH protocol to access another port. Okay, so imagine that you are in a network and that network does not allow you to access to transmit a specific type of data. So let's say that you want to perform FTP transfer. You want to use the FTP protocol to transfer files from your machine, that machine that is restricted, to another machine somewhere else using the FTP protocol, but that protocol is blocked. Let's say that the SSH protocol is accepted, okay? It's not blocked. Well, you can perform SSH port forwarding. What it's going to do is it will establish a SSH tunnel, SSH connection, and then it will transmit the FTP data through that SSH tunnel. Okay, that's what SSH port forwarding is. Obviously, you can perform local and remote SSH port forwarding. Now, specifically under the graphical user interface or remote desktop access topic, you need to understand that you can use SSH port forwarding to perform X11 forwarding. And it is comprised of, again, using a SSH tunnel to transmit, to perform that client-server X Windows Server communication. Now, the benefit of it is you can actually execute an application that is installed remotely on the X server, but it's not installed in your local machine. So, for example, and back in the day, it was very common to see the so-called, at the time, thin clients, right? So let's say that you have a network and 50, 60 machines, desktop computers there. They were not very powerful, right? So, well, and they need to run an application that is a somewhat heavy application. It's a cost application in regards to hardware resources, right? So you had basically two options. One was, okay, we're gonna buy brand new machines, more powerful machines, replace all these 50, 60 computers, desktop computers. Or we can invest in a server, right? And that server is a very powerful server. And the application that these 50, 60 desktop computers need is installed there. And it's a graphical user interface application, right? That application is installed there. In these thin clients, you would perform X11 forwarding using the SSH tunnel. These desktop computers would request the execution of that application to the X server. The X server had that application installed. It would assemble the screen and send it back to all those clients. So those clients were using the application, but the application was not actually executed locally. It was requested, executed, processed remotely by the X server. The X server would only send back the result to all of those clients. And obviously, you can also perform console redirection using the VNC tool, as well as mentioned previously in the previous slide. Okay, so as far as remote desktop and local window manager system and graphical environment for the CompTIA Linux Plus exam, these are the topics that you need. I hope you enjoyed this video. Thank you very much. Hi, so as mentioned in our previous video, the idea here is to simply show you how you can switch between Wayland and the X server. So again, it's actually pretty simple, okay? By default, as I mentioned, Wayland is the default one, but you can actually edit the /etc. Obviously, it depends on the display manager that you're using. In this case, I have GDM. Okay, so under the /etc/GDM3 directory, there is a file here called custom.conf, and that is the file that I am going to edit. Okay, as you can see here, there is one directive, which is the wayland enable equal false. As you can see, it's a commented line. So this line here means I can use it to define whether I want to enable or disable wayland. So by default, it's enabled. If I want to disable it, I can simply uncomment this line, and then I obviously save the file, which is something that I'm not doing here at this moment. But if you do want to do so, you save it, and then you have to restart your display manager. In the Ubuntu system and many other systems, you use the systemctl tool to restart GDM by doing this. I'm not going to do this because it will crash the display, restart it, but that's all that you need to do. With that, you can switch from one display manager to another one. Okay, again, we took the GDM as an example because it's the default one for most distributions. If you use a different display manager, that's the one that you need to configure. You need to add it, and obviously you need to know what the configuration file is. But for now, you don't actually need to know how to do this for the exam. You just need to, I just wanted to show you that this can be done. Thank you very much. Hello, welcome to our CompTIA Linux Plus prep course, and in this video we are going to address virtualization. So virtualization is another topic that was introduced to the new version of the CompTIA Linux Plus exam, although the CompTIA Foundation is not actually requiring you to know how to, for example, know the technical implementation or the technical how to implement the technicalities of virtualization. So what that means is they're much more concerned about whether you understand what virtualization is, the tools that are available, how you can manage virtual machines, and the types of network interfaces that you can implement when virtualizing an environment. So they're basically trying to understand if you know how virtualization works and how you can manage a virtualized environment. Also, the concepts behind virtualization, such as what is a hypervisor, what are the types of hypervisors that you have, such as hypervisor type 1 and hypervisor type 2. And again, you also need to know the virtualization, at least the most common virtualization solutions that are out there, okay? So before we talk about virtualization per se, let's first address virtual machine, okay? So virtual machines are, their goal is to provide strong isolation. And what that means is you want to make sure that you have a virtual machine, okay, which is hosting its own apparently independent and safely separate environment. And when I say independent and separate environment, I'm referring to the physical and the logical resources. So, for example, a virtual machine is nothing more than an instance. It's a software, so it's an instance of a software, just like a container, as we saw in one of our previous modules, right? So a virtual machine is very similar to a container, but a container is a specific application that you are deploying on top of an operating system, and you have a container management tool that is controlling when and how that specific application is deployed, right? Well, a virtual machine is actually also an instance. It is also a software, but it is a software that mimics the hardware. So the idea is to use one single hardware, one single bare metal, and then on top of that bare metal server, you create several different instances of virtual machines. And each of those virtual machines, they are working as if they are an independent physical machine. That's not the case, but that's the idea. You want to use it as if it is an independent, separate physical machine running an operating system and the applications that you want to run. Now, like I said, these are not actual separate machines. They're running on top of one single physical resource. Now, these physical resources, they are organized and addressed to each specific virtual machine that you have deployed on top of that specific server, bare metal server, right? So the resources such as storage, you have, for example, a SSD drive, and then you have 4 virtual machines. Well, you're going to assign a piece of that SSD drive to virtual machine 1, another piece to virtual machine 2, so forth, so on. So let's say that you assign 100 gig to VM1. Well, that 100 gig file is actually going to be seen by the virtual machine as its hard drive or as its storage solution, whatever the technology is, whether it's HD, SSD, really doesn't matter now. Okay, but that is seen as its storage device. Okay, and again, it's important that you have a solution, a virtualization solution that is capable of managing these virtual machines independently and separately, which means that resources, let's say a user that is using virtual machine 1 cannot have any kind of access to virtual machine 2, at least not based on virtualization. Obviously, you can have network communication, you can have files being shared across those different virtual machines. Okay? So again, virtual machines provide strong isolation. Each VM hosts its own operating system kernel, exists in a separate memory space on top of a hardware virtualization layer. Virtual machines are resource intensive, right? Each VM contains its own kernel and applications, and that's why it is resource intensive. Again, if you have 4 or 5 VMs running on top of one bare metal, you need to make sure that hardware, right, that bare metal server, that is the underlying physical resource on which the VMs are running, you need to make sure that physical resource is capable of running those 4 or 5 VMs. It has enough physical resources that it would be similar to having 4 or 5 independent, separate bare metal physical servers. Okay. And it allows the execution of software application compatible with the operating system running on the VM. And this is actually big. This is huge. Very, very important. So, and it's actually one of the reasons why virtualization became so popular. So imagine that you have a Windows machine, right? A machine running the Windows operating system. Well, you can create a virtual machine that is running Mac OS X, that is running Linux, FreeBSD, and basically any of the modern operating systems. Okay? Now, what makes VMs possible, what makes virtual machines deploying virtual machines possible is the concept of virtualization. So again, virtualization is nothing more than creating multiple isolated environments sharing a single hardware resource, right? Such as memory, storage, and network, right? So when you think of network, imagine that you can actually create, let's say that you have a server, one single machine, right? And you deploy 4 different virtual machines on top of that physical machine. Well, you can actually create a network and that is accessible for all those 4 VMs. Okay, although it is a communication that is not going to the actual physical network, they are communicating as if they were in a physical network. So there is a deployment there that will the virtualization solution will be capable of, for example, managing how that, let's say, one single network interface card is seen
as another single network interface card by each of those 4 virtual machines. So at the end, what you have here is that network interface card is acting as if it is a switch, and then you are creating virtual network interface cards out of that physical network interface card, so that each VM has its own virtual network interface card. And again, the physical network interface card is the switch connecting those 4 networked VMs. Now, again, what actually makes this possible is the idea of a hypervisor. So a hypervisor is responsible for managing hardware and isolating virtual machines from each other. So as you can see, basically, VM is not the technology. VM is the instance, right, of a software. The technology is virtualization, and virtualization is deployed by a solution called is controlled, by a solution called hypervisor. So the hypervisor, again, is the software that is controlling the virtual machines, controlling, again, how these virtual machines are deployed, what kind of physical resources they have access to, how much of each physical resource they have, how they are interconnected, how they communicate, how they are processed, when they are deployed, when they should be stopped, so forth, so on. So the entire the manageability of those virtual machines is done by the hypervisor. Okay. And since we have this controlling system called a hypervisor, virtual machine migration is not a problem, or at least it should not be a problem. Obviously, we're going to talk about the different types of virtualization solutions, type 1 and type 2. When you have a virtualization or hypervisor type 2, then VM migration is a little bit more challenging. I would say it's not problematic, but it is a little bit more challenging than type 1 virtualization. Okay, but as far as virtualization, this illustration here shows exactly how it works, right? So imagine that in the traditional solution, right, without virtualization, you have the hardware, so you have the physical resources, storage, memory, CPU, network, right? And then on that bare metal machine, you install the operating system, right? Now that on top of that operating system, you're going to install the applications that you want to launch, and then you run the applications that you need, right? In virtualization, you have the hypervisor as the middleman here, let's say, that is controlling those virtual machines. And that is what makes it possible to run those different instances of a machine, right? So again, when you have the traditional deployment, on a hardware, you can only install one, or at least run at once, a single operating system. You can have more than one OS installed, but you can only run one at a time. With the hypervisor, you have this software here that is capable of deploying virtual machines, independent, separate virtual machines controlled by the hypervisor. So you may have, let's say, as you can see here, virtual machine 1, virtual machine 2. In virtual machine 1, you have operating system 1, and in virtual machine 2, you have operating system 2. So observe that in this example, we have 2 separate VMs running 2 different operating systems as well. And well, each of these virtual machines, they should execute what you want them to execute independently and separately, which means that it doesn't matter what are the applications and operating systems that you want to run. Okay. Now, there are different types of hypervisors. Okay. Again, you have here a representation of the traditional deployment, and these 2 other graphical representations here are representing the 2 different types of hypervisor, or 2 different types of virtualization. Here in the middle, you have hypervisor type 1. Here on the right, you have hypervisor type 2. So hypervisor type 1, you can observe that the hypervisor is deployed directly on top of the hardware. It is a firmware, okay? It is an operating system,
but it's not a commercial operating system. Again, it's a firmware, right? It has some very specific functions. It's supposed to be fast. It's supposed to be performable. That's why it's a firmware, not a fully deployed operating system. Okay? You can have an operating system, but not a fully deployed operating system. If it is a fully deployed operating system, then you have hypervisor type 2. So you have the hardware. On top of the hardware, you have the fully deployed operating system, whether it's Windows, Linux, Mac OS X, right? And then on top of that, you have the hypervisor. And then the hypervisor is controlling the deployment of the virtual machines that you want to deploy, right? So obviously, you can see that the type 2 is the one that does not perform so well. So if you want to guarantee performance and also security, you definitely want to go for hypervisor type 1. Okay. Now, obviously, there is an advantage on deploying hypervisor type 2. It's easy to deploy. It's easy to use. Okay. Hypervisor type 1, it's not that simple. So any person that knows how to install a software and use a computer can install a hypervisor type 2, such as VirtualBox. Now, if you want to use hypervisor type 1, well, that, let's say, a person that is not exactly a technician, an IT technician, or is not IT savvy, will have a difficult time deploying a type 1 hypervisor, okay? Such as the Microsoft Hyper-V. So here as examples, type 1, you have VMware vSphere, very, very common. Also VMware Solutions, ESXi, ESX, and the Microsoft Hyper-V, right? I would say that these, especially VMware vSphere and Microsoft Hyper-V, these are most likely the most common type 1 solutions that you see out there, right? Because of the number of tools, management tools that they have available, the resources that they deliver to you, that they provide to you, right? So for example, VMware vSphere and Microsoft Hyper-V, they support virtual machine migration. They support clustering. They support virtual machine migration on the fly. They support high availability. They support live snapshots, which are resources that are not that commonly available in most of the other solutions, okay? But as you can see, you also have some other alternatives here, such as the Citrix, Zen Server, and KVM. And in the next video, we are actually going to see how you can deploy KVM, but we're going to take a look at KVM combined with KEMU, okay? So as far as type 2, we have the most common one, Oracle VirtualBox. Another very common one is VMware Workstation. VMware Workstation is a solution that is mostly adopted by those that like the VMware products, okay? Let's say ordinary people, they tend to use Oracle VirtualBox. But we also have the KEMU and UTM, formerly known as Parallels. Okay, currently it is known as UTM. If you have a MacBook with the M1, M2, M3 chip, one of those, the virtualization solution that you're going to need is UTM. Okay. You can install VirtualBox, and depending on the operating system that you want to run on top of VirtualBox, of your VirtualBox hypervisor, it might work, but the best solution is UTM, because UTM will allow you to run Windows virtual machines running Windows, running Mac, running Linux, running FreeBSD, for example. Okay. But again, in our example, in our next video, we're going to see the combination of KEMU with KVM, because it is a easy to use solution. It's easy to deploy because, again, KEMU is a type 2 hypervisor, and as I mentioned, type type 2 hypervisors are pretty straightforward. They are easy to deploy, but at the same time, QEMU is just going to be the interface and the combination of tools to control a KVM hypervisor. Okay, so basically you have the benefit of a type 1 virtualization with the easy to use tools provided by a type 2 virtualization software. Okay. For the CompTIA Linux Plus exam, you also need to understand the networking modes or networking types when it comes to virtualization. And although these are not the only 3 networking modes, there are others. It basically depends on the type of virtualization that you're using, the solution, the virtualization solution that you're using. Okay, but basically all of those hypervisors, they will provide you with at least these 3 different networking modes: bridged, network address translation, and host only. Okay, so the bridged mode is more common when you're trying to deploy virtual machines that are going to be integrated with a let's say a traditional network, or with other virtual machines that are deployed by another hypervisor, which means virtual machines running on top of a different server, a different hardware. Okay, that's because the network interface card, as I explained before, for the machine that is the underlying physical machine running under the hypervisor here, its network interface card will work as the switch. Okay, and then you're gonna have virtual network interface cards for each of the virtual machines. But since you have a switch, this switch or this physical network interface card is simply receiving and forwarding packets, right? So the hypervisor or the underlying physical resource is working as a switch. So it's basically a bridge. Okay. Now you may also deploy a network address translation network mode. NAT mode also allows your virtual machines to communicate with the exterior world, the external world. So it allows them to connect to the network, to the public network, the internet, for example. It also allows them to send packets, send data to machines that are in the physical network or in another hypervisor, in another physical resource, but they are behind a NAT. Okay, so the hypervisor is working as a NAT router. It's encapsulating the traffic, which means that unless you make some configuration, the physical machines that are outside of this hypervisor, they cannot reach your virtual machines because they are behind a NAT. Okay, so the NAT type is mostly used when you simply want to have a network, a local network of virtual machines that are capable of connecting to the internet, for example, but they do not need to actually communicate with other machines outside of this hypervisor. And then you have the host only. So host only means, well, this machine is basically a host. You do not need network communication, right? It's basically used for testing and for security reasons. When it comes to production deployment, you're not going to use this. Definitely not going to use host only network mode. Okay, you may use network address translation if, again, you only want to allow these virtual machines to connect to the public network. But in as long as an enterprise deployment, bridged is the network mode that you see more commonly. Okay. The CompTIA Linux Plus exam also understands that you should know what the virtualization management tools that are available out there, or at least some of them, at least the most common ones. Okay. Now,
most importantly, you want to understand what a virtualization management tool is capable of doing. So again, as I mentioned before, you may have a product that is only capable of doing this and that. You have other products that are more advanced, more complex, and more complete. They might be able to do all of these, okay? So a virtualization management tool, generally speaking, they are capable of allowing you to manage virtual machines using that software. So what this means is, imagine that you have a bare metal server in a data center, right? And then you deploy a Zen server, or you deploy a VM or vSphere on that bare metal server, right? So you have a hypervisor type 1. Now, if you've never seen the interface provided to you when you are in front of that machine, that physical machine, it's similar to accessing the BIOS of your motherboard, right? It's very limited. It's a command text based look. It has a command line based look, command line based appearance, and not too many resources that you have in that environment. Now, what you want to do, you can use a command line interface to type commands that will say, well, I want to deploy a virtual machine with this configuration. I want to deploy a virtual machine that is going to boot using this .iso file to initiate the installation of this specific operating system. I want to freeze this VM. I want to migrate this VM. You can do that using the command line based interface. But you would have to, first of all, be sitting in front of that VM. And again, the interface is not that pleasing, right? It's not that easy to use. So you want to use a tool, first of all, a graphical user interface tool. You want to have a GUI interface, right? And also you want to use, because you want to use the cursor, right? And also you want to be able to manage that hypervisor, manage the virtual machines remotely from your laptop computer, from your office, for example, right? So that's why virtualization management tools are so important. And then you have the resources that they provide to you. So they should allow you to remotely manage the VMs, remotely manage storage, networking, taking snapshots, performing VMware migration, and also defining security. So you should be able to create a security profile saying, for example, I will allow users to remotely SSH into this VM, but these are the users that are accepted, or these are the IP addresses that will be able to do that. That sort of stuff, okay? They also implement monitoring, so they will actually create records about the execution of those virtual machines, right? And you have here a list of examples of virtualization management tools, okay? I list here the libvirt virt manager. So libvirt virt manager. So virt manager is the GUI interface that you can use in order to manage virtual machines, right? Specifically QEMU hypervisors, okay? Now libvirt is the module, the kernel module it's actually a set of tools, including the kernel module that you need in order to deploy virtualization in the kernel level using KVM. But as far as the graphical user interface tool, we're talking about virt manager, okay? Some other solutions, this is probably one of the most used ones, which is VM. So VM, the current deployment is called VM1.
There are other previous deployments, but that is the company. So VM currently deploys VM1. This is an amazing virtualization management tool. Okay, it allows you to not only manage virtual machines, migrate virtual machines, but it allows you to remotely configure your hypervisor to use a storage area network, for example, right? It allows you to perform backups remotely, backups of not only your virtual machines, but the hard drives associated, the virtual hard drives associated with those virtual machines. Very complete solution. Similarly, you also have the SolarWinds Virtualization Management, Microsoft System Center VM Manager. The Microsoft System Center VM Manager is a great solution, but obviously it was designed to manage the Microsoft Hyper-V solution, right? And you also have the Red Hat Virtualization, a more complete, similar to VM, a very complete virtualization management tool, but it was designed to be easily integrated to Red Hat Orchestration, which is another solution that provided by Red Hat. Okay? So as far as hypervisor, virtualization, virtual machine, this is what you need to know for the CompTIA Linux Plus exam. And as I mentioned in our next video, we're simply going to see how you can deploy, how you can install and deploy the KVM/QEMU combination. Thank you very much. Hello, welcome to our CompTIA Linux Plus certification preparation, and the idea of this video is to address a service that we have in Linux operating systems. Actually, this is a security/protection solution designed and deployed by Red Hat, and it's called Audit. The daemon is called Auditd. Okay, so the idea here today is to take a look at this service, obviously a required service for the CompTIA Linux Plus exam. Now, the Auditd service is a service that will basically monitor your system or monitor your files. And you can basically tune it, you can configure it, defining what you want to monitor. If, let's say, for example, if there is a specific file that should not be modified and not even accessed, okay, then you can configure Audit to monitor that file, and if any change or access to that file occurs, it will generate an alert. Well, basically this alert is sent to a log file, right? But obviously now it basically depends on how you configure your log system, but you can basically centralize those logs and use any graphical user interface solution that will show your log entries in a more satisfying manner. Okay, but what matters here is that that specific event will trigger a notification. This notification will be registered, will be recorded in a log file. For the CompTIA Linux Plus exam, you do need to not only understand what the Auditd service does, what you use it for, but you have to have at least a basic understanding of its structure, such as the command that you use to configure and the structure of a rule, an Auditd rule. Okay, so that's what we're going to do here today. Well, obviously, you want to make sure that your that the Auditd service is installed, and basically you just need to, obviously it will depend on the Linux distribution that you're using. If you're using a Debian based, such as Ubuntu, that's the one that I have here, then you're going to use dpkg. If you're using a Red Hat CentOS based Linux distribution, you can use RPM. Okay, but again, as you can see, I have Auditd installed here. That's the version that I have. If you don't have it if you don't have it installed, you can basically run the apt-get install Auditd. Okay, once you have it installed, the first thing that you want to make sure is that it is not only running, right, but also make sure that it is
it has been configured to be initialized during the boot process. Okay, so I am going to verify the status here. So systemctl status auditd, and as you can see, it is active and running. Okay, the log file is in the /var/log, and in there you have the audit directory, and in the audit directory you have the audit.log log file. Obviously, this is configurable. You can actually define where those records will be stored, what is the log file. You can configure it in the configuration file for the Auditd service. Okay, but obviously we're just taking what is configured by default. Okay, now before we actually, so let me just briefly show you at least the last lines of the audit.log file. And as you can see here, you have the type of log, right? Well, a service has been stopped. There is a message here. The message is, so PID1, user ID 0, that's the root user. And it is, the message is this message here, right? And what it's doing is it's executing the /usr/lib/systemd command. That's because I just used the systemctl command in order to verify the status of my Auditd service. Okay, but as you can see, it may generate a bunch of it may be very verbose. Okay, and obviously you can configure this, but that's not the goal for the CompTIA Linux Plus exam. They do not want to see if you can define or tune the verbosity of the log file. They're just more concerned about your capability to understand how Auditd works and how you can define rules. Okay, so when it comes to defining rules, a command that you want to learn, you want to understand, is the auditctl. And as usual, right, before we actually look at commands, I strongly recommend that you take a look at the main page. Again, this goes to any tool that we use, okay? Always take a look at the main page for that specific tool. So if you take a look at the auditctl main page, okay, it's not that long. It should not take too much of your time, but we first need to understand what it does. So as you can see, the auditctl tool is a utility to assist controlling the kernel's audit system. So observe that the audit system, Auditd, is a kernel audit solution, okay? And you have many options here. Obviously, I'm just going to briefly comment on the most important ones. And the first one, obviously, it has a standard default configuration, and you can change it in the Auditd configuration file, okay? But the first option that we see here is the -b option, and after -b you can use a number. So as you can see, it set a max number or limit number of outstanding audit buffers allowed. Okay, the kernel default is 64. If all buffers are full, the failure flag is consulted by the kernel for action. So basically what it's saying is, well, depending on the number of rules and how much traffic, the volume of data that should be processed by Auditd, all those processes or all those audits, all those analysis, they will go into this buffer, right? And here you're defining the size of that buffer. Obviously, it is recommended that you do not leave the default option here, which is 64. That's not good at all, okay? But we're actually gonna see that. Going forward, you have obviously some other important options here, but again, we're just gonna focus on the ones that actually matter. And the first one is the -l option. Okay, so auditctl-l, it will list all rules, one per line. And again, that's one of our objectives here, right? Learn how we can create a new rule for the Auditd system. So if you want to verify the list of rules that you have, you can simply run auditctl space -l. Okay. Another interesting option here is the -s. So it reports the kernel's audit subsystem status. Now, not only that, it's not only show you what the status is as far as, well, is Auditd running or not? Is it stopped? Not only the status, but it's a, let's say, it will provide you with information about that specific service. Okay, so for example, we just saw the -b option. It will show you what the value is set for the size of the buffer, the limit of the buffer. Okay, now as far as creating rules, from here on, as you can see, rule options, you have the most important options. Now, obviously, first let's understand what a rule is. A rule is the definition of what kind of audits are going to be conducted, what kind of analysis as far as data that should be processed will be conducted by Auditd. So, for example, like I said, if you want to monitor a specific file, and if that file changes, you want to generate an alert, right? Or you want to generate a notification. Well, you need a rule that is defining how that specific type of data is going to be matched. So, for example, if you want to verify, if you want to audit every time that a user account is changed, if you want to generate an alert every time that a user's password is modified, right? You're going to need a rule for that. If you want to generate a report every time that a specific configuration file is accessed, you need another rule for that. So that's what the rules are about. Now, there are basically three different types of rules, okay? You can create a watch rule, or you can create a syscall rule or system call rule. What is the difference between those two rules? Back in the day, and this is probably what you're going to see in the CompTIA Linux Plus exam, but back in the day, Auditd it only supported the file configuration or the watch configuration, okay, or the watch type of rule. And basically, the watch type of rule is a rule where you define a file or a directory, and you say, well, if this file, for example, is accessed, modified, deleted, or if a file is created in this directory, if permission for execution is assigned to this file, okay, any kind of permission is changed, okay, then it will trigger an event, okay. Now, the system call is a little bit different, and it's fancier, right? Because it will rely not on the user space, but it will rely on the kernel space. Every time that an event occurs, there is a system call that is associated with that specific event, okay? For example, if you simply send a ping from your machine to a specific destination, that is going to open a socket. There is a system call that the operating system is going to trigger in order to open that socket. Well, if there is a system call associated with it, you can create a rule based on that system call, or known as syscall. Considering that syscall is much more, let's say, manageable than controlling permissions or attributes associated with a specific file, that's why Auditd switched that previous watch type of audit to the system call type of audit, okay? Now, if you create a system, if you create a watch type of audit rule, depending on the operating system, depending on the distribution, it will basically say, hey, you are using watch type of rules, which is fine, you can do that, but just be aware that it is deprecated. You should switch to the syscall type of rule, okay? But it's going to work just the same. Okay, When you're creating a rule, you first use the -A option. -A option means, well, you want to append a new rule to the end of this list. If you want to append a new rule, I'm sorry, not append, but if you want to add a new rule to the top of the list, you can use the -A, okay? So as you can see, you can basically say, okay, I want to add, and then what specifically is this type of rule that you're trying to append? So append the rule to the end of a list, right, with a specific action. So please note that the comma separating the two values, okay? So for example, if you do, let's say, if you combine always, let me scroll down and then I'll go back, always with exit, which is very common with exit, okay? You are basically saying, well, the action always means I always want to generate an alert or create a new log when this type of syscall occurs, or when a type of traffic, a type of data, or a type of event matches this specific rule, okay? So basically, that's what you're going to use every time that you append a new rule, right? It will be the always type of action. Now, if you take, for example, user, you're going to add a rule to the user message filter list. This list is used by the kernel to filter events originating in user space before relaying them to the audit daemon. So what it means is this will create an audit rule that will match events that are triggered and controlled in the user space, in the user domain. That's why usually you want to use exit. Exit means add a rule to the syscall exit list. This list is used upon exit from a syscall to determine if an audit event should be created. In summary, what it means is every single time that a syscall, a system call, which again happens in the kernel space, is triggered, it will compare, once the system call is executed, right, it will compare this rule. Exit means once the system call occurs, right after the system call occurs. Well, right after the system call occurs, it will always compare that specific system call, that specific event with this rule. If it matches, it will generate a log, okay? Now a few other, another very important option here is the -F. -F is used to implement filters, and there are so many different types of filters, okay? But most commonly, you're gonna have the arc type of filter. This is, let's say, okay, I want to create a rule that will verify if a specific event occurs, but it also requires that the architecture is a 32-bit, is a 64-bit architecture. So you can define that. You can also associate that with the user ID that is triggering that event. That's what the AUID stands for. If you want to match that with a directory, right, you want to use the dir option. So basically you're doing -F space dir equals the full, okay, not relative, the full path of a directory to watch, okay? Is basically the same thing as using the -W option. The -W option is the option that you use when you want to implement the watch type of rule, okay? But this is combined with the -F option, which is mostly used when you're dealing with system calls, not with the watch type. Okay. Another one, also very interesting, EXZ, absolute path to application that while executing this rule will apply to. It supports equal and different operators, not that you can only use this once for each rule. Now, what it means is, let's say that I have a binary file, an executable file, right? And every time that that specific executable file is invoked, is executed, I want to generate an alert. I want to generate a log record about that. Okay. For example, the passwd command. Every time that a user is trying to change the password using the passwd command, I want to know. I want to generate a record of it. Well, you can use the -f, capital F, exe equals /bin/passwd. Every time that someone tries to change the password, you're gonna see that log. Okay. This is very much used because, well, when a hacker or someone is trying to, someone was able to get access to a machine, one of the first things that attacker is going to try to do is to change the user's password. That is a very common situation, okay? And obviously, like I said, I strongly recommend that you take a very good look at these options here. You can also do according to the path of a file, the permission, okay? As you can see, you have many options. Now, another very, not only important, but actually required option here is the -k option. The -k option is the option that you use in order to set what is called a key name to that rule, okay? So, for example, let's say that every time I want to create a key name that will refer to any file that is, every time that I see a file that I want to monitor, I want to generate a record about that file or those files being changed. So I can create a key name called file change. So, for example, if a specific configuration file is accessed or changed, the shadow file is changed, and then another specific file in the home directory is changed. Just 3 examples of files here. If any of these 3 files are changed, I have 3 different rules. I associate those 3 different rules with the same key name. Or if you want to create 3 different key names, you can. But the idea is, in order to make it easier for you to perform a search according to the type of rule, you should use a specific key name for that group of rules. What that means is, again, if any of these 3 files are changed, it will not only it will generate an entry in the log file, but it will associate that with the key name that I just defined. Let's say file change, okay? Then when I want to verify in my log file if any of those files have been changed, instead of analyzing the content of my log file, seeking or searching, filtering for those specific file names, I can search for that specific key name. Since that key name, file change, is associated with those 3 files, if any of those 3 files is changed, I'm going to see just by searching for that specific single key name. Okay? And again, if you are dealing with the watch type of rule, you need to use the -p option, okay? The -p option stands for permission, but you are actually not only dealing with permission, although that as well. So R means read, W means write, X means execution, and you also have the A for attribute, okay? So what this means is, if I create a watch type of rule, okay, meaning I want to watch a specific file or directory. If this file or directory is read, if it's written, modified, if it's executed, or if its attributes are changed, then this should generate a log entry, okay? And remember that the attributes of a file, you have many attributes, right? You have what is called the MAC time, such as the modification, creation, access time, but you also have the owner of a file, right? The group owner of a file. You have many attributes assigned to a file, okay? Now, again, describe the permission access type that a file system watch will trigger on. This is deprecated. Convert watches to the syscall form. Okay? On the other hand, every time that you want to create a syscall type of rule, you want to use the dash capital S. Remember that the dash lowercase s is used to check the status. That's not the case here. Okay, so if you want to create a syscall type of rule, you're going to use the dash capital S option. Okay? Now, and then you define the type of syscall that you want to monitor. Okay, you want to audit. Well, as I mentioned, the user that is accessing a file, the user that is executing a file, whether a binary is being executed, if you are dealing with a network connection or a socket that is being open, or if you're dealing with the status, the state of a specific process, right? If you want to, let's say, I want to monitor a specific user, but I do not want to use a username. I want to use a user ID. You can do that as well. So every time that anything that happens in the operating system that is managed by the operating system, and when I say operating system, obviously I'm referring to the kernel. So anything that is controlled by the kernel will require a syscall to occur, right? So basically you can create rules, audit rules for basically anything that happens in the system. You just have to figure out what syscall you should use for that specific situation, okay? And also, if, again, going to the watch option, if you want to watch a file, right, you want to use the dash W option to define the path to that file. Okay, and here you have just a couple examples, right? So the Auditd-A, remember, I'm appending a new rule and I want to always verify when a syscall is done. Okay. Specifically, I want to associate this type of audit rule with 64-bit architecture, and the specific syscall is open at, which is when a file is being opened. Okay. And then the dash F option to define the filter. And the filter is success equals 0. So what does it mean? The success type of filter defines whether that specific event returned a successful status or not. If success equals 0, that means that it failed. So in this case, if I'm saying, hey, I want to audit every time that a syscall is made and that syscall is opening a file, and if it returns success 0, that means if someone tries to open a file and that person cannot do that, right? That user cannot do that. Well, why was not this person able to open that file? This is an event that probably should be monitored. Okay, same thing for truncating a file. If someone tries to truncate a file but cannot do that, well, that may be also a type of attack. Okay, so these are just a few different examples. You also have a few other examples here. If we go to the end here, you can see some other examples. Like I said, based on the PID, right? As you can see, Auditd-CTL-A always exit as usual. Dash capital S means to any syscall, right? It doesn't matter what type of syscall it is. To any syscall, if the PID, the process associated with that event, is this number, then I want to generate a record. So let's say that you want to monitor a specific process, right? If that process executes any kind of syscall, then you want to generate a log. Similarly, to any type of syscall as well, if this file or executable file /usr/bin/ls is executed, I want to generate a log event. What this means is if anybody at any point in time lists the content of a directory, runs the ls command, it will also be
recorded. Okay. Lastly, let's just take a look at this last option here, or this last rule: auditctl-a always comma exit -s open at. So to see files opened by a specific user, a UID. Observe that we are using the user ID here and not the username, okay? So every time that the user that has UID 510 opens a file, that should generate a log record, okay? Again, as I said, it is strongly recommended that you take a look at this main page here. This is a type of tool that is you most likely see in your CompTIA Linux Plus exam. Okay. Now, in our next video, we are actually going to see how we can just define. Okay, I have these few examples here, right? How can we actually solve these problems? So thank you very much. See you in the next one. Hi, welcome to another CompTIA Linux Plus preparation exam training. And in this video, we are going to address some new topics that were added to the newest version, to the CompTIA Linux Plus newest version. So although the Linux Plus exam is an exam that is focused on testing if you know the Linux operating system, if you know how to operate, how to manage the Linux operating system, given the fact that information security and cybersecurity became obviously so important, right? It's very difficult to manage an operating system without having the basic understandings surrounding information security and cybersecurity. Therefore, they included this new topic, which is malicious code or malware, but mostly concepts surrounding malicious code and different types of attacks. Okay, so let's start with malicious code and how to detect these, and also how to prevent from getting infected by these different types of malicious codes. But obviously, before we address the defense techniques, we need to understand what a malicious code is and its different types. So malicious code, malware. So malware is short for malicious code, okay? And as the name explains itself, it is pretty self-explanatory, right? Basically, it is a code, which means it's an application, okay, that was designed to cause some sort of harm or conducting malicious activities. So to give you a few examples, it can go from harmful attacks or harmful activities, such as changing a file or even destroying a file, or disrupting a specific machine, right? To simpler stuff that is not necessarily or directly causing harm, but it is an undesired activity, such as installing a backdoor, okay? And obviously, we'll talk about backdoors as well. But anyways, that is broadly the concept of malicious code. But again, there are many different types of malicious codes, right? Here you have a list of a few, at least the most common ones, but these are not the only types of malicious codes that are out there, okay? Just the most common ones, and probably the ones that you may see in your exam. So let's start with the three most traditional, most common ones: viruses, Trojan horses, and worms. Well, we could say that basically viruses and worms, they are more related, and it's very common to see people using virus or worm interchangeably, but we need to understand the differences. Although the differences as far as concept are not that many, there are not those many differences, but as far as the practice, the applicability, and what it does, yes, they differ a lot. So first of all, a virus is an application that needs to be attached
to a host file, not only a host device, but a host file. That's why you say, well, this file is infected. Okay, because a virus does not work if it does not infect, if it doesn't attach itself to a file. Also, the reason why it's got to be attached to a file is because triggering that file or executing that file, that file is what will trigger the activities that are supposed, or the code that is supposed to be executed by the virus. On the other hand, a worm is an independent malware. And what that means is, first of all, it does not need to be attached to a file, so it does not need a host file. The worm is a file itself, an independent file. And also, it can dissipate, it can propagate independently as well. What that means is, first of all, it doesn't need to be executed by the user, okay? It can execute its code by itself, and most of the times it can and it does propagate through the network. So a very common type of worm is a worm that is capable of reading your address book or your contacts, and it will send emails to those other contacts that you have in order to infect those machines. Obviously, it can infect those machines by, well, let's say a user actually downloaded that file, but most commonly that's not how it works. Usually worms, they propagate leveraging a vulnerability. So for example, if you use a Windows operating system version XP, so Windows XP, right? There are some vulnerabilities in the Windows XP, there are some vulnerabilities in Windows 7 that will allow some types of worms to leverage that vulnerability and infect those machines through that, let's say, vulnerability, that available vulnerability. A Trojan horse, on the other hand, is also a software, it's also an application, but its main characteristic is that it's capable of still remaining idle and disguising itself until a specific event or a specific date, for example. Any trigger that is coded by the malware writer, until that trigger is triggered, which will invoke the execution of that Trojan horse. So it's called Trojan horse because it goes back to the Greek mythology, where you have that wooden horse, a wooden horse that was used to hide soldiers until the right moment came, the right opportunity came to execute the attack. Okay. Some other types, you have adware. It's an application you install, an app, for example, but that app will always show you an advertisement. A spyware, also associated with an application that most of the times, not always, but most of the times you install an application, but that application is also installing a spyware, which is another application that will monitor what you're doing, for example, or will perform itself as a keylogger, which means it will track the keys that you are pressing in your keyboard. There are so many different types of spyware software. A ransomware, which became very, very popular, is nothing more than a malware that will encrypt, cipher files, folders, or even an entire hard drive in order to decrypt or to decipher that specific file, you need the key, right? A secret key. Now, the malware writer or the person that was able to infect your machine or that target machine is the one that actually possesses that key. Therefore, if your machine is infected by a ransomware, that ransomware ciphered a file, you want to decrypt that file, you're going to need that key. The attacker will request a ransom. So you have to pay a certain amount to get access to that key. That's why it's called a ransomware malware.
Also, some very popular ones, backdoor, rootkit, and botnets. A backdoor is nothing more than a software that will maintain an open door to allow access, usually unauthorized access or undesired access at a later moment. So it's a technique that is used by attackers to make sure that they can get access to the target machine at a later moment, and ideally that access will not be, that remote access will not be tracked. It won't be noticed by the host. A rootkit, on the other hand, is a type of malware that also allows unauthorized access, but it not only allows unauthorized access, but it allows a remote control by the attacker. So it's similar to a backdoor. The difference is the backdoor will only maintain an open door for a remote access. A rootkit will do that as well, but it will also allow that attacker to perform, to send instructions, to send, for example, commands that the target machine is supposed to execute. And associated with a rootkit, a type of attack called botnet most of the times leverage rootkits to perform attacks using a botnet. Okay, so the idea of a botnet is to create a network of bots, a network of zombies. These zombies are host machines that they're not necessarily the target, but they must be used as, they will be used in a synchronized attack against a specific target. So for example, let's say that I want to perform an attack against a server, but this is a powerful server. If I simply try to flood that server using 1, 2, let's say 10 machines that I do have control simultaneously, well, that target can still manage that the traffic that is being sent to it, the requests that are being sent to it, right? It is not going to flood because of those that traffic that is coming in simultaneously. Now, if I can control, let's say 10,000, 50,000 machines and perform that same, send that same type of traffic simultaneously, then the chances of flooding that target machine will increase because, well, dealing with 50,000 machines at the same time, 50,000 requests at the same time is not an easy task, right? But how am I going to synchronize that attack using 50,000 machines? Well, I can try to install a rootkit in 50,000 random machines, right? And use them as slaves or zombies or bots, robots, okay? Therefore, I am creating a network of bots. That's why it's called a botnet. But like I said, in order to control those zombies, I will need a rootkit, because the rootkit is what will allow me to perform, to control those machines remotely. And a logic bomb is nothing more than a malware where you can define when that specific activity is supposed to be triggered. So as you can see, you can actually combine rootkit, logic bomb, and botnets to perform different types of attacks. We're going to talk about a distributed DOS attack, distributed denial of service attack. DDoS attacks are most of the times triggered by the combination of these three. So I want to create a network of bots. In order to control those bots, I want to install a rootkit. But that is not just any kind of rootkit. It is a logic bomb rootkit where I will define on this date and this time I want to send the command to those zombies, so that those zombies at that specific date and time will trigger that attack simultaneously. Well, now again, one of the main ideas of having understanding the concepts of malicious code is because you want to understand how to respond to detections and how to detect and respond to malicious code attacks, right? So here are a few steps to minimize possible attacks. You want to ensure that all patches for the operating system and applications are installed, obviously, right? So you want to make sure that your systems are up to date. You also want to limit the services that are running on the system. And this is something that is, although it's very elementary, you still see many services being provided by a machine, while that machine does not need to provide that kind of service, right? So a very simple example, since we are addressing the Linux operating system, it's very common to see, especially nowadays, that the Ubuntu distribution, for example, became so popular. People, they install the Ubuntu distribution, which is an amazing distribution, right? But the default installation will bring a graphical user interface, such as KDE, GNOME, Mint, whatever the interface is, right? But that is supposed to be a server machine. It should not be used by an end user. Therefore, there is no need to have a graphical user interface. Although, except for a few very specific situations, but most of the times that GUI interface that is there, right, should not be running. Well, that is a vulnerability because you have services. Remember that the graphical user interface is actually a network service, right? If you're using the X11 or Xorg, right, you have a network open port available. And even if it's not a network port, even if it doesn't allow network communication, you have software that is running, a service that is being provided without necessity. So you have vulnerability there that may be exploited at some point. You also want to limit public disclosure of private information about the organization and its computing resources, obviously, right? Because information that is public can be used in order to gather information and find out a username and password, identify credentials, for example, right? Or perform social engineering attacks. And again, you want to patch all vulnerabilities if you identify those, which means that you also need to do what we are going to discuss in our next video, which is vulnerability management and vulnerability assessment. So you want to patch all vulnerabilities in order to close any entry point that might be available for different kinds of malware. Right? Now, I also mentioned that aside from malware, there is also some other types of attacks. And most of the times, these attacks, they use some type of malware at some point. But obviously, we need to understand what those types of attacks are. I already talked about the DDoS attack, right? It's a synchronized attack where the idea is to bring a service down. So that's why it's called denial of service. You want to force the target machine to start to deny providing the service that it provides, right? But it's very difficult unless you identify a vulnerability that can be exploited, a software vulnerability associated with that service that can be exploited. Most of the times, what you want to do is to overflood that machine up to a point where the machine is there's so much traffic, there is so much, the volume of information that it's dealing with is so high that it will have a hard time managing such traffic, such CPU processing, right? And it won't provide that service anymore. Now, in order to do that, you want to perform a synchronized attack. A buffer overflow is a type of attack where you are leveraging a vulnerability, whether it's a vulnerability associated with the application or with the operating system itself or the network protocol that is involved, up to a point where you cause the buffer, the memory that's being allocated to that application, okay, you force it to overflow so that the data that is associated with that original or that target application will overflow to a space of memory that is not managed and is not associated with that specific application. It will overflow and it may cause the application to fail, even the operating system to fail. Spoofing is nothing more than faking, right? So a common type of spoof is the IP spoof and the ARP spoof. Let's say that the most common one is IP spoofing. In IP spoofing, I am basically lying to an endpoint saying, okay, I have this IP address. So let's say that IP A is communicating with IP B and I am IP C. But instead of saying that I am IP C, I notice that there is a communication between IPs A and B, and I will send a packet to IPB saying I am IPA, and then IPB will start to exchange information with me, thinking that it's exchanging data with the original IPA machine. TCP/IP hijacking is another technique where you leverage the way that the TCP/IP stack establishes communication. One of the most common ways of controlling a TCP/IP session is by using the TCP/IP session ID, right? Well, if I can identify what the TCP/IP session ID is in a specific communication, I can try to interact with one of the endpoints saying, okay, here is our session ID. Well, then the target machine might believe that yes, so you are the other endpoint to which I am communicating with, because I identify this session ID associated with our communication. A man-in-the-middle attack is a type of attack where you also have communication between endpoints A and B, and then there is another entity, which is the attacker, that can capture that traffic. Now, this man-in-the-middle attack can be passive or active. What that means is you may be passive if you are simply capturing the traffic that is being exchanged between those two endpoints, or you can start acting as if you are one of those endpoints. Obviously, you have software exploitation, which is nothing more than identifying a vulnerability associated with the software and exploiting that vulnerability. Some other types of attacks: social engineering. Obviously, there are many different types of social engineering attacks, such as dumpster diving, eavesdropping, piggybacking, and so many others. But the main point here is to understand what social engineering is, and it's nothing more than identifying a way of extracting information from human beings. So let's say that, well, I am targeting a specific server, right? I know that this server is company A's main server. If it's company A's main server, there is a very high probability that the user accounts are in that server. Well, so I can start to gain remote access using credentials. So let's say that at some point I identified that yes, I can perform remote access to that machine. I can get a remote access to that machine as long as I have a user's credential. Okay, now what are the users? And obviously, what is the password associated with that user account? I can try to perform social engineering attacks to put together that kind of information. For example, I can use social media, social networks such as Facebook, Instagram, and so many others, Twitter, right, to identify what the user account is. But I can also use that to try to identify what the password might be. More information I can put together, bigger the chances of me identifying the user's password. Flooding, as I already explained, it's nothing more than sending too much data to a machine so that up to a point where that machine is not capable of responding to those requests anymore. Password sniffing,
although it seems like something very old because most protocols, network protocols nowadays, they use TLS, SSL, so they are encrypted, right? But for your surprise, let me give you an example of a very common network protocol that does not, by default, does not implement encryption, and it can be, a password can be sniffed. That is the FTP protocol, the File Transfer Protocol. So if you use a software such as Wireshark, you can sniff a FTP transmission password. Privilege escalation, that's when you get access to a host with a limited account, such as a guest account, and then you try to identify ways of getting your way up in the as far as privilege. So you try to escalate privileges. Brute force is nothing more than trying combinations of username and password, most of the times, right, in order to get remote access. And replay attack is more common in Wi-Fi networks. A replay attack is an attack where you capture data and you try to, you actually replicate that data that you captured, you make copies of it, and you replay that traffic several times so that you can observe how the other endpoint of your communication will respond to that data that you sent, and based on that response, you are capable of identifying identifying a password, identifying a hash, identifying what the security implementation is. Right? So as far as security deployments in order to defend against these types of attacks, again, very common things, right, such as physical and digital access control, authorization processes, as we already addressed in previous videos, automatic logoff, account lockout. So let's say if this, well, there is actually two different types of account lockouts that you can do here. You can determine, let's say, well, if a user tries to log in and the password is typed wrong 3 times, then it will be locked out for 5 minutes, for example. Or you can actually, if you identify or if you suspect of that activity, you can send that account to a much more limited environment. Obviously, you want to monitor logs because the logs will tell you what is going on, right? That is a resource that will put together a lot of information that you can analyze. You also want to make sure that your the time, your clock is synchronized, because if it's not, then your logs are not that reliable anymore. I mean, if the clock is not right, how are you going to identify or how are you going to rely on the timestamps that are shown by your log files or the MAC time associated with your files? And obviously, you also want to make sure that you implement pen testing. So you want to make sure that you are constantly verifying if your systems, if your infrastructure is reliable, is secure, okay? And that is something that is achieved by one of the main ways of achieving that is performing penetration testing. Now, since logging is so important, obviously you want to make sure that you have monitoring solutions in place. IDS and IPS, or if you prefer, IDPS systems are very important in order to achieve that. The idea of an IDS is to have a system that is capable of identifying anomalies, which are tasks or events or traffic data, traffic packets that are not seen as ordinary, regular, or normal packets. They are classified as anomalies. Okay, observe that an IDS or IPS system is not necessarily identifying attacks. They are identifying anomalies. Again, you want to make sure that you have log servers. You don't want to rely on logs that are independent, meaning you have a log file in host A, another log file in host B, another one in host C. Obviously, because they are not synchronized, but that's not the main reason. The main reason is because, well, if an attacker gets access to a target host, the first thing that they will do is to wipe out the logs, right? If those events are being sent to a remote server, a log server, then if the attacker wants to wipe out the logs, he or she will have to get access to the log server as well. And obviously, you want to have a CM tool that is very, very useful and very powerful. And I would recommend Splunk. But additionally, network monitoring tools are also very useful in order to give you an idea of what is going on with your network. So you want to monitor the behavior of your network. And here is just a list of a few tools that you can use in order to do that. So here are some examples of network monitoring tools. CACT, Zabbix, Nagios, OpenNMS, PRTG. PRTG is for the Windows operating system specifically. Okay, not least important, file integrity techniques and file integrity checkers are very, very useful and important. Nowadays, the Advanced Integrity Detection Environment Aid tool is probably the one that is most widely adopted because it's similar to Tripwire, but much, much easier to use. Okay. So as powerful as Tripwire, but much easier to configure and to follow up. Okay, so basically what these tools do is you say, okay, so let's say that I have this new Linux machine, right? Since it's a brand new Linux machine, I am going to change a bunch of configuration files. Many changes will be made to this system. But once the configuration is fully done and the machine is, let's say, at a stable state, I'm not going to change much. Well, obviously there will be some changes, but I do not want to change much. I can tell Tripwire or Aid, okay, this is what the machine state should look like. I want you to take a snapshot, and if anything changes, let me know. So it's basically going to verify the integrity and detect the integrity of files. Not necessarily if a file changes, that is an attack, but I will be alerted. I will be notified about that change. So let's say that a configuration file changes. Okay, who changed the configuration of this file? Okay, I can go there and inspect, but I will be notified about that. A rootkit hunter such as RK Hunter, that's also freely available for the Linux operating system. It is a tool that will basically try to identify if there are rootkits installed in your machine. And a signature validation tool is also very important because you can basically define, okay, I am going to start signing my files, okay? And you can verify the signature. So if there is a file or an email, for example, right, that is not signed, or if it's been signed, but it is a signature that I do not recognize, I will be able to identify that, which means that, well, if it's not signed the way that I expected it to be, then there is something wrong here, or there might be something wrong here. And we are actually going to take a look at one of those tools, which is the GNU PG, the GPG tool. And lastly, you also want to make sure that in order to destroy data, you are using a secure data destruction tool. Okay, well, obviously, if it's a physical resource such as paper, you want to use a shredder, but you also have the shred tool. But personally, I would recommend using DD. So let's say that there is a hard drive that you want to dispose. Before you dispose the hard drive, you want to make sure that you were wiping out all the data that is there. Now, if you format the partitions, that is not going to wipe out the data. It's just going to wipe out the translation table or the address table, the table that the operating system uses in order to identify where each file is stored physically in that hard drive, right? But any recovery tool, data recovery tool, is capable of, or at least is able to try to rebuild that address table. If you really want to wipe out the data, you want to override the data that is in there. And the DD tool is probably the best tool to do that, because it is going to perform a bit by bit or byte by byte override. Meaning you can say, DD, I want to rewrite the data across this hard drive, and I want to going from block 1 to the last block, to sector 1 to the last sector. I want to write bits zeros. I want to write bits 1. Okay, so you're basically overriding the entire data of that hard drive. Okay, so as far as malware and attacks, that's what you need for the CompTIA Linux Plus exam. But like I said, you also need to understand vulnerability assessment, and that is going to be our next topic. Thank you very much. Hello, welcome, and as discussed in our previous video, aside from malware analysis and how to defend against malware, another topic that you must understand for the CompTIA Linux Plus exam and its newest version is vulnerability scanning, vulnerability analysis. Obviously, there is a big difference actually between vulnerability management, vulnerability assessment, vulnerability analysis, and vulnerability scanning. The CompTIA Linux Plus exam is more focused on testing your understanding of vulnerability scanning. And what that means is that you obviously don't need to understand all the steps, the phases involved in vulnerability management or vulnerability assessment. You just have to focus more on understanding the practical implementations to identify vulnerabilities. So that's what vulnerability scanning is about, okay? And you also see that it's not complex at all. It's actually very simple. The whole goal here is to show you what a vulnerability scanner does when it scans for vulnerabilities, when it tries to identify vulnerabilities. And although there are many tools that are out there to do that, and a very simple one that you can use to perform vulnerability scans is Nmap. Okay, Nmap, the network map, the most common network mapper tool, is also capable of scanning for vulnerabilities. You obviously need to use some plugins, some add-ons that are written in the Lua language, but you can attach those plugins to Nmap to perform vulnerability scans. However, there are two main vulnerability scanners that are widely adopted nowadays. Those are Nessus and OpenVAS. They are very similar. The way that they behave is very similar. Their plugins are very similar. Okay, I would say that the main difference between those two is that OpenVAS, as the name says itself, it's an open software and it's also free, whereas Nessus is not. It's not free. Actually, there are many versions of Nessus. You can use Nessus, a trial version, which is also a free version. The problem with that is that you will have access to a limited number of plugins, so your vulnerability scans will be very limited and outdated as well, because those plugins, the number of plugins is limited, and they are not being revised. They are very old. Okay, but what matters here is that you understand what a vulnerability scanner does. And again, it's pretty simple. What it's going to do is it will use these so-called plugins, okay, that will test specific vulnerabilities. They will try to identify specific vulnerabilities. So going from very simple stuff such as, well, there is a plugin here that will verify the version of your web server. Let's say that you have a Apache web server running. What is the version? If it's a a very old version below 2.4.4, then there are some vulnerabilities, known vulnerabilities associated with that specific or those versions, and it will identify that and obviously alert you, notify you about that. It may even go to more advanced plugins that will not only verify version and try to identify known vulnerabilities, but it will actually tackle it. They will actually attack. Those are called active vulnerability scans. They actually deploy the attack. So, for example, how can a vulnerability scanner verify if your the user accounts that exist in the system, if they have vulnerable password or weak passwords, right? Well, it will actually try to execute a brute force attack. So again, these are the plugins. The plugins will do that. Now, it's not only about identifying the vulnerabilities, but also scaling, okay, identifying the severity of these vulnerabilities. So broadly speaking, this is what you get when you use a vulnerability scanner such as Nessus. It will provide you with a summary of that specific vulnerability, but it will also provide you with more details about it, how you can fix or what is the solution to it, how it came to the conclusion that this is a vulnerability. So you have, and when that plugin is executed, the plugin will generate an output, a response, okay? References so that you can learn more information, you can study more, you can understand better what that vulnerability is. And what is more important as far as vulnerability scanning is the risk and vulnerability information. So just a very brief example, as I mentioned, if you have a Apache that is lower than version 2.4.46, then, well, so here it is. The version of Apache HTTPD installed on the remote host is prior to 2.4.44. It is therefore affected by multiple vulnerabilities as referenced in the 2.4.46 advisory. Okay, and then you have the common vulnerability exposures unique identification number that uniquely identify this specific vulnerability and the other ones. Again, solution, very simple, you just upgrade it, but and again, a solution, output, reference, but what matters the most here is the CVSS score, okay, and also the CVSS vector. As you can see, there are two CVSS scores here. You have the CV, where is it? The CVSS v3 base score, and you also have the CVSS base score. This is the CVSS 2.0 base score, okay? This score here, or these scores, are the scores that identify the severity of that vulnerability. The higher the vulnerability, more severe it is. Now, observe that this is the CVSS score, right? There are many different frameworks. We're just using the NIST CVSS as an example. There are many others, okay? But just so that you understand how it works, depending on the output, on the result generated by the plugin, the framework will use a few metrics to try to identify the severity. And here are the metrics used by the CVSS score. So just an example, the CVSS scoring system, as you can see, will use these metrics here: attack vector, access complexity, authentication, confidentiality impact, integrity impact, availability impact. And then you have a description of these metrics. But as you can see, the complexity associated with the deployment of that attack, okay? The access complexity, if there is authentication associated with that system, the vulnerable system, right? If confidentiality is breached, what is the impact of the confidentiality? What's the impact on integrity of the information? What is the impact on the availability? maybe this service, this host, will become unavailable if this vulnerability is exploited. So these metrics, they will have a score. As you can see, the attack vector will have the score here. If it's just a local attack vector, meaning it just impacts on the local machine, then you have this score. If it impacts on the machine and it's adjacent, its neighbors, you have this. If it's a vulnerability that may impact on the network entirely, you have the highest possible score for this specific metrics. Obviously, the CompTIA Linux Plus does not require you to understand the CVSS scoring system, and even less so its metrics. But it's just important that you understand how it works. Again, each framework, they have their own methodology, but broadly speaking, they will all have some scoring system that will, at the end, as you can see, give you that base score like this one. Okay, so this score will tell you what the severity is. Oops, I'm sorry. It will tell you what the severity is, so that you then can understand how critical the severity is. That's the first thing. With that information in hand, you now have a list of the vulnerabilities that exist. Well, how are you going to address them? That's why you have this scoring system, because you should address the more severe vulnerabilities, the more critical vulnerabilities to the lowest ones, okay? Also, the CompTIA Linux Plus may also require you to understand what the more common vulnerabilities are. And as you can see, outdated system, outdated devices, unsupported systems, being systems that they're very old, so there is no support to them anymore. Buffer overflow, very common, as we discussed in our previous video, right? The different types of attacks. So a system that is susceptible, vulnerable to buffer overflow can be easily impacted. Okay, privilege escalation is also very, very common. Most of the times, privilege escalation is a vulnerability that is associated with it's basically a human factor, a human error. Administrators or end users that do not follow the information security and password policy. That makes those passwords very vulnerable, easy to guess. And if it's a user account that has privileges, then you are allowing privilege escalation. Shellcoding is also another one. Shellcoding is a vulnerability that will, most of the times, it is combined with buffer overflow, but it's a type of vulnerability where if you know a specific code that may impact how the operating system manages that application, you may crash, or most of the cases escalate your privilege because of that shellcode that you insert into the main memory. For example, you are in a Linux system with a limited user account, a regular user account. Depending on the version of your Linux system, you may execute a shellcode that will instantaneously switch your limited account to the root user account. Also, insecure protocols, certificates that are not valid anymore, not recognized, certificates that are not issued, they are not verified by a certificate authority, DNS issues, and obviously information disclosure. Finally, misconfiguration, IoT devices, especially because IoT devices, they are fairly new, although they've been around for 15, 20 years, more commonly 10 to 15 years. But as far as the inspection of security, they are still unknown, therefore they are very vulnerable. People still don't know how to deal with these type of devices. All kinds of injections, whether it's a LDAP injection, SQL injection, XML injection, doesn't matter. It's very common to see, to identify injections as well. And cross-site scripting, also very, very common, because cross-site scripting is a type of web application vulnerability that exploits the client side, not the server side. Most of the times, administrators, they're more concerned about the security on the server side, and clients are not, most of the times, they are not a major concern. Okay, so for the CompTIA Linux Plus exam, as far as vulnerability scanning, you just need to understand how it's conducted, have some understanding of the more common vulnerabilities, and how it actually performs that scan. I hope you enjoyed this video. See you in our next one. Thank you.
Hello, welcome to our last module in our CompTIA Linux Plus prep course. And the last topic that we are going to address, actually, it's two different topics, but one is related to the other one. So first, we are going to talk about artificial intelligence, and which obviously includes some other resources, technologies, solutions under the artificial intelligence umbrella, which includes machine learning, deep learning, and artificial neural networks as well. But broadly speaking, we're going to talk about artificial intelligence. The next topic will be Python, using Python or preparing the Linux system to allow you to implement, to code in Python. But the reason why the CompTIA Linux Plus exam requires you to understand how you can prep your Linux environment for a Python, to deploy and run a Python code, is because of your possibility, your option to run artificial intelligence code using Python. Okay, but obviously that's what we're going to discuss in our next video. The same module, but another video. So first of all, we need to briefly understand what artificial intelligence is about, right? And obviously, since this is such a trendy topic, it's so modern, and it's all over the place, it's what everybody's using. I just want to make sure that you understand that there are different types of artificial intelligence solutions, right? Probably the most common one, the one that you maybe use on daily basis, right? Use very commonly, is called the generative AI. Generative AI is a type of artificial intelligence where this solution is capable of analyzing different sources of data, analyzing a data set or different data sets, and then based on that input, all that information, all that data that is provided to this artificial intelligence system, it is capable of generating an output. So it's not basically classifying or predicting, okay? It is capable of generating a result, okay? And in many situations, this might even be a brand new result. It's a result that does not exist. And obviously, that's why it became so useful, resourceful, and important nowadays, okay? But there are, like I mentioned before, there is also machine learning, deep learning, and artificial neural networks. Now, artificial neural network is a type of deep learning system, okay? And deep learning is also a type of machine learning. So we don't need to exactly understand the difference between those, because these are just some tiny details or even algorithms that will differentiate them. The difference is much more about which one would provide you with the best result. But broadly and generally speaking, they are the same in regards to what they are trying to accomplish, okay? And they are a type of artificial intelligence solution where you have a data set, right? A previous information, previous data that you feed to that system. and analyzing that data, the machine learning system will try to identify patterns so that it is capable of either classifying or predicting an output. So, for example, let's say that you have a business, right? And you want to know how many items you are going to sell next year, or a specific item, right? How many units of that specific item you are going to sell next year? Well, a machine learning system is the perfect solution to solve that problem. You basically tell this system, hey, this is how this is the number of items or units of this item that we have sold in the past, for example, 10 years, month by month. Okay, given this, the machine learning system will try to identify patterns to then being able to predict how many of those items, of that item, you are going to sell next year. Okay, but again, artificial intelligence, the generative artificial intelligence is the one that is most common. You can see that, for example, in image generation. We recently saw the trend of those images, those cartoon images being generated from a source, an original photo, right? We also use it on a daily basis when you're using a chatbot, right? You need the support from a company, so they provide you with a chatbot where you can enter some you can enter your question there, right, or what you're looking for, and that chatbot, that is not a person, it is a generative AI system that will analyze the words that you are inputting to then generate the result that you're looking for. Okay. Now, the CompTIA Linux Plus requires you to not only understand where you could use AI, broadly speaking, but also you need to understand why that is so resourceful, why it is so impactful, why it is so powerful. Well, with that being said, one of the things that is listed in their outline, in their curriculum outline, is use cases of AI. So you can use AI for code generation, documentation, and optimization, right? If you are a programmer, and obviously if you are a Linux admin, a operating systems admin, you are writing codes, mostly not a commercial application, but mostly scripts, which still you are going to write codes. So you can use AI to generate code for you, right? You can use AI to document what you're doing, document the code that you just wrote. And obviously you can also, let's say that you wrote your own script, not using AI, you wrote it yourself, but you want to optimize that script. You can use AI for code optimization as well, right? Now, another very common use of AI when it comes to system admin, and more specifically in code generation, you can use AI as a regular expression generator, also known as regex gen. And what happens is, imagine that you access a website and there is a form that you need to fill out, right? And you have one input field is asked for your full name, and another one asks for your email, right? And you type, let's say that in your email, in the email input field, instead of typing your account at gmail.com, you do your account.gmail.com. It will not accept that. It requires you to enter the @ sign. That's how it identifies that it is an email. You are actually using an email account. Well, there is a regular expression that was created, embedded into the website code to verify that, right? You can use AI to generate that regex, regular expression verification code. Okay, so for example, you can ask a AI system, what is the regular expression, or generate a regular expression to validate an email input field. Simple as that, right? Even ChatGPT, which was not written specifically for coders, for programmers, but even ChatGPT is capable of understanding regular expression generations. Okay, and also infrastructure as a code. These are the most common use cases of AI when it comes to a Linux administrator, a Linux admin. Okay, infrastructure as a code. That's when there are many solutions nowadays where you can write a code, and that code is that file, right, is what will be used to deploy an infrastructure, right? CloudForm, for example, that is a good example of that. Ocean as well. So all those cloud platforms where you do not have, you don't necessarily need to use their control panel to deploy your infrastructure. You can actually write a code that defines what your infrastructure will be, your virtual infrastructure will be composed of. The NML, Network Markup Language, is a good example of a infrastructure as a code. And you can use AI to generate infrastructure as a code, to write infrastructure as a code, also to optimize the code, the infrastructure code that you already have, and you can use AI to generate code reuse, right? So there are some, since you were writing that file, that infrastructure cloud file, there are some parts of that file, of the instructions that are in there that can be included in a method or function, if you will, right? Well, but when you wrote it, you didn't realize that. You can use AI to do that as well. Okay. Now, some concerns that the CompTIA Linux Plus exam has, and this is actually a concern in industry as well. AI best practices. Okay, so you need to ensure that you are using ethical, reliable, and impactful AI systems. You want to align the development with the business goals. So you need to make sure that you are tailoring the AI system that you're using. You are aligning it with the business goals. You cannot use a artificial intelligence system to generate generic responses, generic results. Okay, if the AI solution that you're using is not capable of analyzing your business goals, your unique reality, for whatever reason, right? Well, the output that it generates, you need to verify it and tailor it, adapt it to align it with your business goals. And obviously, you want to minimize risk and bias. Again, artificial intelligence systems, they are systems that they do not know your own reality, your specific reality. Okay, so you need to make sure that you are always verifying the output, the result that has been generated. Also, it's really important that you select and evaluate the model that you are using. Again, as I mentioned, generative AI is very common nowadays, but is that actually the best solution that you have for your specific situation? Also, among all the generative AI solutions that are out there, you have different algorithms. You need to understand those algorithms, those models, so that you can match it to your specific reality. So choose models based on task complexity and data availability. This is also very, very important, data availability. The accuracy and the strength of the result will depend on the data set that has been used by that specific AI system. Okay, so you need to make sure that you have a strong database, strong data set that is being used as input. So for example, like I said, like I mentioned before, ChatGPT is a more generative AI. It means, what I mean is, it is a generative AI system that was created to deal with any kind of problems or questions that you may have, where you have other solutions, right, that are written specifically to, for example,
resume.io. It's a website that uses generative AI, but that generative AI system was designed specifically to create resumes, CVs, okay? Obviously, if this is the goal, resume.io will give you a better result compared with ChatGPT. And always use baseline comparisons. Always use your original information to compare that with the result that was generated by the AI system you're using. And you need to continuously monitor performance metrics. Again, you should never rely 100% on the results that are being generated by your AI system, okay? You never know where the sources are coming from. You never know if there are biases being included for whatever reason. So you need to continuously monitor the results that you are getting from that AI system. Okay. Again, the model training and testing is also very, very important because this will define the result generated by AI. So you need to train on diverse and representative data sets. You should not use generic data sets. Okay? Try to use resources that are specifically associated with your own scenario. You should avoid overfitting, right? So you should use regularization and cross-validation. So overfitting there is always noise in any system, right? So for example, if you have if you're analyzing network traffic, right? Let's say that generally speaking, your network has a traffic of, let's say, 50 megabits per second. That's in average. That's what you get, right? Now, there is that is an average, but it's common to have some peaks of, let's say, 70, 80, even 100 megabits per second, right? And same thing when it goes down. Sometimes you have a traffic that is going down to even 0 megabits per second. Well, nobody's using the network. It's 2 a.m. in the morning, for example. Now, there might be some peaks where your network usage goes up to 1 gigabit per second. Now, is that normal? No, that's not normal. If it's a peak that happens, let's say, once a week or maybe once a day, that's a peak. That's not ordinary, right? So that's noise. You need to make sure that the artificial intelligence solution that you're using is not considering that peak as normal. It is considering that it can see that is a noise so that it doesn't consider that into your solution. And you want to split data appropriately, okay? Basically, you have a few phases when it comes to training and testing your artificial intelligence system. Again, even more so when it comes to machine learning, deep learning, and artificial neural networks. The phases are training, validation, and testing. Training is when you use the data set that you have and you feed it to your AI system saying, hey, this is the data set that I have. I want you to find identifying patterns here, okay? Now that you have identified those patterns, I want to validate what you're doing. I want to validate if you are actually capable of identifying those patterns. And once you have validated it, you're going to test. So now I have this brand new information. I didn't use it during the training phase. I didn't use it during the validation phase. I want you to look at this new data here, this new information here, and I want to see if you are capable of classifying it. So just an example here. In cybersecurity, you want to have an AI system that is capable of analyzing network traffic, and then when there is a malware, traffic data that is consistent with a type of malware, you tell your AI system, this is malware, this is malware, this is not malware, this is legit benign traffic, okay? Now that you have trained the system and validated the way that it works, validated how it identifies patterns, you take a new packet, a new network packet that is consistent with a malware, and then you feed it to your AI system and asks, is this malware or not? Okay, so that's the testing phase. You need to make sure that you are splitting your data appropriately. So for example, if let's say for the totality 100% of your data set, you use 20% for training, 10% for validation, and 70% for testing, you won't have an accurate solution. Okay, most of the times the testing data should be a lot smaller than the training data. Okay, that's what splitting means. Defining how much of your data will be used for each of those three phases. Another topic that you must be aware for the CompTIA Linux Plus exam is responsible use of AI. Okay, so you need to embed fairness, transparency, and accountability. You need to make sure that, again, the results that you're getting are aligned with your business goals, and obviously your business goals should include transparency, accountability, and fairness. Okay, you cannot have a biased result. Collaboration and iteration, that is another topic that you have to understand for the CompTIA Linux Plus when it comes to the use of AI. You, as the, let's say, the sysadmin, as the Linux admin, as the network engineer, whatever your role is in the company, you have to understand that you are not the one to dictate what is going to happen or how things are going to be done. Okay, the decision for that will mostly be made when you are interacting with other important roles, other important members of the organization. So you need to work cross-functionality. You also want to use agile methodology for fast feedback, because in order to speed up the process of deploying and using the AI solution, you need to give a feedback to the other members that we just talked about, right? The other members that are involved in that scenario. And you want to regularly retrain with updated data as stated before, okay? Also, AI data governance is really, really important. You must observe that when it comes to AI, the CompTIA Linux Plus exam is focusing a lot on the usage of AI, of artificial intelligence, for data governance at the managerial level. Okay, they're not so concerned about what are the technical implementations, the technical deployments when it comes to the use of AI. They're much more focused on the care, the concerns that you should have when it comes to using those solutions. Again, aligning it with the managerial, with the organization goals. Okay, so AI data governance is really, really important. And what that means is that you must have a framework or policies or procedures that are defining how AI is going to be used. That is for that's because you want to allow the management of the data quality, privacy, and compliance. And especially nowadays, with compliance being so strong and actually required in any environment, right? So you want to ensure the trustworthy of AI outcomes. You want to make sure that the results that are generated are reliable. That is because you have a few, actually three key principles when it comes to using AI in a corporate environment. You want to guarantee accuracy, consistency, and lineage, right? You want to guarantee that the data that you're using reflects reality. You want to maintain uniform formats, and you want to make sure that you know where the data comes from. That data, as stated before, that data must be aligned with your organization's reality, okay? You cannot use generic data. You cannot use any data. It's got to be reliable data, reliable to your situation, to your scenario. And again,
compliance is very, very important. In many environments, it's actually a law. There are regulations that regulate what your organization must do, how they must conduct their business, including how they use their information technology resources, right? So for example, in the healthcare system, you have HIPAA, which dictates, for example, how a hospital or a clinic should handle personally identifiable information, right? So there are many businesses that they must adhere to the GDPR, CCPA, HIPAA, PCI DSS, and so many other compliance regulations, right? You want to make sure that you are using anonymization and data minimization, and you want to implement data access control. All these go back to compliance regulations, right? You need to make sure that the data that you're using, unless it is not personally identifiable information, unless this is not sensitive information, you must make sure that it is not going to be exposed. Remember, AI solutions, AI systems, they are being used by different clients. So the information that you use in your AI system could be used by that AI. Well, it will actually be used by that AI system to provide output to other clients as well. Now, how is it going to be exposed, right? You have to be very careful in that regard. And the data lifecycle management is also really important because, again, the information, the data that is being provided to the AI system, and also the data that is being provided by the AI system as a result, must be dealt with care. Okay, so you need to define rules for the collection, storage, processing, and deletion of that data. You want to automate data retention policies, and you want to monitor for data drift. Okay. Finally, the governance tools and frameworks, they are out there, they can be used, right? So you can leverage those data catalogs and metadata tools for your own benefit, okay? You can use governance platforms integrated with AI pipelines. What that means is you can increase your data set by using government resources that are public, and you can integrate that with your AI so that you can either use it as a baseline to compare with the results that you got, or you can use it as a data set input to your AI system, okay? And the last topic when it comes to AI for the CompTIA Linux Plus exam is cares that you need to have when it comes to use an AI, the AI prompt. Basically, the AI prompt is that interface that you have, that you use to interact with the AI system. Like I mentioned before, if you're using a chatbot to ask a question, right? Well, the input field that you use to type your question, that is your prompt. So how you ask that question, the words that you use for that question are really, really, really important. So the AI prompt engineering is important for designing effective inputs to guide the large language modules. Large language modules are, that is the module that is used to analyze the input that is being provided, the words or the questions, right, that are being provided by the user. So you want to enhance the accuracy, the tone, and the reliability of the outputs. Again, try to be the most specific as possible when you are using an AI system, okay? Try to be also as descriptive as possible, which might be kind of ambiguous or even counterintuitive. How could I be succinct, right? How could I be direct, but at the same time also be detailed? But that's what you want to do. You want to detail what you want, but you do not want to use words or keywords that are not strictly necessary for your search or your question. So the design principles, when it comes to designing, either designing an AI prompt or using the AI prompt, you want to be clear, concise, and specific. You want to include context and format expectations, and you want to use examples to steer output, to dictate the direction, to determine where you're going, so that the AI system understands better what you're looking for, what kind of answer you're looking for. Okay? So that's what you need to know as far as AI for the CompTIA Linux Plus exam. And in our next video, we are going to see how we can use Python, or how you can set up your environment to use Python, and how you can integrate that, how you can allow your Python system to code artificial intelligence. Thank you very much.